And of course, this is a toy example. In general, I could have, a very large number of inputs and a corresponding number of, right? If I want to, let's say I have n inputs, right? If I want to not lose any information, right? If I want to have lossless compression, what's the minimum number of units that I need in the hidden layer? Log n, right? Anybody care to slightly refine that answer?
Log sub 2 of n.
Anybody care to refine it even more? Ceiling of log 2 of n. Okay, everybody agree? Very good. So this does perform something useful, right? And another reason why autoencoders are actually popular these days, they were actually popular in the early days of neural networks in the 80s, or in the early days of multi-layer neural networks, and they've actually come back big time in the last few years. You know why? Because you can use them. They're actually the most promising way, or one of the most promising ways, to build networks with many layers. And the way you build networks with many layers is that first you build an autoencoder, right? And then you take this layer as your new input, and you learn an autoencoder for that. Right? Potentially a very powerful thing. So hopefully what happens is that you learn more and more refined and more compact representations of the input, which after all is what your brain seems to be doing, with what you see, right? There's all these pixels, but then you see there's a corner here, there's a rounded thing there, oh, it's an ear, it's a nose, oh, it's a face, oh, it's my grandmother. Right? So maybe with autoencoders we can do that. Truth in advertising, we're not quite there yet, but nevertheless, autoencoders are an interesting thing. Now, the question for us here is, can we do this? Well, first of all, in principle, can we do this? Right? Before we worry about how we're going to do this with backprop, right? The question is, can we learn weights for these units that will learn a representation in here that will be lossless? Yes or no? This is actually not a question about neural networks. This is a question about digital logic.
I think yes.
Absolutely, right? What is the encoding that you need to learn for this?
Binary.
It's just the binary encoding of the input, right? I need to learn, for example, 00 for this guy, and 001, and et cetera, right? These three guys should be the binary encoding, right, of the inputs. So we can certainly represent it, provided we have enough bits, right? But the question is now, can we learn it using backprop? That's a much more interesting question. Well, let's find out. Let's actually run this, here's my input and corresponding output and so on. Let's try running backprop on this, right? I'm not going to do it live here for you, but here's what happens. Here are the hidden values that I learned. Right, so here's what happened. Here's what this table shows. When the input is 1000, right, with this particular run of backprop, my three hidden units, one of them has the value 0.89, one of them has 0.04, and the last one has 0.08. And of course, the desired output for that is 100. Yeah.
So what do you mean by the hidden?
The value of the hidden. So these are not
like the sum of all the weights.
No. The actual value, right? So remember, the value of the value at this output here, after the sigmoid. Right? So, this is the neuron, right? This is the output of the neuron that I'm talking about here. Right?
So it's the sigma function
yeah,
applied to the sum of all weights.
It's sigma of the sum, of the weighted sum of the inputs. Right.
So sigmoid applied to.
Yeah.
So then the weight from that first input to the first hidden thing is the 0.8 something that was.
No. So what's going to happen is that let me draw a little sigmoid here, right? What's going to happen is that let's say I have 1000000 here, right? And I have a bunch of weights, right? In particular, going to this unit, right? These guys are all zeros, so we can ignore them, right? So what's going to happen is that this guy times this weight through this sigmoid is going to be 0.8. Okay. And then, if things are working properly, this guy's output is going to be 1, and the other guy's outputs are going to be 0. Again, as a function of their weights and their sigmoid, right? This guy also has a sigmoid, and it has these weights. Okay? All right, so here's my great challenge to you. Can you squint at this table? This is from a real run of backprop, and see what it has learned. Remember, this is wetware, right? So things are not quite as clean as digital logic, but can you look at this and see what's going on? Notice that if you go through all these values, they tend to be either quite high or quite low, right? There's nothing here, between 0.3 and 0.7, right? So let's see roughly what this means, right? So 0.89 is roughly 1, right?
Right.
And this is roughly 0, 0.04, 0, right? So and now let's keep going, 0, 0, 1. Well, you see where this is going, right? This thing has learned the binary encoding of those, 8 inputs.
0.6 down there, though.
Oh, okay, yeah, well, where's the 0.6?
Bottom left.
Okay, very good. I like that. This is a perfect, illustration of, what happens in reality, right? Yeah, this guy was not quite perfect.
But this
is what happens with neural networks, right? They kind of get things more or less right, but, in the end, they still recognize their grandmother. But yeah, so, there was one failure here, which, again, is pretty typical.
Does that count as a 0 or a 1?
Well, you put it, it's neither a 0 nor a 1, right? It's actually in that, linear part of the sigmoid. So the question, though, right, is this going to work at the end of the day? At the end of the day, if your input was this, you're still going to get a higher activation at the right unit than at all the others. So this is still going to be doing its job despite being noisy here and there. And this is exactly how neural networks are, right? They kind of absorb the information, things are messy, but on a good day, when you look at what's happening at the output, it's the right thing. So it did learn the right representation, right? Let's see how it learned the right representation. There's also something, so this is one case where we can actually understand what's going on in the hidden layer. And more generally, the theme of this is that what the hidden layer should have learned is the important features of the input. Unfortunately, what it often learns is it's not like one unit learns one feature, but one unit learns a weird combination of 2 features and another one. So altogether they're doing the right job, but it's seldom the case that it's that clean. In this case, it was very clean. Okay? Let's see how this happened. Right? So here's the sum of squared errors for each output unit as a function of the number of epochs of training, right? And notice how disturbing this is, right? I was just trying to learn an autoencoder for, of 3 bits, and this took 2,500 epochs. Granted, this was a very crude form of backprop, right? So, today's autoencoders, are much better than this, so, don't panic. But nevertheless, look at what happened, right? Initially, the error was actually high for everybody, meaning they were just flailing randomly, they didn't know what was going on. And then what happened is that each of these curves is the error for one of the units, right? So there's 8 of them. Okay? Notice that they didn't all learn at the same time. First, one of them kind of started to figure things out, right? And notice how all these curves are actually sigmoids too, right? This is very typical. First, you have a hard time, figuring out where to go. But then you kind of start going in the right direction, and then, you make a lot of progress for a while. And then kind of things settle down again. And then, so there was this batch of units that figured out what to do first, and then there was another batch, and then there was a laggard. Yeah, maybe this is the 0.6 guy who still is confused. Okay? So this is how the errors evolve, right? Here's an even more interesting graph. This is the encoding in the hidden units of the input 0, 1, 0, 0, 0, 0, 0. Right? So each of these curves is the response of one of the hidden units. Right? This is the table that we had before. It was the table for all of the examples. And again, in the beginning, this is all random, right? So they're all basically, doing the same, slightly different thing, right? But not very useful. But then notice what happens. One of these has decided randomly at first that it's going to be 1 for this input, right? Notice that actually doesn't matter which code you assign to which input, right? As long as, there's a coherent code at the end of the day, right? So this one decided that it's going to be 1, and then it's going for 1, right? And then this other one, with some hesitations, but, equally fast on balance, decided it's going to go for 0, right? So for this input, 0, 1, 0, 0, 0, one of these units is going to be a 1, the other unit is going to be a 0. But the most interesting thing that happens here is with the third unit. The third unit actually changes its mind halfway through. At first it's going for 0, but then suddenly it decides it's going to be 1. And I'm not having a look at this in detail, I don't know exactly what happened, but I would hazard the guess that what happened here was that there was a conflict, right? There was a competition here between encoding this guy and another one, and at that point, this guy had to become different. Right? So in isolation, right, it would have been perfectly okay for these two to be 0. But there's some other one, there was some other input that was getting the same 0, 1, 1 code. And so at this point, one of them had to diverge. And again, because there's randomness, chances are one of them will do better than the other for one of the inputs and will evolve that way. Okay? So if you squint at it carefully, you can actually somewhat understand what's going on here. Okay? So finally, here's the weights from the inputs to one hidden unit. This is really what's controlling the behavior that we're seeing in the other two graphs. Okay? And again, in the beginning, they all start out random and small. Okay? And then what happens is that, as you might expect, some of them go to 1, some of them go to 0, right? Some of them do not entirely make up their minds, and they do not all evolve at the same rate. But by the end, right, we more or less are where we need to be. With a lot of noise, but, we still did enough to learn the right answer. And, once we're getting the right answers at the output, it doesn't matter how messy the input is, there's no more reason and there's no more mechanism for the weights to keep changing. Okay? Questions?
I mean, you mentioned 2,500, but that's not huge, right? This would take like a second to train, right?
Well, yes, sure. Because in this case, the
It's really
outputs are
simple.
short. No, but this is exactly. So the problem here is not so much in terms of CPU time, which in this case was cheap, right? But it's like you need 2,500 runs through all the examples to learn this very simple function. So now imagine a much bigger function, right? Now, truth in advertising, actually, an autoencoder like this is a hard thing to learn. And the autoencoders that people have these days actually use a very different idea, which is they actually have a much larger hidden layer, which makes things much easier. But then they have a term in the penalty function that forces them to be sparse. That makes many of them be off. And the representational power is the same, but not the landscape, right? This is all about finding your way, in those very difficult mountains becomes easier. So the landscape for this is actually pretty hard, right? There's a lot of these XOR type situations, right? If you think about it, learning an autoencoder, right? If you think of it in terms of digital logic, it's full of XORs, right? And if you have an autoencoder for things, like you don't have too many terms, right? Think of it in terms of a DNF. But learning an autoencoder for a large thing, well, that's a lot of terms in your DNF, in fact, an exponential number. Okay. More questions? Okay, so let's keep going. Let me just mention a couple more things about backprop before we conclude. One of them is, speeding things up. We've touched on these things before, but let's, systematize now. And then the all-important issue of overfitting. So, we know that we may not converge, in general, we will not converge to a global optimum, right? We're going to a local optimum. So, question 1, what can we do about that? Number 1, we can add momentum, right? We already saw how that can help. Number 2, we can use stochastic gradient descent. Right? Initially, people did it for the sake of speed, but it also helps to, with the issue of local optimum. And number 3, you can, do multiple runs with different initial weights. Okay? These are all simple strategies, and these are all recommended. Okay? Second aspect, right, is how do we converge, right? We want to initialize the weights near 0 because we want to start in the linear region. Okay? And then, as learning progresses, we get more and more nonlinear. Okay? So again, we've touched on this before, but let's bring those issues together here. Okay? Questions? Now, one question that we've always asked before, right, but we haven't gotten around to yet, except very very briefly, is so what can we represent with a multi-layer perceptron, right? Can we, for example, can we represent any Boolean function? Remember, we already saw the answer to this one today. But then there were all those beeps and they'd erased your memory. Right? We can represent any Boolean function with a neural net, with a multi-layer perceptron. How? Right? Let's say the function is in DNF. 1 unit for the OR, right? And 1 unit for each of the ANDs. Okay, very good. But what about continuous functions, right? This is the other interesting thing about neural networks is that, just like your brain, they don't really care about digital versus analog. They can do, both things. Can we represent any function, continuous function, right? So now thinking of a regression, doing regression using neural network, can I represent any function using a multi-layer perceptron? Well, this is not an obvious question, and somebody figured it out and then proved theorems about it. And here's the rule. If your function is bounded, meaning it never goes to plus or minus infinity, in fact, a network with one hidden unit, with one hidden layer is enough. But you might need an infinite number of hidden units. So that's the good news and the bad news. What is the intuition for this? The intuition for this is actually quite simple, right? Let's say you have an arbitrary function, right? You need to approximate this using a bunch of sigmoids, right? So how do you do that? Well, let me do this in color. What you do is you put one sigmoid here, right? And then you put a sigmoid with a negative, slope right here, right? And then another one here, right? And then you need to put a positive one here, right? So every time the function goes up, you put a sigmoid to make it go up, and every time it goes on, you put an inverted sigmoid to make it go down, right? So clearly, I can approximate anything this way. Also, clearly, if I want to approximate it exactly in the worst case, I need an infinite number of sigmoids, right? Because for unless the shape of that changes exactly sigmoid, which it generally won't be, I will need a lot of sigmoids to reproduce the function exactly, okay? Nevertheless, what this means is that, neural networks with sigmoids are a pretty good approximation for general functions. This is also true if you use radial basis functions as your approximant, right? With other functions, well, it depends on the function. Okay. Now, what happens if my function? If my function can actually go to infinity, right? Because a lot of functions go to infinity. At that point, actually, you can't do this with just two layers. Again, the reason for this is not obvious, but clearly that case is going to be harder, right? How do I make a jump that's both infinite in size and of the right shape, right? At that point, I actually need two hidden layers. But that's not bad, right? So, with a multi-layer perceptron with two hidden layers, I can approximate any continuous function. In the worst case, with a very, very large number of units. But, that's better than that. Okay? So this is good. This means that, neural networks are actually pretty general. And I can see the kind of argument that people used to have in machine learning circa 1990. It was like, the instance space learning people said, like, I have a theorem that says I can do anything with nearest neighbor, so why bother with the rest? And the decision tree people said, I have a theorem that shows you can do everything with the decision tree. And the neural network people said, like, I have a theorem that shows you can do everything with the neural network, so forget about the rest. The answer to this, of course, is that, sure, you have all these theorems, but they're not enough. It's not enough to be able to represent something. You also need to ask whether this is a better way to represent it in terms of being a more compact model, and very importantly, whether it's easier to learn this function with your representation than with the other one. And once you ask that question, which is actually the important one, in the real world, are you going to learn this or not, versus in principle, then none of these dominates. Sometimes the decision tree wins, sometimes the neural network wins. So, all those, ideological wars of the 90s, have, largely faded away, and good machine learning people today know to have many things in their toolkit. Back then, you'd have one hammer, whether it was backprop or decision trees, and you tried to hammer everything with it. This is not the right approach, right? And in fact, when we talk about theory next week, we will see some deep reasons why this actually has to be the case. Any questions about this? So, multi-layer perceptrons are expressive, but that's not the end of the story. Okay, so final issue, overfitting. As always, if your model is powerful enough, you need to worry about overfitting. And certainly, we just saw that the model is powerful enough. If you keep adding hidden units, you'll be able to model anything, even, be able to just memorize the input. Okay? So by the way, one of the things that people spend a lot of cycles on is figuring out how many hidden units to have, because that really is a crucial parameter. Okay? So here's another nice little example of learning curves. This now is with error instead of accuracy. And now this is my number of weight updates. Okay? And this is from a robot perception task. And again, we see the usual phenomenon here of the training set keeps getting lower. The training error keeps getting lower. But the error on the validation set, at first it goes down, but then it starts to slowly inch up, right? And what we would like to do, of course, is to stop somewhere around here. Okay? By the way, just so you don't get the impression that learning curves are always like this, here's another couple of learning curves from the same task. But, this always happens. This also happens. Here's my error on the training set, right? It looks beautiful. It goes to 0 very quickly. The error on the validation set actually does something a little more unusual, which is Yeah, at first this looks like, the normal thing, right? It goes down to a minimum and then it starts to go up again. But then, after a while it actually starts to go down again. In fact, you can prove, it's unfortunate, but you can, that in principle, anything can happen in a learning curve. Right? You have this very complicated landscape. Sometimes you slow down and then you speed up again. Sometimes you get stuck and then you come unstuck. You kind of inch your way across that plateau and then you find another, exit in this highly multidimensional space. So notice that in this case, I actually did not overfit. The best network was this one. Okay? Nevertheless, you should still not trust that network because notice there's still this very big difference between the error that you think you got and the error that you're really getting. Okay? Nevertheless, in general, you need to have overfitting control mechanisms, which, if this is the case, will let you go all the way to here. Otherwise, will make you, stop early. Okay? So, the question for us is, how do we combat overfitting in neural networks? And, here's 4 different ways, all of which have their pros and cons. One way, somebody had a question?
How it can learn something like sine curve where the input keeps on increasing?
One more time, sorry?
Like, how can neural network learn a sine functions, for example?
Oh, sure. That's a good example. Let me show you. Well, actually, I don't even have to show you. I'm just going to pretend that this curve was a sine. You see?
But the input keeps increasing and it has to extrapolate.
No, so remember, what I'm trying to do is this is my x, right? And I'm trying to learn to produce this y as a function of my x, right? So what happens is that I have a sigmoid for this part of the sine that goes up, and then another sigmoid of the same magnitude that basically takes you down again, and then another sigmoid that makes you go up again, right? So I can approximate. So now, truth in advertising, what I'm going to get is not exactly a sine wave. It's going to look, not quite the right shape, but it's going to be a fairly good approximation. Okay? And now if you want to make the approximation better, now you need to put some thinner sigmoids there to just make it be closer. But you can certainly learn it. Okay? All right. So, how do we avoid overfitting? First and most popular method is penalizing large weights. One of your homework exercises is actually about this. Right, so here I'm going to tell you how you do it, and then I'm going to leave you with all the hard work of actually figuring out how. But the idea is very simple, remember, if I start out with small weights, right, I have only a function which probably won't overfit, right? It's just a hyperplane. Overfitting happens when my weight starts to get large and I start to learn very complicated surfaces, right? So I can avoid overfitting just by making my weights stay small, okay? On the other hand, I don't want to hard bound my weights because what if someplace I actually do need a large weight, right? So what I want to do is and again, this is a very typical strategy in machine learning, is I'm going to add something to my objective function that encourages the right behavior without actually forbidding anything. And that something that I'm going to add is just the sum of the squares of the weights. Or, if you want to think about it that way, it's going to be just the squared norm of the weight vector, right? So I'm not going to like to have a large weight vector. I'm going to prefer to have a small weight vector. Meaning that for my weights to go up, that had better improve the fit by more than the penalty. And notice that, unfortunately, we have yet another parameter here to fine-tune, right? Which is my gamma, which is my complexity penalty. If my gamma is large, right, I will tend to stay fairly linear. If my gamma is low, I will let my weights become quite large, right? Unfortunately, you see why this is a problem at this point. It's I need to choose my number of hidden units. I need to choose my momentum parameter. I need to choose my weight initialization. I need to choose my, my complexity penalty. And now there's all these combinations, and each run takes, 10 hours. So things become painful. Okay, but nevertheless, this is a very reasonable method to, probably the most widely used method to avoid overfitting in neural networks. Okay, you do need to figure out, a good value for this parameter. Okay. The other thing that you need to figure out is, now that this is my error function, right, you need to figure out what the new rules for the gradient descent are, right? So what the exercise in your homework is take your, we did the derivation, right, for the weight updates with just this part. Now what we want you to do is to do it for the whole thing when you add the weight penalty part. Okay? Question?
Yeah. The question is, is it the large weight or is it difference between the weights? Because even if the weights are small, you could kind of have the same complex function, right? As long as
No, not really, because remember, yes, in principle, right? You might think, well, why aren't we invariant with respect to weight scaling, right? So the really important thing here is the relationship between the weights and the sigmoids, right? I want my weights to be small relative to the slope of the sigmoid, because that keeps me in the linear region. And remember, the key thing is that as long as I'm in the linear region, it doesn't matter how many hidden units I have, this is still just a hyperplane. And with a hyperplane, you're unlikely to overfit, unless it's a really, really high-dimensional hyperplane, which actually can happen, but let's not worry about that case. Okay? Okay, so a second idea, very devious one, is if you think about it, overfitting happens when instead of sort of like a smooth thing like this, right, I started really trying to fit all the data points very well, and then wound up with something that's like really trying to catch every point and is very jaggedy, right? Now, another way to look at this, which is like very natural if you come at this from the point of view of gradient descent and, backprop, is there's one, how would you characterize the difference between these two curves, right? One is kind of very smooth, right? And the other one jumps around a lot. But in terms of gradient, right, what this means is that the gradient here is always kind of low to moderate, right? And the gradient here can be very high, right? I can jump up and down, right? So the slopes are very different. Okay? Here the slopes are small, but here the slopes can be very large. Let's look at this point here, right? At this point here, let me zoom in, right? Let's say that the true value was this, right? This is what I'm trying to fit there, right? This is my x and this is my y, right? And I'm doing this, right? Actually, at that point, my overfit function is actually getting things right. Nevertheless, just by looking at that point, I can figure out that this function is overfitting. You know how? Right? How would you figure out that this function is overfitting? Because the slope is very different from the real slope, right? The function is the same, but the slope is very different. Right? Actually, I didn't put the slope of the real function here, so let's say that the slope was close to the one that I had there before. Okay? So the value is right, but the slope isn't right, which means that the value, delta, x over is going to be wrong. Okay? So the other thing that we can do is not just use the values, the target values for training, but also use the target slopes, right? I have that information, so why not use it? Okay? So what I'm going to do, again, is add a term to my objective function, right? So now in addition to my usual penalty, that penalizes the difference between the training, but between the target outputs and the outputs of the network, I'm going to penalize the difference between the slope of the output and the slope of the function that I currently have, right? If you think about it, if I learn the right function, I should match not only the values but also the slopes, right? And since backprop is already basically what it's doing is working with slope information, I can just throw that in. Okay. Truth in advertising, this method is not as simple to apply as the weight. People sometimes call this weight decay, because it makes what this does is it gives the weight the tendency to decay to zero, right? Which is also again kind of interesting related to human memory, right? Your neurons are not perfect, and the synapses in the absence of stimulation will tend to become weaker. And maybe that's actually a good thing if you think about it, in order to prevent your brain from overfitting. Okay, so this is often called weight decay. This training on slopes is not as easy to do and is less popular, but nevertheless, for some things it's actually, for example, say you're learning a controller, right? You're doing something for robot control. Training on the slopes can be a very good thing because you want the function to be smooth, for its own sake as well. Okay? Here's a third method, weight sharing. Overfitting happens because you have too many weights, right? If you only had a few weights, no matter how nonlinear things get, you really can't overfit that much, right? The idea in weight sharing is that I will have a lot of weights, but I'm going to make them similar. And now you're thinking, well, but what is the point of having a lot of weights if they're similar? The point is that there will be weights on different inputs. Where this is used a lot is in things like vision problems. So for example, there's state-of-the-art networks for character recognition that do things like process checks and process zip codes for the post office. There's a retina, right? Where the digit appears, like there's an 8 here. And you want to distinguish 8s from 9s and so forth, right? And now what happens is so neural networks are very good for this, and after all, it's what your eye uses, right? Is a neural network in your brain. But you want to learn, you have to put units, with weights over all of the pixels. over all the neighborhoods. Like there's going to be, a unit over here, a unit over there, right? And naively, you could learn different weights for all of them, but this is not going to work very well at all because it's too many weights, too much garbage, too much noise. What you want to do is you want to, put the same weights reproduced everywhere in the image. So what happens is that like you have this little, template neuron or neural network, and you just copy it. You translate it over the image. For those of you who know signal processing, this is doing a convolution, and those are often called convolutional neural networks, right? So weight sharing can be very useful because in some cases that's actually what you want to do, is you want to have the same model shifted over, right? Another application for this is things like speech and whatnot. But then you want to share the weights among those because, you don't want to have too much freedom. Okay? So that's weight sharing. The final one is actually the earliest one. It's early stopping, right? Early stopping is what kind of you immediately think of when you look at a diagram like this is, well, what I want to do is figure out that I need to stop here, right? And, the way to do early stopping is, of course, you have a validation set, right? You're using the training set to learn your weights and using a validation set to decide where to stop, okay? Very simple idea, right? Can also be very good for speed, right? Because often this last part takes a lot of time, but it's actually not helping you, right? You could actually speed things up by an order of magnitude with this on a good day, right? So this is one option, right? Now the interesting thing is that early stopping is actually equivalent to weight decay. Very surprising thing when people found this, right? For a while, both of these methods were around, and they tend to produce the same things, but that's because they were doing the right thing, right? But then someone actually figured out that these two things, at least in a proper setting, were formally equivalent. My question to you is why? Why would weight stopping and weight decay be equivalent? And notice that I said in the right setting, right? So they're not always equivalent, but they're equivalent if you do the kind of training with the kind of settings that we've been talking about. So why might that be the case? Let me give you a hint, right? They are the same if you do start with small random weights. If you start with large weights, they are not equivalent. So with that hint, why would they be equivalent?
So you're overfitting. Your weights tend to just get bigger over time as you keep training over and over again. So by early stopping, you're basically just stopping the weights before they get too big.
Exactly. If I stop the weight training early, I stop them from getting too large, right? If the weights start small, they can only increase by, order of the learning rate at every step. So early stopping means that I basically put a box on what the weights could be, right? And, you can also show that it's equivalent to put a box on the weights or put a panel like this on them. Right? Again, without getting into the math, the intuition is the same. Both of these prevent the weights from getting too large. So it actually turns out they're equivalent. And so often these days people just do, penalizing large weights because it's easier for the user, right? Somebody modified the objective function by putting in, the sum square of the sum of the squares of the weights, and now it's just one run, right? And you don't need to worry about validation and whatnot. You might still want to do it for other reasons, but okay. So these are some methods for avoiding overfitting in neural networks, and you will need them. Questions? All right, so that was our introduction to the wonderful world of neural networks. And now let us go on to something totally different. Model ensembles. We won't finish it today, we'll finish it next time, which is fine. But today we'll actually get to see at least the simplest of this class of methods that we're going to look at now, which is model ensembles. Model ensembles are actually now getting into the more recent machine learning ideas. The stuff that we saw up to now, appeared in the 50s, 60s, 70s, 80s. Now we're getting into the 90s. Okay? We're covering a lot of decades, as we go through the class. So what is the idea of model ensembles? And model ensembles is something that is really worth knowing about because it's not very complicated and it can really improve your accuracy. The basic idea in model ensembles is very simple, is don't just learn one model, learn a whole bunch of them. Part of what gave people this idea, actually people can make model ensembles from a whole bunch of different directions, but one of these directions is a very natural one, is like, people spend their days trying different versions of algorithms and different algorithms, and then they threw everything away and just kept one. Couldn't you really do something better with all those different variations that you tried? The answer is yes, you absolutely could, and we're going to see how. Okay? So, the payoff of learning model ensembles is that you get better accuracy, sometimes a lot better, sometimes shockingly better, right? Often with a very small addition to the algorithms that you already had, right? You already have this big bang of implementations of, decision trees and neural networks and naive Bayes and whatnot, and now you just have to wrap something around it, and suddenly your results get much better. On the other hand, there are two downsides, right? An obvious one is what? Speed, right? This is going to take longer, right? And the other one is, again, a model ensemble is going to be more opaque than just, say, a single decision tree. But again, you can imagine, and again, there's been work about that. Actually, I did some of it, come to think of it, on extracting comprehensible models from a model ensemble. Like I have an ensemble of trees, and I'm not trying to get a single tree that best approximates that. Okay? So, model ensembles, again, are not the panacea. They do have some disadvantages, but nevertheless, they're well worth knowing about. Some of the conventional wisdom is that some of the most accurate classification methods that exist today are model ensembles. Okay? And in fact, when you care about accuracy, almost nobody these days just goes and learns a decision tree, for example. They will learn an ensemble of them. Now, there's a whole plethora of methods. We're just going to look at 4 of the most important ones. The first one is bagging. Also, historically, the first one. And also the simplest one. This is a really simple method. And it's one that, is going to be in your homework. And then boosting, which is a fiendishly clever idea. We'll talk about it, probably next week. Boosted decision trees are generally considered, if I had to just give an advice on what would you use for maximum accuracy, it wouldn't be naive Bayes or nearest neighbor, right? Or even the single decision tree. It might be something like boosted decision trees. Okay, so well worth knowing about. And then we will look at 2 more. Error correcting output coding, which also does other things for us besides improving accuracy, as we'll see. And stacking, which is a representative of a very large family of what are called meta-learning methods. Stacking is I'm going to have a learning phase where the inputs to the learner are what the other learners did. Okay? Stacking is what really answers this question of I've learned all these models, can't I do something with them? Stacking is a good answer to what to do with them. Okay? So we're going to go over these. Again, there's many more, but these at least give you a good picture of the space. So let's start with bagging. Bagging is such a joyfully simple idea. It's like this. You have a training set. You learn a decision tree on it, right? This is the traditional thing. The idea in bagging is just the following. I'm going to generate random variations of my training set, right? In a way that we'll describe shortly, but I generally, let's say, 50 different variants of my training set. And then I learn a decision tree on each one of them or whatever, but let's say decision tree, right? These methods are usually very popular with decision tree learning for good reasons that we'll talk about next week. So I learned 50 decision trees, okay? So now I have 50 decision trees, and along comes a test example. What would you do?
Vote.
Vote, yeah, exactly. Remember, it's always a good answer to a lot of machine learning questions is vote. Whoever has the most votes from decision trees is the winning class, yeah.
How do you change your training set, every time you generate a tree from it? I mean, because if it's the same set,
of course,
you get the same tree every
yeah.
time.
So let's get to that question. You do this by generating what are called bootstrap replicates of the training set. In fact, this is an idea that came from statisticians, and what they did was extend to learning classifiers, something that had been around for some time and been heavily studied for doing things like estimating variances and means and the kinds of stuff that statisticians worry about. So what do? You create bootstrap replicates. Bootstrap replicates because what you're doing is you're pulling yourself up by your own bootstraps. What you would like to have, right, is 50 different training sets, but you don't. So what you have is one, and then you fake 50 different training sets. The way you do that is by sampling with replacement. It's a very simple idea. Let's suppose that my training set consisted of 1,000 examples, right? I'm just going to generate another data set of 1,000 examples in the following way. I'm going to randomly pick an example from the training set and put it in the new set. And then I'm going to do the same thing again, but with replacement. If I did it without replacement, I would just wind up with the same set again. When I do with replacement, what happens is that there's a certain chance that one example would get chosen twice.
Oh.
And a few examples will even get chosen 3 times. And there's an exponential decrease in
there will
probability.
be some samples that aren't chosen at all.
Exactly, and there's some examples that aren't chosen at all. So what happens at the end of the day is that you have a training set that's of the same size as the original one, and the important thing is that the statistics are actually still the same, unless you look at very fine-grained statistics, but the usual statistics are still the same. So this is sort of like where the statistician's knowledge was very useful, is that you've created a data set that statistically looks just like the real ones, right? It looks just like taking a new, sample from the original process. Of course, if you're looking at things like, well, how many times do you get duplicates? Well, now this is going to give the wrong answer because, you're going to get more duplicates than before. But in terms of things like averages and variances and whatnot, you actually get still pretty much the same thing, okay? And the procedure is very simple, right? Just sample with replacement. In fact, sampling with replacement in terms of implementation is easier than sampling without replacement, right? Basically, every time you just repeat the same thing of like randomly pick one of 1,000 and keep going, okay? And then what happens is that you have 50 different training sets, and 50 is not a random number. When you do bagging with 10, it improves things a lot. 20 improves them a bit less. 50 very little, and 100 is seldom worth the trouble. Okay, so 50 is usually a good number to go for. But if you're short of time, 20 is also okay. 10, you're already losing something substantial, right? You learn 50 decision trees, and then you just vote them. Very, very simple idea, right?
So you take an item from the test set, send it to all the trees, and whichever is the most common decision wins?
Yep.
Okay.
So here's this thing graphically, right? So I have my original sample. I generate my so-called bootstrap replicas, 1 to n. I apply my base learner to each one. We often, in model ensembles, we often call the learner that we're wrapping the ensemble over the base learner. There could be more than one. In this case, there's just one. It's the decision tree learner. Okay? But it could be something else, right? So I run it through the base learner, and of course, each one of those runs produces a different model, right? And then what happens when I have a test example is that, I just send it to the ballot box. Each of the models votes, you are spam, you are not spam, and then the majority class wins. Now the beauty of this is that after you've spent, in the old days, a long time implementing decision trees, these days you might just use an existing suite, but after spending a long time playing with your decision tree to, make it, do as well as possible, you do this to it, and your accuracy could easily go up by 5%, maybe 10%. And once you're into that part of the curve where you've gotten to 78%, but it's really hard to get to 80%, suddenly being able to get 83% is amazing, right? If you're a credit scoring company, 5% better accuracy is a big deal. If you're Google, 5% better accuracy on people clicking on the ads is a big deal, and you can get it with basically a couple hours worth of effort. So very worth having. Of course, it costs more cycles, but these days we have a lot of cycles. Now, what's the key thing that is essential for this to be useful? All right, let me put it this way. This will work for decision tree. Do you think it will work for naive Bayes? What if my Bayes learner was naive Bayes? What would happen? I generate bootstrap replicas of my training set, right? And I'm going to count how often the class occurs and how often each attribute occurs with each class, right? And what do you think is going to, these models are going to look like? Are they going to look different, or are they going to look similar? In the cases of naive Bayes, they're going to look very similar, right? Because bootstrap learners preserve those low order statistics. They are bootstrap replicates, right? That's what that's why they were designed, right? So this will not work with naive Bayes because you just get 50 times about the same classifier. The thing that's kind of perverse about this is that it will work very well for decision trees because of something that is actually a disadvantage of decision trees, or at least superficially a disadvantage, which is that, and I don't know if you've observed this, but you can certainly try it with your learner and something like the e-commerce data. What happens with the decision tree learners are very unstable, as are multilayer perceptrons, for example. Meaning that I change a few percent of the data in your training set at random, and you could learn a completely different decision tree. And this at first is very disturbing, because it means that you can't really trust what the decision tree looks like. Sure, it's accurate, but don't get hung up on all the details of what's in that tree. The upper levels, they're probably meaningful, but once you get down to the fine details, you run it again, you get something completely different. So decision trees are unstable. And unfortunately, instability and power go together, right? Naive Bayes is not unstable because it's also kind of dumb. right? So, smart algorithms, maybe like smart people, are more likely to hallucinate, right? You could be a genius or you could be a madman. So bagging is very easy, but it only works on learners that have this property of instability. Okay? The amazing thing about bagging and some of these other methods is that after all that we've worried about pruning, once you put an ensemble over things, exactly how much pruning you do doesn't really matter anymore. You probably still want to do some pruning, but the fine points of where you prune, you're probably better off under pruning. Why is that? Why would you want to under prune when you're going to run an ensemble? Right? Let me ask you the question this way. Should you run the decision tree learner with the same settings whether or not you're doing bagging?
No.
No, because?
Get very similar models again if you do a lot of pruning.
Exactly. If you under prune, right, the bagging will average out the overfitting. That's the beauty of it. Bagging is a great overfitting control technique. Right? One of them was like this, the other one was like that, right? Bagging, the majority is going to win. Only where the decision trees agree are they going to prevail. Okay. So bagging is very simple, but it's very powerful. When we talk about learning theory next week, we will see a more fundamental explanation of why bagging and other ensembles work in terms of two quantities called bias and variance, which are very popular among machine learners. But for the moment, we will just stay with this intuitive understanding. Questions about bagging?
Just to confirm, each of the base learners is exactly the same, right? I mean, they use
In bagging, each of the base learners is exactly the same, but it could also be different learners. Right? And again, we will see later some algorithms where the learners are different. In general, the theme in model ensembles is that you need some way to generate variation, right? The way you generate variation could be by varying the training set, it could be by varying the learner, it could be by varying the parameters, it could be, for example, in the case of backprop, by varying your initial weights. Okay? So there are many different legitimate ways of generating variation. For example, here's an interesting little point. There's actually a way to make bagging work with naive Bayes. You know how? Clearly, randomly selecting instances isn't going to help me, but is there something else that I can do that will generate a lot of variation?
Add noise, change the trading set.
Adding noise actually, again, doesn't work because it will tend to wash out, because I'm computing these very low dimensional statistics, right? Just how often each word occurs, right? But there's something with...
Add missing values.
Well, sure. I mean, there's a bunch of things that you can do, but let's suppose for a moment that there are no missing values, right?
Find naive Bayes with other types of learning trees or learning models? Like mix up with learning trees or something and bag them together?
Yeah, again, you could do that too. It's not the answer that I'm looking for, though.
Use different features maybe? Or?
Yes, exactly. What you can do is instead of doing, bootstrapping over the instances, you do bootstrapping over the features. Because with respect to those naive Bayes is unstable. You take out some of these high information features and now it's going to have to rely on others. And of course, in low-dimensional problems, there's not going to be much to do. But for example, let's say you're doing text classification, which naive Bayes is very good for, right? You have 10,000 dimensions, right? So there you have plenty of room to do, bootstrapping over the features. So, and you can think of your own, just as people did, right? You can think of your own way to generate variations of the algorithm or the data or whatever, and see if that works. In fact, there's a lot of papers in the machine learning literature about this, and combining these different methods and decision trees with naive Bayes at the leaves, with bagging over them and whatnot, right? So, okay, so in the 8 minutes that we have left, let's just at least give the gist of what boosting is. Boosting is one of the most famous algorithms in machine learning, and for good reason. Boosting is a shockingly accurate algorithm. And it actually comes from a different origin than bagging, and it's actually interesting to compare the two. Boosting is a great testament to the power of theory. In fact, the guys who invented this won this Kanellakis Prize for the, best theory with, real applications, right? You can win lots of awards for theory that looks pretty but never made a difference to anybody's life, right? But there is this, very prestigious award for theory that actually made a big difference. And boosting is a golden example of that. Because what happened with boosting is that boosting was invented as a way to prove a theorem. People were not thinking of coming up with a better new machine learning algorithm when they invented boosting. It was this guy called Rob Shapiro. And there was this problem that, the founder of one branch of, actually, Leslie Valent, who just won the Turing Award last year. He and one of his students, Mike Kearns, formulated this question. This is the kind of question that, theorists think of that often winds up having very important consequences. Their question was, what is the relationship between weak learning and strong learning? Weak learning is, my learner is just slightly better than chance. So a weak learner is a learner that is 50 plus epsilon% accurate, okay? Assuming the base rate is 50%, okay? And the strong learner is a learner that's 100 minus epsilon% accurate, right? Now, what you would like to have, of course, is a strong learner, right? What you have most of the time is a weak learner, right? And their interesting theoretical question is, are the two equivalent, right? Just like, is P equal to NP, right? And their suspicion was that, no, they were not equivalent, right? I mean, just because the learner is weak, just because you can learn slightly above chance, surely doesn't mean that you can learn almost, with complete accuracy, right? And then, this other guy, Rob Shapiro, came along, and he actually proved that weak and strong learning were equivalent, which was, a big surprise. He proved that if you have a learner that is 50 plus epsilon% accurate on any distribution, and that is the key condition, it has to be 50% accurate on any distribution of the instances in space, then you can, boost, and hence the name boosting, that weak learner into a strong learner, right? And this is an amazing thing to have, right? You have a learner that is only slightly better than chance, and by putting into this magic machine called boosting, you get a learner that is almost 100% accurate. But, he was a theorist, he proved his theorem, made a big splash and went home happy. Right? That was part 2 in this story. Part 3, another guy, these were all at different universities, over a span of a few years, called Yoav Freund, and it was Freund and Shapiro who won this award because they both contributed. He came along and said, maybe I can turn this into a real algorithm. And now the version of boosting that Rob Shapiro had was like a very ugly thing. Right? No one would want to use that. And in fact, it wasn't very good in many ways. So what Yoav did was he found a way to turn that into like a good, high-performing algorithm. So there were all these steps, and then the final step, which in some ways is the funniest one, is that these were still just theorists, right? What they did was prove theorems for a living. They proved a bunch of things about this, but then they were by this point they were at Bell Labs. Right, the famous Bell Labs. But these were the decaying days of Bell Labs when AT&T was, going downhill. And they were starting to be under pressure to show that they could do something useful with their theory. At which point, there was this contact between the theoretical and the empirical machine learning community, and they were like, oh, why don't we try this on these data sets in these, repositories, the famous UCI repository that people have been trying their algorithms. Let's try boosting on this and see what happens, right? It's not that hard. We can do that, right? They probably couldn't build a big system, but 100 lines of C code they could put together. And then they run it, and that's when their jaw dropped. Because these were data sets where people had been struggling to get 1-2% improvements in accuracy for 10 years. And they were getting 5-10% improvements in accuracy just like that. And the rest is history, as the saying goes. So, what is the boosting algorithm? Right? The boosting algorithm is a very clever idea. It's similar to bagging in some ways in that what you have is you learn many classifiers and then you vote over them, but the difference is that now there's going to be the examples are going to have weights. I'm still going to it's similar to bagging in that I generate different classifiers by learning on different variations of the training set, but now the variations of the training set are not random. They're designed. Because if you think about it, is it that really the best thing that I can do in order to generate different classifiers, just randomly generate different training sets? How about after I've learned my first classifier, what I do is I cleverly perturb the data to learn a classifier that is good where the first one was bad. This is what I want to do, right? I don't want to learn another random classifier. I want to see, where was the first classifier good? Well, that part of the space you can leave alone, right? That's fine. Where was that classifier getting things wrong? Let me now try to learn a classifier on that, and so on. Right? Now I learn my third classifier where the previous ones were bad. And so by the time I've learned 50 classifiers, if I've done this right, I've actually learned a very good classifier. In fact, if I could have 50 weak classifiers turning into one strong classifier. by weighted voting among them. Okay, so that's the general idea in boosting. Very, very clever. Okay, so here's what's going to happen. I initialize with uniform weights, just like a normal learning, right? This is my full training set. It's not a bootstrap replica. It's my full training set, and all the examples have the same weight. And then I just go into the following loop. And each cycle through the loop is often called a round of boosting, right? So one of the parameters of the algorithm is going to be the number of the rounds of boosting that you want to do. And again, as a rule of thumb, 20 rounds is probably good, 50 is fine, 100 is too much, 1,000 is bad because you'll probably overfit. With bagging, you can never overfit. We will talk a little bit more about that next week. With boosting, if you take it too far, you can overfit. Okay? Because you can start learning, a classifier just for here and one just for there and overfitting the noise. Okay? So what is each round? Is you apply your learner to the weighted examples. Okay? So you need a learner that can take in a set of examples and weights for the examples. Not all learners can do this, but again, in another fortunate accident of history, remember, how we handled missing information in decision tree learning was by having fractional examples, right? 80% of the example goes to red and 20% goes to blue. Because of that, people like Quinlan already have algorithms that could handle, weighted examples, right? Because what is a fractional example? It's a weighted example. And so luckily, all they had to do was expose that and wrap boosting around it. If, however, you really, have a black box learner that doesn't handle weights and you don't want to modify it, there's a way to do this which works almost as well, which is, again, what you do is you do the bootstrap idea. You sample from the training set, but now it's with replacement, but now what happens is that instead of sampling with uniform probability, the probability is the weight. Okay, the weights all add up to 1, and you just create a training set where the examples that had more weight are more likely to show up and, will show up more times. Okay? And the ones with low weight maybe will show up once or 0 times. Okay? So even if your learner doesn't take in examples with weights, you can still do boosting quite successfully. So you apply your learner to your examples. Out comes a classifier, and now here's the key step. You look at which examples were misclassified and you increase their weight. Right? Now there's some very interesting theory behind this, but intuitively this makes a lot of sense, right? So the next classifier is going to focus on the examples that were bad for the first classifier. I'm going to increase the weight of those. And if there are some really difficult examples that the classifiers keep getting wrong, their weights are going to go up round after round after round until I'm really just learning a classifier for those examples until I'm guaranteed to succeed. And this is how you can get a strong learner out of a weak one. Okay? And we will see the details of and finally, you combine the models by voting, as before, except that now, of course, the voting is also going to be weighted. The classifiers that were more accurate have more weight than the ones that were less. Again, this makes sense, right? Why make a uniform vote when some classifiers are better than others? Okay? And next week, we will look at the details of boosting, and then talk about some other models, some methods, and do some learning theory. Okay? And in the meantime, have fun with your strand classifiers and so forth. All right, let's get going. Today on the menu we have two things. First of all, we're going to finish model ensembles, which we started last week. And then we're going to switch gears and talk about learning theory. Okay? So first of all, boosting. Last time we talked about boosting and we saw the general idea, and today we're going to see the details. So as a recap, the general idea in boosting is that we're going to have weights for the examples. And then what we're going to do is we're going to apply the classifier, the learner, to the weighted examples. Okay? And then the whole trick is that then we're going, after each round of boosting, as it's called, we're going to change the weights of the examples to make the classifier focus on the examples that the previous classifier got wrong. Okay? So the idea is that we keep shifting our attention to the examples that are being misclassified, and at the end of the day, we're going to have a collection of classifiers that together will do much better than an individual one did. Okay? So this was the general idea. Now let's look at the details. So there's many versions of boosting. It's a popular algorithm. The best known, probably most widely used one is something called AdaBoost. And it's the one we're going to look at here. So AdaBoost has 3 parameters. The first one is a training set in the usual form of pairs of examples and their classes. Okay? The second one is a learning algorithm. Right? This learning algorithm has to take in not just the training set, but weights for the example. And we saw last time what to do if the learner doesn't allow weights, right? We can just sample according to those weights. But for now, let's just pretend that, yes, we can have weights. And the classifier, and then the learner outputs a classifier that predicts a class for each example, okay? And the final parameter is the number of rounds k. This is the number of times that we're going to do boosting, and therefore is the number of classifiers that we're going to have in the final ensemble, okay? And then predictions on new examples are going to be done by voting among the classifiers in the ensemble with weights that we'll see. Basically, the more accurate classifiers will have higher weight, which is the natural thing, okay? Okay, so how does add a boost work? Well, first of all, we're going to initialize the weights to be uniform, okay? So if I have 1,000 examples, each one is going to have a weight of 1 over 1,000, okay? And we're going to need to keep the weights normalized, right? So the weights always have to add up to 1, okay? You can think of the weights as a probability distribution over the training set, okay? So now, in each round of boosting, from 1 to k, we do the following. First of all, we renormalize the weights. Now, in the first round of boosting, the weights don't need to be renormalized because they started out normalized, right, by design. But as we shall see in later rounds, we need this renormalization step, okay? And then what we do is we call the learner on the training set with these weights, right? Whatever learner that might be. It could be a decision tree learner, it could be, back prop, it could be whatever, right? And this learner outputs a classifier. I'm going to call that classifier HR. So this is the hypothesis H in the round R, okay? And then what I'm going to do is I'm going to measure the error rate of that classifier on the probability distribution represented by the weights, right? The whole idea here, as in bagging, is that I'm going to pretend that this probability distribution over my training examples is the real distribution, okay? So, and if that's the case, then my error rate is really just the sum over all the examples, right, of the weights of the examples that the classifier got wrong, right? So if the classifier got the example right, its contribution is 0, right? It doesn't contribute to the error. But if the classifier got the example wrong and its weight was, say, 0.02, then this makes a contribution of 0.02, okay? So epsilon r, as we're going to call it, is really just the probability, the total probability of the examples that the current classifier is getting wrong, okay? And this epsilon r is going to play a crucial role in the algorithm. Any questions so far? Okay, so far so good. And now comes the following proviso. If this epsilon r is greater than the half, we're hosed. Why are we hosed? Remember, the whole idea of boosting is that it turns a weak learner into a strong learner, right? A weak learner is a learner that is accurate, 50% plus change. If the accuracy of this classifier is less than 50%, then the weak learning hypothesis is failed. Right? So we're outside the assumptions of boosting, and as you'll see, what we're going to do next will not work. In fact, it will do something very crazy if the error of the classifier is actually more than 50%. Okay? So this is actually potentially a problem. Right? What we do in this case is we basically throw up our hands and say, this hypothesis is bad, I'm going to reject it, and I'm just going to return my previous classifier, okay? Or my, if this was my round R, right? What I'm going to do is I'm going to return not k rounds of boosting, but only R minus 1 rounds of boosting, right? I'm going to stop at the previous ones, okay? So in particular, if this happens at the very first, with the very first learner, then basically boosting doesn't do anything useful, okay? Luckily, as long as the learner is powerful enough, this will not happen. Right? This might happen if the learner was a very weak learner, right? Even weaker than 50 plus epsilon. But if the learner is something like a decision tree, most of the time this will happen. Unless we're in the situation of having a problem with many classes, in which case we might need to do something else, which we will look at later. Okay? So now let's assume that we did indeed get an error rate that was less than 50%. Okay? Now what do? We compute this very important quantity called beta r. Beta r is just epsilon r, the error, over 1 minus epsilon r. Okay? So epsilon r is the weight of the examples that the classifier got wrong. Therefore, 1 minus epsilon r is what?
The number got right.
It's the total weight of the examples that the classifier got right. Right? Okay, so my beta is just the ratio of those two things. Okay? You can call it the odds of getting the example wrong. Okay? Very good. And now comes the key step. This is the step where we reweight the examples. And really the cleverness is in this step. So how are we going to reweight the examples? Here's what we do. You see this exponent here? This is just saying that, so this is my current weight WR of I. So the weight of the ith example on the current rth round, okay? My next weight for that example, WR plus 1 of I, right, is going to be the previous weight times beta raised to this complicated thing, which is just 1 minus indicator function, blah, blah, blah. Ignore the math details. Here's what this is doing, is if my current classifier is getting the example right, that's what this is saying here, then I'm going to multiply the weight by beta. Okay? So for each example that my current classifier gets right, the weight is going to be multiplied by beta. Okay? For each example that the current classifier gets wrong, this is 1 minus 1 is 0, so I don't multiply by anything. The weight stays the same. Okay? So, after this step, what has happened is that the total weight of the misclassified examples is what? Actually, that one hasn't changed, right? Because remember, if the example is misclassified, its weight doesn't change, right? So the total weight of the misclassified examples is still what?
Same as it was.
Same as it was before, epsilon r, right? Very good. What is the new total weight of the correctly classified examples? This is the important part, right? It used to be 1 minus epsilon r, right? But I multiplied all of them by epsilon r over 1 minus epsilon r, right? So what is the new total weight? It's the old weight, right, epsilon r, right, times what each one of them was multiplied by, right, which is 1 minus epsilon r over epsilon r, right? So it was 1 minus epsilon r, right? The previous weight of the correctly classified examples, right? And now I've multiplied it by, let me correct this, just a second. Right? I put this in backwards. Times epsilon r over 1 minus epsilon r. Right? So what is the new total weight of the correctly classified examples? It's just epsilon r, right? So, an interesting thing has happened, is that the total weight of the correctly and incorrectly classified examples is now the same. Right? So what happens after I renormalize? What's the total weight of them going to be? Remember, after renormalization, right? After renormalization here, right? The weight of the weight of all the examples correctly and incorrectly classified is going to be 1, right? So what is the total weight of the correctly classified examples going to be? It's going to be a half, right? Because they're the same, right? Before renormalization, they were both equal to epsilon r, right? So they were the same. Right? Now they're still the same, but they add up to 1, which means that they are now both equal to a half. Aha! Very interesting. What I have done is rejig the weights of the examples such that the accuracy of the classifier on this training set, the accuracy of the most recent classifier in the training set, is equal to random guessing. It's 50%. What this reweighting has done is that it has made my classifier basically be as random as possible on the new data set. Right? On the old data set, the classifier had whatever accuracy, let's say 70%. But now what I've done is I've changed the weights of the examples, right, such that the accuracy of the classifier is now 50%. And what this is really doing is basically saying, I'm going to create a new training set such that on this new training set, my old classifier is as good as random guessing. And this is the new training set that I'm going to pass to the next round of learning. Okay? So this is not a formal proof of anything, but it should give you the intuition of what's going on in boosting, right? Is that boosting is like, you can think of each classifier as capturing some information about, the real distribution and, and what the classes are. But in some sense, what this reweighting does is it zeroes out that information. It says, well, Now let me look at the things with respect to which this, classifier doesn't know anything, and focus on that. Okay? And then I just go to the next round. And now in a new classifier, which will have its own accuracy, and then I again reweight the examples to make that classifier be, maximally uninformed, and I keep going for my set number of rounds. Okay? So at the end of the day, I have a bunch of classifiers, and finally, when a new when a test example comes along, what do? What I do is I vote among all these classifiers with the following weights. Log of 1 over beta r. So, it makes sense that the weights should be dependent on the error, right? So the more accurate the classifier is, the greater the weight it should have. The particular form log of 1 over beta r, the reason this comes about is that with this algorithm and these weights, they were able to prove something which is not obvious, which is that as long as I have a weak learner, at the end of the day, I can, with these weights, I can perfectly classify the training set, no matter what that training set is. Provided that in each round I can get an accuracy of at least 50%, okay? Or 50% plus epsilon, okay? So that's boosting for you. Questions?
So is this guaranteed to improve or reduce the error rate? Or I assume that's if you do infinite number of rounds of proof.
Yes,
Okay.
but notice that this is on the training data, right? So this proof that they have, in some sense, doesn't prove any. It's not obviously a priori that would be the case, right? But in some sense, what's been proved is not that interesting. It's just that, I can memorize my training set, right? What's interesting is that I can take a very poor learner, right, that is barely better than random guessing, and I can concoct this thing around it that lets me memorize the training set. But if all I wanted to do was memorize the training set, I could have just, learned the decision tree with, one leaf per example, right? The interesting question is, how well is this going to generalize? And the whole thing that's exciting about boosting is that this generalizes much better than learning a decision tree like that. Okay? How many rounds of boosting you want to use in practice is actually an interesting question, because it gets into issues of overfitting. With bagging, you never run the danger of overfitting, because basically you're just averaging. But with boosting, you could overfit. And this makes sense, right? If you have the ability to perfectly learn the training set, by definition, you have the ability to overfit. Okay? But what turns out to be the case is, actually, in the beginning, when people first tried boosting, they actually thought it didn't overfit, because they were only doing maybe 50 or say 100 rounds of boosting. And with that number of rounds of boosting, because what they saw was that things asymptoted, right? And they were like, okay, we're good. And they were getting very good results with that. But then somebody said, well, let's just do a lot more rounds. And then what they found is that at some point, you started to overfit. And obviously, the noisier that it is, the sooner you will start to overfit. So with boosting, you have to worry about overfitting. But one way to hopefully not have to worry about it too much is to do just something like 50 rounds, and that'll probably get you as good a result as you're going to get. More questions? So it was not obvious when people first came up with this algorithm that this was going to be so good, but it is very good. And people have come up with various theories to explain why it is good. And we will talk about some of these theories in a little bit, not just apropos of boosting, but apropos of a whole bunch of different things. Okay, so let's go on to the next method, which is error correcting output coding. And error correcting output coding was invented for a totally different reason. It wasn't because learning a model ensemble is more accurate than learning a single classifier. The interesting thing is that all the methods that we're going to look at, they all came about at around the same time for completely different reasons. Was it a coincidence? I don't know. So error correcting output coding was invented as a way to solve the following problem. Suppose I have a classifier that only works for Boolean classes. Okay, it's a binary classifier. It just learns concepts, chair or not chair, dog or not dog. There are actually many classifiers like that, and we'll see some in the future. Like, for example, your basic support vector machine is like that. Okay. Also, something like boosting, as we just saw, can run into problems if you have many classes, because then the probability of each class is very low, and getting above that 50% threshold can get very hard. Okay? So for all of these different purposes, you often would like to have some sort of nice thing that you can wrap around the binary classifier and turn it into a multi-class classifier. Okay? And so this is what error correcting output coding was invented for, and you can use it for that. But then what people found to their surprise is that this actually turned out not only to turn a binary classifier into a multi-class classifier, but often a classifier that was actually much more accurate than you would think. Like, for example, you might have the binary version of, say, a perceptron, right? And apply this to it and have, the multi-class equivalent of a perceptron, which is learning a hyperplane for each class, and then, a function for each class, and then picking the one with the maximum value. This often gives much better results. So even when there's a multi-class version available, sometimes you're actually better off using error-correcting output coding. Okay? So let's see what error-correcting output coding is, and leave for later the question of why this might work so well. And as a quick preview, one standard explanation for all these things work well has to do with the notions of bias and variance, which we're going to look at in a little bit, and you may have heard of already. Okay, so how does error-correcting output coding work? It's another one of those superficially very simple ideas, but actually remarkably effective, right? And if you guys know about things like communications and whatnot, you might already have heard of error-correcting output coding because people there use it for the purpose of, ensuring reliable communication by essentially adding redundant bits, or at least that's the simplest way to do it. So here's what we're going to do, right? We have a binary classifier, and we have, say, a problem with, like 5 classes, A, B, C, D, and E, right? And the problem is, how can we build a classifier for 5 classes out of a classifier for only 2 classes? And here's the idea in error-correcting output coding. I'm going to form a binary problem out of, say, my 5-class problem by randomly aggregating the classes into superclasses. Okay, I'm going to say, well, A, B, and D are going to be my class 0, and C and E are going to be my class 1. Okay? And I pick this randomly. And in fact, if there aren't too many of these, I could even do it exhaustively. I could try all 2 to the 5 combinations of them. Okay? Now, now I have a binary problem, right? I've replaced my labels ABD by 0 and my labels CE by 1, right? And I just have labels 0 and 1. I can apply my binary classifier. Okay? Now, of course, the output of this binary classifier on a new example will tell me whether I'm in this group of classes or this group. But for example, if the winner is 1, it won't tell me whether it's C or E, right? So how do I get around that? The idea in error-correcting output coding is just do this many different times. Right? So one time C will come together with E, but maybe another time C will be in 0 and E will be in 1. Okay? So if I do this a whole bunch of times, at the end of the day what happens is that each class, you can think of each class as being represented by a binary vector. For example, the class C might be represented by the vector 1, 1, 0, 1, 0. That's what its representation would be if I have formed 5 binary problems, right? In the first binary problem, randomly C was in class 1, right? C was considered to be a subclass of the superclass 1. Same thing on the second problem, but then on the third one, it was in 0. Okay? So for each class, I'm going to have a little binary vector of this form, right? And then, and in this case, I also have 5 classifiers, but there are 5 binary classifiers. Okay? And now what do I do at test time? Well, you're probably already guessing what I'm going to do at test time, right? Is I'm going to apply each classifier to the test example, right? And now when I apply a classifier to the test example, right, it produces a prediction, right? Let's say that the prediction that it produces is, 1, 1, 1, 0, 0. So meaning the first classifier produced 1, the second classifier output 1, and the last 2 output 0. Okay? So now how would you pick the class? Right? Over to you. Right? I ran my 5 classifiers, the first 3 output 1, the last 2 output 2.
Hamming distance.
Hamming distance, right? How do you figure that out? Did you look at the slide? That's cheating.
Took my working last quarter.
There you go. Yes, exactly. Yeah, exactly. Like, if you know any, communications theory, you know what's coming, right? So Hamming distance, right? Everybody here, I assume, knows what Hamming distance is, right? And what that's going to do is going to say, I'm going to pick the class whose vector most resembles the one that was output, right? If my class C, let's say, sometimes was a 1, sometimes was a 0, but the classifiers always tend to output the superclass that it was a member of, well, then this class is probably the right one. Okay? Everybody got this?
Could you explain how you got the code for C, for example?
Yeah. So let's look back at that, right? So remember, what I do is I form a binary problem by randomly assigning the classes to superclasses. Like for example here, I assign A, B, and D to 0, and I assign C and E to 1, right? And now I have a binary problem, and I learn a classifier for that, right? But what this means is that for the first problem, for the first classifier, C is 1. Okay? And let's say that I'll do this again, and again, by chance, C winds up being assigned to class 1, then I get a 1. And now let's say that when I do this for the third time, so I'm going to form a third random binary problem, C this time gets assigned to 0. Okay? Now, then my third bit is going to be 0. Okay? So what happens is that if I formed n problems, right, in each one of those problems, C was randomly assigned to one class, this is just the vector of the classes to which it was assigned. So this says that in the first problem, C is a subclass of class 1. In the second problem, it's a subclass of class 1. In the third one, it's a subclass of class 0, and so forth. Okay?
However, that's a training time,
Mm-hmm.
right? So but it's random. So there's no fixed code for C.
No, but for each of these, it's randomly generated, but after that, it's frozen, right? And now what happens at test time, right, is that, think about it this way, is that if at test time the first classifier outputs 1, right, that classifier is telling me this example must be either C or an E, right? So I don't know whether it's C or E yet, but hopefully there's a later bit, right, where C and E differ. Let's say in that later bit C was 0 and D was 1. But if now the classifier outputs 0, then maybe then it must be C. Okay.
So all the learners that you learn are there.
Yeah, exactly, precisely. Yeah.
Why do we do this randomly? Like, I mean, to me it seems like you'd be better off if you came up with an encoding that would maximize the distances between each of your final classes so that you could more easily distinguish them. But if you're doing it randomly, it seems like you have two that are like right next to each other.
Absolutely, right. And in fact, this is what people first did, right? You know, they did the right thing, right? But then they tried random, and the random actually worked better, right? This is a common phenomenon in machine learning. Right?
Okay.
Is there a very definitive answer to that? I don't think so. I think it avoids overfitting and things like that. Right? Again, if you don't have too many of these, right, you could actually just do exhaustive, right? And that one, you know, is quite sound. I wish I had a better answer for you, but you know that, yeah. Doing it non-randomly is actually also more complicated, right? So people put themselves through the trouble of really engineering their right, and then random, and then somebody basically just said, well, I'm just going to do this at random, right? What the heck? Because it's easier, and then that actually tended to work better. So people almost always do it random these days, or exhaustively. So, yeah. But if you're an electrical engineer and you believe, in your principles, then you can just do it, the optimal way. Which basically consists of over-dispersing the bits to make sure that there's as little overlap as possible. Another way to look at this is that, if you make this vector long enough, right, at some point it actually doesn't matter, right? Because you have, the discriminability is going to be there anyway. The chances that, if you think about, like when would doing things randomly hurt you, right? That would be if I wind up with two classes that are not discriminable, meaning like they had the same representation in the entire bit, in the entire vector. And this becomes exponentially less likely to happen as your vector gets longer. So, questions? Okay. So that's error correcting output coding for you. Another very good tool to have in your toolkit. Again, notice that this is another one of those techniques where, there's a simple thing, easy to code that you wrap around your classifiers, and suddenly they can learn on multiple classes, and they're probably also more accurate. Okay.
Is there a certain number of groups you need to do for it to actually work?
Again, this is like the number of, resamples in bagging and the number of rounds in boosting. There is no, universal number, but probably if you do something like 50, it's a good number to use. And these numbers don't come out at random. They have to do with the fact that the variance goes down with the square root of number of the number of samples that you have, right? So if you think about the variation of the square root of n as n goes from 10 to 20 to 50, this is a pretty good decrease. From 50 to 100, you get a small decrease that's probably not going to show up. And then from 100 to 1,000, it probably doesn't matter. Okay? But if you're using this in practice, it does pay to experiment a little bit. Although, when you're doing this in practice, you have, 50 parameters to play with, and actually this is not one that I would focus a lot of attention on. I would just, stick with 50 and worry about other things. More questions? There is some theory about these things as usual, but, a lot of this theory is not something that you can say just, like, the theory tells me to use this number and I will use it. Right? Because at the end of the day, it depends on the characteristics of the problem, so there's really no replacement for, using a validation set or something like that, despite all the theory that exists about it. And, and we will see some of that theory shortly, which, can certainly give you guidelines. More questions? Okay, so finally, let's look at stacking. So the idea in stacking is, I've run 20 different learning algorithms, each with 1,000 different parameter settings, right? And that's, 1,000 parameter settings is easy to come by, right? It's just 3 parameters with 10 settings each, and you're at 1,000. And now, instead of just picking the best one, maybe there's some way to actually combine them all and get a better result. And this is the idea in stacking. And your learners could be anything you want, right? Anything you have in your toolkit, right? Run your suite, burn the cluster, run 500 decision trees, 1,000 nearest neighbors, right? This is what people did in the Netflix prize. They literally had like hundreds of versions of, each of these things. 100 versions of matrix factorization, 100 versions of, or 500 versions of restricted Boltzmann machines, which is a type of neural network and whatnot. Okay. So now what do you do with those? Stacking is an example of a class of learning techniques that are called, that go under the general heading of meta-learning. Meta-learning, as usual, the term meta, right? What this means is that it's learning about learning, right? So what you're going to do is you're going to learn about your learners. You're going to figure out how good each learner is, right? And then use that to combine them, okay? So what I'm going to do is I'm going to run a learner whose inputs are the outputs of the other learners. Okay? This is what stacking is going to do. We call it stacking because, we're really stacking learners on top of each other, right? So we're building a stack of them. And, this stack in principle could have many levels, but in practice people just use 2, like this. Okay, so here's how this works, right? I have my examples, right? I run them through my different base learners, right? And then what I do is I take the outputs of these learners. So notice, when I was learning a decision tree, right, the input for the decision tree were the attributes of the example, right? Whether or not, my email contained different words and whatnot, okay? Standard learning. And then the decision tree outputs, let's say yes or no, okay? Now the output for the meta-learner, the input for the meta-learner is the outputs of the learners. Like say, for example, here, let's suppose that I just have one decision tree learner, one naive Bayes classifier, and one neural network, right? The input to this meta-learner would be vectors of 3 features. 3 binary features, supposing that the problem was binary. Okay? So I take all my classifiers and I take their outputs and I form a vector, right? And now now you see what's going to happen here, right? Is like that vector of outputs of the classifiers is my input, and the output is the real class of the example. Okay? So now what my meta-learner is a very clever idea if you think about it. What my meta-learner is going to learn to do, right, is it's going to learn to predict the real class of the example as a function of the classes that the base learners predicted. Okay? And your meta-learner in principle could be anything, but what people have generally found is that it doesn't pay to have a very powerful meta-learner. Like, for example, people looked at using a decision tree as a meta-learner, right? In this case, use this, in that case, use that. But it's actually tricky to make this work well. Can you guess why? What is the danger in having a very powerful meta-learner?
Overfitting.
Overfitting, yeah. Yeah, see, you guys are experts now, right? But why? Tell me why, right? Getting the right answer is not enough anymore, right? We already know that the answer is overfitting. Why is there a great danger of overfitting if I have a powerful meta-learner? Well, think about it. A decision tree is a powerful learner, right? As is, say, a neural network, right? Naive Bayes not so much, but actually, naive Bayes, if you have 10,000 input words, can already start to overfit, right? Because you could have some random little word that correlates very well with your class. This whole thing together is a super powerful learner. But this is the problem with meta-learning, right? Is that meta-learning is, overfitting potential taken to the next level. right? So it's very easy to overfit massively. This is not to say that you couldn't use, say, decision tree as a meta learner, but what people typically tend to use is something, simple like, say, a linear regression or a logistic regression. So they just learn a weighting of the classifiers, right? You can think of, bagging has no weights on the classifiers, boosting has its clever little scheme for adjusting the weights of the classifiers, right? But it has this very sequential flavor, which makes it not a very good candidate for large problems, right? Here, I can learn all these classifiers completely in parallel, right, using a big cluster, right? And then what I learn is the weights for them using, something that learns weights like linear regression, for example. Okay? There's one more very big issue here, right? What we've actually seen so far is not yet a good stacking algorithm. What would happen if we use the stacking algorithm the way I just described is, what? For example, let's say that I had learned, my best decision tree and my best neural network and my best naive Bayes. Like, let's say the neural network was learned using, backprop. You know what would happen here? Can anybody guess? This is hard to guess, but hey, surprise me. Let me ask the question in a slightly more concrete way, right? So let's say my meta learner is, some sort of, regression, right? Linear regression. And I learn a weight for the decision tree, a weight for naive Bayes, and a weight for the neural network, okay? Who do you think is going to have the biggest weight?
Whichever is more accurate.
That's what we would like to happen, right? But is that what's really going to happen? Here's what the problem is, right? This is actually something that you probably don't remember by now, and neither would I if I was you, but remember when we saw that naive Bayes has a tendency to be overconfident? Right? Naive Bayes is a dangerous classifier because it's highly prone to hallucinations, right? The probability of plus was 55%, but naive Bayes thinks it's 99%. Okay? And the problem with the meta learner is that it's in risk of believing naive Bayes. Right? Naive Bayes says, I'm really confident that this is a 1. Right? And the decision tree, which actually knows a little bit better what it's doing, says this is probably a 1. And the neural network, which is actually probably the best one for accurately computing these probabilities, right? Because decision trees are not as prone to overconfidence, but I might have a leaf with 5 examples in which 4 of them, were positive. Naive Bayes thinks it's 99%. The decision tree thinks it's 80%, and the neural network, which is actually the most accurate thing, thinks it's 65, right? But naive Bayes is confident, and the meta learner believes naive Bayes. So the problem with doing things the way I've just described is that they run a risk. So some classifiers are, the technical term for this is calibration. Some classifiers are naturally better calibrated than others. The calibration of naive Bayes is very poor, right? It tends to be all or none, right? For reasons that we saw before, right? And calibration can interfere with stacking, right? What we would like to have, so one option is to recalibrate the classifier such that they now all, have the right distribution of, positive and negative confidence, but this is a lot of trouble, right? Another thing that you can do is use cross-validation. Cross-validation makes things a bit more costly, but it's the simplest solution to this problem, and it's a very effective one. So what we do is the following. Remember, what I want to do, right, is I want to assemble a training set for my meta learner, right, out of the predictions of my classifiers and the right class, right? But the problem, right, is that if these are the predictions, right, of my classifiers on the example that I'm now seeing, right, there's nothing preventing this from overfitting, right? So what I want to do, and this is the slightly clever thing about stacking, is what I want to do is that I want these to be predictions of the classifiers on this example when they did not have it for training. That's the key. I'm not willing, I, the meta learner, am not willing to look at the predictions of the classifiers on the examples that they were learned on, right? Because I already know those are going to be probably overfit, right? Again, maybe more for some than others, but I'm not going to trust the classifiers on that. Okay? So what do? I do cross-validation. Meaning, with some number of folds, people, if the learner is not too expensive, this can actually be done. Leave one out, right? But let's just say we do 10 folds, right? So here's what happens: is that like I learn my classifier and say this 90% of the data, right? And then I make predictions on 10% that I didn't see. Okay? And then it's those predictions that I'm going to put into my training vector for the meta learning. Okay? With live one out, this would be I learn on all the examples except one, right? And then I run, let's say, the decision tree, right? I learn my decision tree on all the examples but one, and then I use the decision tree to just predict the one example that it didn't see. Okay? But this now is, is a fair prediction, right? Because it's a prediction on unseen data. And that's what goes into that example, right? Let's say that this was example 51, right? For example 51, I'm going to have here the prediction of the decision tree when 51 was held out, and the prediction of naive Bayes when 51 was held out, and so on and so forth. Okay? And if I go through each example, leaving it out, at the end of the day, what I have is, a good training set for the meta learning, because now the meta learning is really going to learn when these guys are active, when they aren't. Okay? Questions? Mm-hmm.
I don't think I follow that last step. So you're talking about, so you're now saying that you drop out some of the first level of learners for the leave one out?
No, I don't. The beauty of this, remember, as always in cross validation, is I'm still using all the data. I pay a price in that now I have to run the learners multiple times, right? So, but let me put it this way. Let's briefly go through this again. I have example 51. Right, which used to have some number of attributes, 100 or 1,000, that all these classifiers, ran on. Okay, but the question is, how am I going to assemble example 51 for the meta learner? Okay, it's going to have its real class coming from the training set. Right, this example was a 1. Okay, it was a chair or whatever. Okay, and now this here, right, is the prediction of the decision tree. Okay. And this here is the prediction of naive Bayes. Of course, in reality, that would be 100 different versions of decision trees and so forth, right? And this here is the prediction of the neural network, right? And now the question, right, the key point is, where does that prediction come from? I don't want this to be the prediction of the decision tree that was learned on the entire training set, including 51, right? Because then I'm going to be rewarding the decision trees that are more overfit, right? Bad idea, right? By that standard, the more overfit you are, the better. So what am I going to do is, I'm going to hold out example 51. Right? Let's say there were 100 examples, right? I'm going to have examples 1 to 50 and 52 to 100. And I'm going to run my decision tree learner on those examples. And out comes a decision tree. Okay? And now I use this decision tree for the sole purpose of predicting the class for this example. Okay? And let's say that on this example, the decision tree predicts 0. Well, it got it wrong. Okay? You follow? And then I do the same thing for the others.
Right.
So, we're paying, notice that this is expensive, right? Because I'm building all these classifiers just for the purpose of classifying one example. Like I said, you don't have to do this with, leave one out. You could do it with tenfold, it's going to slow you down by an order of magnitude, but hey, or maybe you just need, 10 times more cycles on, the Amazon cloud or whatever. Okay? Questions? Okay, very good. So that was model ensembles for us. Let us now look at learning theory. So we've spent several weeks looking at different kinds of learners, right? And we actually covered quite a few by now, right? Now you have a good sense of the variety of inductive learning methods that are out there, right? Another thing that you've probably noticed is that there are certain themes that keep recurring, like overfitting, the curse of dimensionality. How much data do I need? Can I be confident that I have learned a good classifier, right? Is this really going to work well on new data, right? And so far we've sort of done this piecemeal. We said well, here's a heuristic way to avoid overfitting in decision trees. Here's a way to avoid overfitting in neural networks. But maybe there are more general ways to deal with these problems, right? Maybe there are good ways to explain when a classifier is doing well and not doing well, right? You've just ran your bag of tricks and nothing is working. Right? This is a common experience, right? Usually what happens in practice is one of three things. Nothing works. Everything works. There's problems on which everything works right out of the bat. They're easy, you're off to the races. Some problems, there's a couple of things that work, but maybe not quite as well as you'd want to. So in those and in the ones where nothing works, now you need to figure out what should I do. Right? Are there some general ideas that you can sort of have in your toolkit, independent of the particular domain or the particular algorithm? Indeed, there are. and that's what we're going to see today. Okay. So the first thing that we're going to look at is a very famous result in machine learning called the no free lunch theorems. Right? You've heard the expression that there's no free lunch, but in machine learning this actually has a very precise technical meaning, and we will see what it is. And it's going to be very shocking, so be prepared. Don't have a heart attack. And then we're going to look at these notions that I already alluded to a couple of times of bias and variance. Bias and variance are, two of the most useful things that a machine learner could have. And then we're going to look at pack learning. PAC is not political action committee. It's probably approximately correct. Okay. There's also six-pack learning, which you do once you're starting to get happy. But this pack. The probably, the P stands for probably, and the A stands for approximately, and C for correct. So this is probably approximately correct learning. And this is a bit of a mouthful, but by hedging it twice, probably and approximately, you can get a lot of results, right? Leslie Valiant got the Turing Award for this. Big deal. Right? Back in the 60s, people had all these negative results about the things that you couldn't learn. And, it was kind of demoralizing for a while. But once you go into the PRAC framework, suddenly a lot of interesting things happen. Okay, so, worthy of a Turing Award. And then we're going to look at the notion of VC dimension. VC is short for Vapnik-Chervonenkis. Vapnik and Chervonenkis are two Russian scientists that invented this notion. And what it's going to allow us to do is to generalize the notions of PAC learning to continuous spaces. So first we're going to look at discrete hypothesis over the discrete attributes like Boolean, but then we're going to want to generalize this to continuous spaces like Rn, and VC dimension lets us do that. Okay, and then next week we're going to look at a major application of these ideas, which is support vector machines. So support vector machines are one of the best performing and most popular types of learning these days, and they basically come out of this theory. Okay, so another reason why it's worth knowing this stuff is that it's going to lay the groundwork for support vector machines next week. Okay. All right. So let's start with the no free lunch theorem. What does it mean in machine learning that you can get a no free lunch, and what consequences does that have for your daily life? So no free lunch theorems are about the generalization accuracy of learners, as opposed to the accuracy. So what is the difference between accuracy and generalization accuracy? So remember, there's accuracy on the training set, right, which we know is not interesting because it's easy to get 100% on that. But then most of what we've looked at so far, and most of what statisticians have traditionally looked at, is your accuracy on the whole distribution. Okay? The thing about accuracy on the whole distribution is that it allows you to get these asymptotic results that if I see infinite data, then I do very well. But if you think about it, all these results, they're not, in some sense, they're not very satisfying, because if I see infinite data, well, then I've seen everything. So if I just memorize it, right, then of course I can do things well, right? So in some sense, all these asymptotic guarantees that, most random statistics papers have, they really don't do what you want, right? Because in reality, in the real world, you don't have infinite data. You haven't seen everything infinitely often. The whole point is how well you generalize to the examples that you have not seen. Right? So generalization accuracy is the accuracy on the non-training examples. Okay? So as I see more training examples, right, those don't count anymore. I'm still only worrying about the non-training examples, which in any realistic setting are always going to be the vast majority of your examples, right? I'm never going to be in the regime where I've already seen everything infinitely often. So this is really the setting that is important in practice. So, we can put all those asymptotic results on hold and say, what happens in this case, right? And this is what the no free lunch theorems are about. Okay? So let's call, curly F the set of all possible concepts. And, there's many versions of the no free lunch theorems for continuous domains and, with various, options and whatnot. Here we're just going to focus on the simplest setting and the essential, reason for the no free lunch theorem. So let's just assume that, again, I'm in this Boolean setting. All my attributes are Boolean, and I'm just trying to learn a Boolean concept, right? Not because the ideas don't generalize to other settings, they do, but because it's the simplest one. Okay. So The set of all possible concepts, then, if I have, n Boolean inputs, it's just the set of all 2 to the 2 to the n possible Boolean functions. Okay? So this is what I'm interested in. Okay? The role of my learner is to pick one function out of those 2 to the 2 to the n. Okay? And so my function is f of x, right? X is the input, and notice that x is a vector, it's in bold, and y is going to be my output, which again, let's suppose is just binary. Okay? It's a yes or a no. Okay? So let me start by stating the no free lunch theorem. The no free lunch theorem says that for any learner, right, this is a completely universal theorem. There are no exceptions to it. The average generalization accuracy of that learner, average over all possible target concepts, right? I'm applying, learning to a new problem that my boss or my customer just gave me, right? I don't know what the right function is, right? It could be anything, right? And what this theorem says is that, on average, over all possible functions that I could be learning, you know what the expected accuracy of my classifier is? 50%. Random guessing. Right, so a shorter way of saying this is that no learner is better than random guessing in general. So, before you mob me and shout at me for having wasted all these hours of your time, right? Let's first see why this is the case and then why it's not the end of machine learning, right? I remember, the guy who first came up with these ideas was a physicist named David Walker, right? Who became widely hated for doing this and other things as well. But, he also tried to unify Bayesian and frequentist statistics. Right? Remember when we talked about Bayesian versus frequentist statistics? This was all part of the same line of work, which I think was a very meritorious idea, but what he managed to be was, hated by both the Bayesians and the frequentists. So he also proposed this theorem, and then, somebody came up, I think it was, one of these learning theory guys, David Housel, came up with the notion with the name of no free lunch. But the version that we're actually going to look at here was a guy called Colin Schaefer. And he called it a conservation law of generalization performance. And I actually saw him give, one of the early talks about this, and I could see, the anger on people's faces as he gave this talk to a machine learning audience, right? Because he seemed to be saying that, what you're doing is useless, right? Your classifier is never going to be better than random guessing. Right, so, first of all, let's see why this is the case, and then let's see why it's not the end of the world for us. Okay? So first of all, are you surprised by this result or no? Right, just give me your gut feeling. Right? Does this come as a surprise to you or not so much? There is no wrong answer to this question, so what is yours? Are you surprised or not? Some of you look surprised. Some of you look amused, which I think is the right reaction.
What I'd say is for any learner, does that include all the really, really, really bad learners?
No, actually, yes, all the really bad learners for sure, and all the really good learners. That's what's disturbing about this, right? I'm a machine learning researcher. I spent my whole life coming up with better learning algorithms, and this theorem is telling you that they're no better than the bad ones. In fact, Cullen went on to write a paper about learned decision trees with using, instead of trying to maximize information gain, trying to minimize it. And to try to show that did as well as maximizing information gain, right? This is all profoundly disturbing, right? Basically says what are you guys spending all your effort on, right? Why come up with a better learning? Just flip the coin. Okay, so first of all, let's see why this is the case. And notice, the proof of this is in just these 4 lines. So it is not a very difficult argument. Again, if you read, Walpert's papers, it's a little bit more complicated than this, but the basic argument just goes like this, right? How do we prove that the average generalization accuracy of a learner, whatever the learner, is always going to be 50%? Irrespective, notice, of the distribution over the training examples, right? The training examples could have any distribution that you want, and your training set size could also have any distribution that you want, right? Having a larger training set size doesn't buy you anything here. For accuracy, it buys you something, right? Because you've seen more of the distribution. But remember, if you're focusing on generalization accuracy, a priori, all those examples that you've seen don't actually help you with respect to the new ones, right? this might remind you of something that we did on, week 1, but, week 1 was a long time ago, so if it doesn't remind you, that's okay too. But so let's see what the reason for this is, okay? The reason, the chain of reasoning behind this is very simple. It's like this. Let us take a concept, a particular function f, right? I have now chosen out of my space curly f of all possible functions a particular Boolean function that is the one that we're trying to learn, okay? And let's say that my learner L, so there's a real function that I'm trying to learn, and I'm bringing my favorite learner that I put all my work into to try to learn that function, okay? And let's say that the generalization accuracy of my learner on that function is better than random, a half plus delta, right? This delta is the result of all my hard work, right? I'm doing better than flipping a coin, right? This is what I bought by developing, this great crackerjack learner, right? And, the delta could be small or it could be large, right? It could be, another half, in which case, my learner, just nails down that concept, right? So things are looking good, right? I have a learner L that can do better than random on this function, maybe even a lot better than random, okay? Now, here's the crux of the matter. For each such concept f, there is guaranteed to exist a concept f prime where the accuracy of my learner is a half minus delta. So if my learner was 75% accurate on f prime it's going to be 25%. If it was 100% accurate on f prime it's going to be 0. Okay? And you see that if this is the case, right, then immediately this follows, right? Can anybody tell me why that follows? Well, what is the average accuracy of the learner L on f and f prime? 0.5, right? Well, now I can group all my concepts into pairs, right? One member of the pair, the accuracy is a half plus delta, another one is half minus delta, right? So the average on those two is, a half. And now what I have is an average of a half times, the number of concepts over 2. Mm-hmm.
When you say concept, do you mean like a test data set? What is concept?
Remember, concept is a Boolean function. Right? There's a natural Boolean function that goes from your Boolean attributes to your Boolean value. Right? Remember, we're trying to learn a function, right? We're trying to learn a discrete function, and in particular in concept learning, we're trying to learn a Boolean function. So concept is just a Boolean function. There's a real function, right, that will produce the results for all your test data, and it has also produced the results for your training data. Remember the example that we had back, in week 1 of, here's my table of the function, right, x1, x2, x3, and here's my y. And I have seen, the examples 0, 0, 0, and y is 1. And then there's a bunch of examples that I haven't seen, right? And here's, 1, 1, 0, and here it's 0. Right? Remember this? Right, this table is what I'm trying to learn. My training set are the lines that I've seen. Right? My test set are all the lines that I haven't seen, or it'll be a subset of those lines. Does that answer your question? You still seem a little puzzled.
But the concept is the complete truth table once you have all the...
Yes, exactly. The
training.
concept is the complete function. You agree?
Okay.
You still seem puzzled. Yeah.
It's a related question. So, for example, if I knew this was a Boolean function, I would have a learner that tests all the values, and if I had a data set that's the size of a truth table, then what is the concept that I couldn't learn from?
No, but remember, I'm interested in the generalization accuracy. That's the key. I'm only interested in the accuracy on the examples that you haven't seen. If you've seen all the examples, the generalization accuracy is undefined. But remember, in the real world, you've never seen all the examples, right? There's way too many. Okay. Any other questions?
So
Why does f prime exist?
No. Okay. Very good. Wait, that's the key, right? That's the next step, right? But for a moment, let's suppose that f prime exists, right? First, I would like to convince you that if f prime exists, then the accuracy of my learner is 50%. Irrespective of how much training data I have, I'm allowing myself to do exhaustive search. I can have an infinite computer, right, with infinite resources. None of that saves me, right? Somebody was saying like, well, why can't you exhaustively try all possible concepts? You absolutely can. Try all possible concepts. That is still not going to save you. Okay? As long as it is the case that for every concept f where you're delta above chance, there's a concept f prime where the accuracy is delta below chance. Okay? So everybody agree with this part of things, that from this follows this?
So
Okay,
when you say
very-
different concepts, do you mean like using a neural network with different weights, or like using a different algorithm to create a neural network?
Any of the above, right? So notice that for this theorem, we're actually not concerned with how you generate your hypothesis, right? Again, imagine that you're able to generate all of them. It could be using a neural network, this learner L, let it be your favorite learner, whatever it is, right? If you're a big fan of backprop, this is backprop, or your version of backprop, or whatever, right? So this applies to any learner, so pick whichever one you want. Okay? All right, so why is this the case?
Because no matter what I happen to learn or figure out to predict, I can pathologically choose to make all of my generalized answers the exact opposite of everything I predicted.
Yep. Did everybody follow this? Right? So more precisely, right, there's all, this is an existence argument, right? I just have to be able to construct that concept, right? Now, the most obvious answer to this question, which is not quite right, is I could have a concept that is the, so here's one answer that is not quite right, is how about I make my f prime be f but flipped, right? Where f was 0, f prime is 1. And where f was 1, f prime is 0, right? So these concepts are the exact opposite of each other, right? Which means that on all the examples that I haven't seen, right, wherever one was right, the other one was wrong, okay? So if one of them has accuracy half plus delta, obviously the other one has the accuracy half minus delta. Okay, you agree? But this is not quite the right answer. Why? Is this what you were suggesting?
I'm suggesting that it is the opposite of f for everything you have never seen.
Mm-hmm. Right, but what about the things that I've seen? Right? They have to agree on the things that I've seen, right? They have to agree on the training set. So they can't just be the opposite of each other, right? So what do they have to be? They have to be the same on the examples that I've seen and the opposite on the examples that I haven't seen, right? Making them the same on the examples that I've seen, by definition, makes them indistinguishable, right? As far as my training data goes, I cannot tell the difference between these two. Because if I could tell the difference, then there would be some classifier that potentially, based on that difference, would learn one thing for one and another thing for the other, and defeat this. Okay? But if they're exactly the same on the training data, then there's no way to distinguish them based on the training data. But then on the test data, they're exactly opposite, meaning that every point of accuracy that one of them gets above chance, the other one gets below. Okay? Notice it's a very simple argument, right? But it was only in the late 80s, early 90s that somebody actually came up with this. Machine learning had existed for let's say 40 years when that happened. Did everybody follow this?
But why do we, how do we assume that the number of concepts of type 1, how do we assume that there is a one-to-one mapping between the number of concepts of type 1 and type 2? It could be one-to-many or...
There is no type 1 and type 2, right? All I'm saying is, you give me a concept, right, where the accuracy is a half plus delta, and I will give back a concept where the accuracy is a half minus delta for any learner. Okay?
But is that actually possible?
Pardon me?
But is that actually possible to get something like that unless you're deliberately trying to make it opposite?
We just, right, that's the question, right? But we just show that it's possible, right? This is the argument, right? Like, let me construct that for you, right? So you give me your concept where your learner is 75% accurate, right? I will give you back a concept where your learner is 25% accurate. And the way I'm going to construct that concept is I'm going to make that concept be the same as the first one on all the training examples and be the opposite on all the other examples. Right? It's shockingly simple. Okay, now this has a very important corollary, which is that give me any two learners, L1 and L2, right? Let's say, you're a big fan of decision trees and you're a big fan of, neural networks, right? This says that for every learning problem where the decision trees win, there exists a learning problem where the neural networks win. So all those arguments that people used to have about like, well, neural networks are better because it's what the brain does, or, symbolic learners are better because this is what, intelligence really is all about, right? All those arguments basically crumble to the ground. Nothing is always better. Right? You see why this follows from this theorem? Right? I mean, think of the random, of a coin flipping learner, right? The simplest possible one, right? This is true between every learner and the random learner, right? Therefore, it's true between any two learners, right? In essence, this is what the reasoning is. Okay? For every learner where the decision tree was better, right? For every concept where the decision tree was better, right? Where it was a half minus delta, whatever that was, right? I can using the same recipe produce a concept where it's now the neural network that's better. Okay? And so on for any pair of learners that you might care to produce. Okay? So this raises, any questions about any of this? So this raises some profound questions about the usefulness of machine learning, right? What is all this brouhaha about, right? Why is machine learning so important, right? If you could just be flipping coins. Okay? What does this really mean for you? Well, remember Ross Quinlan, the inventor of decision trees and the foil first order learner and whatnot, right? One of the most famous, most widely cited people in machine learning, and the UW alumni, right? He did his PhD here. I remember him giving, a keynote talk at ICML, one of the top machine learning conferences, where somebody, this was at the time that these results came out, and somebody told him, but aren't you worried about the no free lunch theorems, right? Don't they make all of this useless? And, Ross is like this very calm and flappable guy, and he looked at, at the person and said, like, well, no. The no free lunch theorems are like the death of the solar system. It's going to happen someday in the distant future, but in the meantime, you can live your life and not worry about it. And luckily for us, he was right. Now, why was he right? So, now this is my next question to you: is why does this not, here's the theorem, right? Why does this not imply that machine learning is useless?
Not all concepts are equally useful. For example.
Exactly. Yeah, absolutely. Notice this thing here, that I'm doing an average, right, over all possible concepts, where they all have the same weight. Right? It's 1 over the size of curly f. Right? But in the real world, not all concepts are equally likely. Of course not. Very far from it. Right? The whole reason why we humans are able to learn in the real world and machine learning algorithms are able to learn in the real world is that the real world is not a function randomly selected from the set of all possible functions. Hell no. Right? And when you get to a new application of machine learning, there's always this pathological possibility that it's like something completely, out of left field. But most of the time it's not, because, the world does have regularities. And, in some sense, the power of machine learning comes from the fact that there are some very general regularities that our learners can exploit that are enough when combined with data to do quite well. And in a sense, our job, as developers of machine learning algorithms, is to try and develop algorithms that somehow encode those regularities and exploit them for learning. Okay?
Even if they weren't equally likely across the entire universe, wouldn't this still be the case that it's not the end of the world? Because it's not likely that you're going to pick if you randomly select your data, assuming that you can randomly select it, it doesn't seem likely that you'd ever get all of data in your training set being F and all of your test data being F prime.
No, but
it seems really unlikely.
No.
I'm
glad you asked that question. Right? There's a fallacy in your question. Right? You're saying like all the data. Remember, you're saying like all the data in training is from F, and all the data in test is from F prime. Right? What's wrong with this argument? The training data is neither from F nor from F prime. It's from both. Remember, the training data is the same for both. If, let's say you are now, applying machine learning to a new problem that you've never seen before. If that problem really was generated at random from the set of all possible problems, you would have no reason to believe that whatever your learner is would be good, would be better than flipping a coin. Even if your learner was a big stacked complication of decision trees and neural networks and everything in the universe, there would still be no reason to believe that that would be better than flipping a coin. So the usefulness of machine learning hinges completely on the fact that this is not a uniform distribution.
Okay.
And sometimes there are problems where nothing works and then you just give up, and we tend to not hear about those, but they do exist, so who knows, right? There's an amount of selection bias in that, we keep applying machine learning algorithms to the problems that they're successful in, to certain broader classes of problems, right? Maybe there's a lot of stuff out there in the world that we just think is random, right? But it's not that it's random, it's that our brains and our algorithms don't know how to figure out where the order in that is, right? For all we know, that's what's going on. But at the end of the day, what matters is, for any given problem that you're going to apply machine learning to, there's a very good chance, based on past experience, that, the assumption of some or other of your classifiers will actually be a reasonable match for that problem. Okay? Nevertheless, it remains the case that you should not expect one learner to always be better. Right? Because remember, a learner is better if it's more correct, if it encodes correctly more truth about the domain. Right? The more your learner already knows about the domain in whatever form, the better off you are. Right? But the more it knows about one domain, the less it knows about a different domain, right? So there's no learner that's always going to be better for all domains, right? A learner might be better in a certain class of domains that share certain structure that learner captures, but then there's another class where another learner will do better, right? So you can't say a priori, like, people used to circa, 1990, backprop is always going to be better. I mean, people first found out empirically that wasn't the case, and then they started trying to figure out why. And that's when, it's not an accident of history that, the no free lunch theorems and things like bias variance came along at that point. Because first people were developing these algorithms pretty much in isolation, testing them on different things and believing in them. And then they started comparing them head to head. And then they found out that no algorithm always won. And then they tried to figure out why, and that's when things like, no free lunch and bias and variance came out. Okay? So the moral of the story for you, and this is a very important moral of the story, is do not have a hammer that you want to, hammer, everything with, irrespective of whether it's a nail or not. A good machine learner doesn't have one algorithm. It has a suite of algorithms and will apply them and the different variations of them. Right? You need to have a toolkit, not just one tool. Okay? Even today, there's still a lot of people who fall into this trap of, yes, they really like decision trees and that's what they use all the time. That's a dangerous thing to do. This is much less common than, in the early days of data mining, there were like single algorithm systems being put out, like, like Quinlan's system. These days, every company worth its salt, provides a suite of algorithms, right? But, it still behooves you to know how to use them and try them out and whatnot, okay? You have to go through this process of trying things, trying variations of the data, understanding the problem before you actually get something that's really good. Okay? So that's one moral of the story. But now let's, maybe there's something here that remains a little bit puzzling, which is the following. Or maybe not, right, with what you know already. So it's one thing to say, well, decision trees are never better than neural networks, or vice versa, right? Well, they're very different, right? But what about a one-layer perceptron, right? Think about neural networks, right, which we were talking about last time, right? What about a one-layer perceptron and a multi-layer perceptron, right? We are claiming here that it is not the case that the multi-layer perceptron is always better than the one neuron perceptron, right? How could that be the case? Anything that the one hyperplane perceptron can learn, right? The multi-layer perceptron can learn too, right? It could always, blow away the weights of all the other, neurons and just leave one, right? And there's for sure a lot of things that the multi-layer perceptron can learn that the one-layer perceptron cannot, right? So the question is, how do you square that with the fact that neither of them is always better, right? How come the multi-layer perceptron isn't always better than the single-layer one? Any ideas?
The complicated one might hallucinate more.
Might what?
Hallucinate more.
Yeah, absolutely, right? Overfitting. Right? I told you the answer is always going to be overfitting, and this is no exception, right? That's the thing, right? Again, this is something that people did not appreciate in the early days of machine learning. In the early days of machine learning, people were like, oh, we need to build ever more powerful learners. We need to go from, perceptron to multi-layer perceptron and from single rules to rule sets and whatnot, because the more powerful, the better, right? We want to be able to learn more things. What they didn't quite realize is that there's a downside to being more powerful, which is exactly, your word is the right one, is you're more prone to hallucination, right? You're very creative, you could be a genius or you could be a madman. So the problem, with a multi-layer perceptron over a one-layer perceptron is that it's more prone to overfitting. Yes, it can learn things that the one-layer perceptron can't, but it's also more liable to basically crash and flail and produce silly things when, the perceptron is very boring but also very stable, right? Things like perceptrons and naive Bayes, they're kind of boring, but on the other hand, they're safe, right? They're very predictable. They don't get, overexcited about patterns that they found here and there in space. It's like, I think there's a hyperplane here that separates my head. This is all I'm going to tell you. You might miss out on a lot of things. On the other hand, if you learn a decision tree and don't prune it properly, this thing could find all sorts of crap flying around. Okay? So what we would like to have is a way of understanding this trade-off. Right? This is the key. At the end of the day, when you're doing machine learning, you have to trade off the expressiveness of your learner, right? You want a very powerful representation on the one hand, but on the other hand, you don't want to, wind up hallucinating things. And this is a very big risk in machine learning and data mining, is hallucinating things. In fact, I don't know if you guys know this, but data mining first appeared in the 1960s as a pejorative term for hallucinating patterns. Statisticians used to call data mining what you should not do. If you were finding patterns where they weren't, and they say like, oh, you're just data mining, also known as torturing the data until it confesses. Right? You always have to be aware of doing that. And, these days, data mining is just, has gotten beyond that, but that danger is still there. So let's understand it. And this is where the notions of bias and variance come in. We've already seen that overfitting is always the answer to, what's wrong with a machine learning algorithm. Here's another, thing that's worth having in your set of ready answers, right? For these cocktail party moments, right? If somebody then wants you to dig deeper, right? Well, how do we explain what this algorithm is doing? The next, 3 words out of your mouth should be bias and variance. There's a famous machine learning researcher who says that bias and variance are the El Nino of machine learning. Because that on years where there's an El Nino, everything that happens with the weather, people say like, oh, it's El Nino, right? Oh, it's very wet this year, or very cold this winter. Oh, it must be El Nino, right? You can do the same thing with bias and variance. No matter what question somebody asks you, if you can't think of an answer, just say, oh, it's because of bias and variance. Then people go like, yeah, you could be right, yeah. So, the two notions worth knowing. And like on a more practical level, you might want to actually measure the bias and variance of your learner. In fact, we're going to ask you to do that in, the final assignment of this class. Because, the problem that you often have is your learner is not as accurate as you would like it to be. Why? Right? What should you do to make it better? And what bias and variance do is like, instead of just looking at the error, which is not a very informative thing, if you decompose the error into bias and variance, then you can see which one is dominating. And depending on which one is dominating, you want to do different things. If variance is dominating, your learner is probably too powerful. If bias is dominating, your learner is probably not powerful enough. Okay? So let's look at bias and variance. So we're going to look at how to decompose error into bias and variance, and then what to do with that. And then, with bias and variance, we can explain why simple learners can do better than powerful ones, right? Why a single-layer perceptron might be better than a multi-layer perceptron, or why naive Bayes might be better than a decision tree, which was very shocking to people, in things like text classification. It will also help us to explain why model ensembles are so useful. But when model ensembles started doing very well in the beginning, people were somewhat puzzled, and then they tried to come up with explanations. And one very good type of explanation is using bias and variance. It can help you to combat overfitting. So if you want to avoid overfitting with your learner, keeping bias and variance in mind is a very good thing to do. Now, bias and variance are two notions that were first invented by statisticians. And remember, statisticians mostly do regression for a living. So they were for regression problems, where people are mostly concerned with squared error. Remember, when we do linear regression, and we're trying to minimize the sum of the squares of the errors. Okay? Also known as the squared loss. Like statisticians often call your error measure the loss, right? It's very poetic, right? You suffer the great loss when your algorithm didn't work, right? Economists call it utility, right? So economists are optimists and statisticians are pessimists. We, however, are mainly interested in classification where the loss is what's called 0-1 loss, right? It's called 0-1 loss because accuracy and error rate, right? What happens is you either get the example right, in which case your loss is 0, or you get it wrong, in which case it's 1. Okay? So what we're going to do here is, first we're going to look at the standard, squared loss for, regression problems, and then we're going to see how to extend that to the classification case. Okay? And in your assignment, you're going to apply it in the classification case. Okay? Any questions so far? Okay, but before we get into the math, as usual, let's start with the intuition. Okay? And as usual, we're gonna use a sports example. We've already looked at tennis a lot, but now let's look at throwing darts, right? It's not Saturday morning and you're not playing tennis. It's Friday night and you're at the pub and you're throwing darts with your friends. Okay? And so here's what I'm going to do. I'm going to put the bias on the y-axis, low and high, and I'm going to put variance on the x-axis. Can everybody see variance? And here's low and here's high. Okay. And now here are my dartboards. Okay. So I'm going to draw 4 dartboards here. And forgive my poor drawing skills. You notice there's a certain variance in my drawings of the dartboard? But, okay. So, let's say that you're a champion dart thrower, right? This means you're going to be very accurate, right? So where are your darts going to land? In the bullseye, right? So this is the low bias, low variance situation, is where your darts all land around here. Okay? Now, what do you think is the high bias, low variance scenario? Where are your darts going to land in that case?
They all land together, but not in the center.
Precisely. They're all still going to be clustered together, right? Low variance. You don't vary a lot from one dart throw to the other, but they're all off, right? It's, I don't know, let's suppose that this was, archery instead of dart throwing, right? And there was a strong wind, right? So all your arrows wind up being, over here on the right, right? So this is high bias, low variance. Okay? Now what's high variance, low bias, right? You're very drunk, right? The end of the night is approaching and you're just kind of throwing the darts over there and they land, all over the map, right? So what's the high variance scenario? Yeah, I just said half of it, right? They are all over the map, but...
The average is in the center.
Exactly. On average, they're all over the map, right? But if you do the average of all of them, the average is the bullseye. Right? So yes, you make lots of mistakes, but they're random mistakes. Right? On average, you know the joke about the statisticians, right, who went duck hunting? And one shot was above the duck and one was below, and the statistician said, like, hooray, we got the duck. Right? That's the low bias, high variance scenario. Okay? All right, so finally, what is the high bias, high variance scenario? The worst possible one. Right? The roof of the pub has been blown off, there's a strong wind, and you're drunk, and nothing is going right. So what happens in this case? Well, it's high bias, right? So you know that on average, your darts are going where? Not in the bullseye, right? They're off center, right? On the other hand, it's high variance, so they're very dispersed, right? So they're all over the map, right? They're all over the map, but with a tendency to say the left. Okay. So this is the highly technical definition of bias and variance. Okay. So obviously, we want to be in this scenario, right? But the whole problem here is that, like, we don't know where the bullseye is, right? We're trying to figure out where the bullseye is. It's very dark, and we're trying to infer where the bullseye is. We only get a little bit of light when a dart lands somewhere, right? So we don't know what situation we're in. Maybe I can measure the variance, right? The bias is actually trickier, right? But what I would like to know is, am I in this case? Am I in this case? Am I in this case? Right? Because depending on which case I'm in, I have to do different things, right? In this case, what I need to do is I need to steady myself, right? I can still point in the same direction that I've been pointing all along, right? Because it's the right direction, but I have to be steady. I have to not diverge from that direction, right? Here, right, and people who do like, rifle shooting and what know this, what happens is like, you need to correct whatever, problem with your rifle there is that's not quite, or the wind or whatever, that's not quite making things go in the right direction, right? It's not that the bullets are varying a lot, it's that, they not quite, you need to compensate, right? In these Hollywood movies, right, when, somebody sells a gun to the assassin, right? The assassin goes out in the country and, shoots at a tree and goes like, oh, I'm 1 foot below where I should be, right? And then when they go to do their real hit job, they aim 1 foot above, where the, the target is, right? That's bias correction for you, right? Of course, the Hollywood screenwriters don't know this technical, background, but that's what's going on, right? They're doing bias correction. Okay. All right. So, any questions? Everybody got this intuition? Okay. So let's look at a slightly more, not yet the math, but a more technical example of this. Oh, but actually, let me actually do the definitions first. Okay, we've already kind of more or less talked about some of these things, but let's do those before we do the example. So I have a training set. They're pairs of examples x, where x is a vector of attributes and target values t. Right. So I'm going to use t for the actual values in the training set. So they're my targets. The learner is going to induce a model f that applied to x produces a predicted value y. Okay. So t is the real value and y is the predicted value. And the loss is a measure of the difference between those two. Okay? And your goal is to learn something that has as small a loss as possible. Okay? And now there's many different versions of loss. There's squared loss, and I'm generally going to use the letter capital L to represent a loss. Squared loss, so this is for a particular example. Right? Squared loss is just t minus y squared. Okay? The difference between the actual value and the predicted value is squared. Absolute loss, which is also sometimes used and is actually in many ways more robust than squared loss, is just the absolute value of t minus y. Okay? These both make sense when t and y are continuous values. Okay? For classification, you can have 0, 1 loss, which is 0 if y is equal to t, right? And 1 otherwise. Okay? There's also more interesting things that you can do for classification, like, for example, having different costs for different decisions. Remember when we talked about how diagnosing that you don't have cancer when you do is a much more dangerous thing than saying that you do when you don't, right? These things have different costs. So in general, I could actually have a cost matrix with one cost for predicting 1 when it's 0, and another one cost for predicting 0 when it's 1. Or if I had n classes, right, I could have an n squared, an n by n matrix of costs, okay, and so on. For probability distributions, people often use this thing called the relative entropy, also known as Kalbeck-Leibel divergence, and so on. You can define your own cost function for your application if you want. Okay? So let's just suppose that we have a loss function. Right? The basic thing that we're going to look at here is that I can express my loss as an additive function of something called the bias and something called the variance, and one thing that I haven't mentioned yet, which is noise. I didn't mention noise today, but I've mentioned it before, right? Apropos of the Bayes rate, right? The noise is the unavoidable inaccuracy. Even if you had seen all the examples and were making the best possible prediction, if out of all patients with these exact symptoms, only 80% of them have pneumonia, I will predict pneumonia, but I will inevitably be wrong 20% of the time, right? So the noise you can't do anything about. In fact, if your problem is high noise, you know what you need to do? You need to gather more attributes for each example, right? Because you need maybe other tests to be able to further discriminate among those people, okay? So if your problem is that you have very high noise, you need more data, not more examples, but more attributes for each example, okay? In this lecture, we're going to ignore noise just to keep life simple. There's a paper which we point you to in the assignment that actually has the full treatment with noise, okay? And there are some tricky issues in terms of distinguishing bias and noise and whatnot, but we're going to ignore those here and just focus on bias and variance, right? The difference between noise on the one hand and bias and variance on the other is that the noise is the unavoidable error. Bias and variance are the avoidable error. Given your training set, you could in principle reduce your bias and variance to 0, so it behooves you to try and make them as small as possible. And then what's left is the noise. Okay? So we're not going to do anything about the unavoidable error, which is the noise, but we're going to try to do something about the avoidable error, which is the bias and variance. Okay? Any questions? All right, so let's look at our slightly more technical example. First of all, let's see an example of bias. And we're going to do this in the in the regression setting because it's the one where it first naturally comes about. Okay? So let's suppose, here's my input variable x and my output variable y, right? And I'm trying to learn something of the form y equals ax plus b, right? My problem is what are a and b, okay? But, and this is what happens in the real world, your real function is not a straight line. You'd be astonished at how often people try to model nonlinear phenomena with linear regression. It's just amazing how often they do that. It's easier, right? But hopefully one of the things that you'll get out of this is not to just stick with that Stats 101 toolkit of linear regression and basically refuse to see anything that's not linear, which some people out there actually do. Less so these days, but okay. So your actual function is this solid line here. It's a parabola. Okay. Now the thing, I just bad-mouthed linear regression, but linear regression may not get you the right function, but usually it still gets you something, right? If there's a linear component to your function, linear regression will get it. Okay. So let's say that, again, I'm in the same setting as before. I have a training set. These are the x's here. They're xy pairs, right? And these xy pairs are obtained by adding Gaussian noise to my true function. Okay? Remember, this is the setting in which we're going to want to minimize the sum of squares, right? We saw that before. Okay? So I'm given such a random training set. It's a random sample from the real phenomenon, right? And now I'm going to learn my linear regression, and I learn one of these dotted lines. Okay? Let's say that this dotted line here is my line of least squares for that training set that I just showed. Okay? Now, if you give me a different training set, right, a different random sample from the same phenomenon, right, those will be different points, right? I'm just going to represent those with dots now. And then from those, you will learn a slightly different line. Right? So as my training set varies randomly, the model that you output also varies randomly. Everything in this whole idea of bias and variance is about random variations in the training set and the variations that causes in the learned model that you output. Okay? So, with different training sets, my line swings back and forth. But now let's suppose that I did this, with a lot of training sets, many, many different random samples of the real phenomenon. And then I average all those lines, right? I would get this line that I put here, the dashed line, as opposed to the dotted lines. Okay? So this dashed line is my average prediction. Average over what? Average over training sets. All of which are randomly sampled from the real phenomenon. Okay? And now what is the bias? Right? The bias is how much this line is off from this line. Okay? In particular, there are two lucky points here where the bias is 0. Right? At this point here, x2, and this point here, x1, there is no bias. You got lucky and you actually nailed the function in those 2 points. Of course, in most other places, the picture is going to be different. Like, for example, at this point here, right, there is this difference between the real curve and the curve that you predicted. That is your bias. Right? So bias is your difference between reality and your average prediction, squared. Okay? Because we're concerned with squared error, at least in the treatment that we're going to do here. Okay? Everybody got this? We're going to see the math shortly, but the math is actually going to be quite straightforward. So the important thing is to understand the concept. Okay. In this case, the variance will be very low, right? Linear regression, again, is kind of boring, but is also kind of solid, right? It doesn't oscillate a lot. Okay. To illustrate variance, let's look at a different case where you're like, linear regression is really too limited. Let's really use the latest, most powerful, highly nonlinear regression algorithm, right? I'm going to fit a polynomial of arbitrary degree to my data, right? We can do that these days, right? We got the algorithms for that, and we even know how to do these things fast and so on. Okay. So here's my same true curve as before, right? And now what I have here is 3 different training sets. One of them, I don't know if you can see this exactly, it doesn't matter that much, but one of them, the points from that training set I represented using an S. The other training set, they're X's, and the other training set, they're little O's, okay? So notice that all these points are basically lying around the true curve, plus some noise, okay? But of course, the noise is going to be different for the different examples, okay? And now, I have my crackerjack super powerful machine learning system, right? And it can fit those points absolutely perfectly, right? So for example, if you follow the trail of my axis here, right, you will see that I have just learned a polynomial that what does it do? It beautifully passes through every single one of those x's. Isn't this great? Wouldn't you deserve 100% if you did this on one of your assignments? What could be better than learning things perfectly? Okay? Now, you also learn the S's perfectly and you also learn the O's perfectly, but it gets better than that. You know what happens if you do this a lot of times and then you average all those curves? What is the average curve going to be?
The actual line.
It's going to be the true one, right? So it's easy to scoff at these wild swings and go like, oh, what a bunch of crap, right? You should have known better. If you do that a bunch of times on average, right, the result is actually the truth. Which means that the bias for your very powerful learner, for your polynomial of arbitrary degree is what? What is the bias here? It's always 0, right? Go to any point, right? Remember, the bias is the difference between the average curve and the true one, right? And we just saw that, and remember in this case here, right, in some places they were quite distant, right? But in this case, your average curve and your true curve are right on top of each other, so you have no bias. Does this mean that you can declare victory? Alas, no. And this is where the variance comes in, right? Given one training set, you still produce the curve that looks nothing like the real one. It kind of oscillates above and below the real curve, but it ain't the real curve, right? So what's killing you in this case is variance. Can anybody guess what variance is from just our description so far? So bias was the difference between the truth and the average prediction. What is variance?
Deviation from mean.
Kind of, yeah. So it's the difference between what and what?
The actual value and what we predicted. The difference.
Not the actual value, right? The variance has this interesting. Actually, let's go back to this example here. Sorry. Here's a very interesting thing to notice, right? The bias very much depends on the relationship between your predictions and where the truth is, right? The truth here being the bullseye, right? If you're off from the bullseye, you have high bias. But look at variance, right? So here we have the high variance case, right? And here we have the low variance case, right? High versus low variance actually has nothing to do with where the truth is. It's just a measure of how much the classifier or the regression flails, irrespective of where the truth is, right? Notice in this case, right, the truth is off to the side. In this case, it isn't, right? But the variance is the same in both, right? So the variance just has to do with how dispersed your predictions are, irrespective of where they are relative to the truth. Of course, where they are relative to the truth is very important, but that is measured by bias. Okay? So, going back to our example here. What is variance? So bias was the difference between the average prediction and the truth. And variance is the difference between what and what?
Average prediction minus prediction.
Exactly. The variance is the difference between your average prediction, meaning your average over all training sets, and your particular prediction from one training set. If all your training sets lead to the same prediction, you have no variance. The clock that is always stopped at 12 has no variance. It has high bias, except when it's actually 12, right? At that particular moment, it has no bias and no variance. Okay, so the variance is a measure of how much you vary, hence the name, around the average prediction. So in this case, so remember, like in this case here, the average prediction is here. It happens to be also where the truth is, right? Because in this case, there's no bias, and the variance is the difference between those two. It's this distance here. Okay. In reality, it's the average distance, right? So the variance is not defined for one particular set, for one particular training set, but as an average over all of them. Okay. Did everybody get the intuition? Okay. So it's 8:08. Let's break until 8:18, and then we will see the actual technical part of this. Okay.
Really familiar with now.
Okay. Let's derive the famous bias variance decomposition for squared loss. Just a couple of easy steps. So here's my squared loss for one example. It's t minus y squared. Okay? T is the target value, y is the predicted value. Okay? And I'm going to represent with a bar the average y, the mean y. Right? So let me just add and subtract to this y bar. Okay? So all I did from the left to the right of this equality was subtract y average and add y average. Okay? So this is still the same thing as before. Okay? And now I'm just going to expand the square, right? Thinking of t minus y bar as a and y bar minus y as b. Okay? So, a plus b squared, right? Here's a squared plus b squared plus 2ab, right? So here it is, right? A squared plus b squared plus 2ab. Okay? Just simple algebra so far. Okay? And now let's just take the expected value of both sides. Remember, these are expectations over random training sets, right? Averaging over all different training sets that you could generate at random. Okay? So now I have on this side the expectation of t minus y squared, right? Which is the expected loss, right? The expected loss is your average loss. Okay? So with any one given training set, you might have a certain value of the loss. This is the average that you would have over a lot of different training sets. Okay? So on the right-hand side, I'm going to have the expectation of t minus y bar squared, right? But I can take out the e. Why is that? And just get t minus y bar squared. Why is that?
They all know.
These two things are both constants, right? T is certainly a constant, right? It's the target value. And y is also a constant independent of the training set because it's the average over all training sets. Okay? So both of these things are constant. Therefore, the expectation of their square difference is just the square difference itself. Okay, everybody agree? Okay, so this is my bias. Right? So this is the definition of bias for squared loss. It's just the target minus the average prediction squared. Or you can think of it as the loss between the target prediction and the average prediction, okay? Should be fairly intuitive given what we've seen before, okay? And then, of course, you have your expectation of this term here, right? That expectation has to stay right because the y varies with the training set, and this is the variance, okay? So the variance is just the expected value of the difference between my average y and my y for a particular data set. Okay? Any questions so far? Right? And finally, this whole part goes away. Why does it go away? Right? What happens when I take the expectation of this? Here's a little, piece of Stats 101 that is useful here. Remember the whole linearity of expectation, right? The expectation of a sum is the sum of the expectations, and the expectation of a constant times a random variable is the constant times the expectation of the random variable, right? So let's look at this and see what's constant and what's changing, right? So 2 is certainly a constant, right? So I could put the e inside it. You agree? Right? By linearity of expectation. T and y bar are also constants, right? We saw that before, right? So I can keep moving the expectation past it, right? So finally what I have is a constant times the expectation of y bar minus y. You agree? Okay, but now again by linearity of expectation, this is the expectation of y bar, right? And what's the expectation of y bar?
Y bar.
Just y bar, right? And what is the expectation of y?
Y bar.
Aha, y bar. And y bar minus y bar is?
0.
Yeah, this one was hard, right? Could have been a trick question. Right? So that part goes away. And there you have it, right? So this is the famous bias variance decomposition of squared loss. My expected loss is the sum of bias and variance. Right, very nice. We just have these two components that add up. So when you have a certain amount of loss, it could be due to some combination of bias and variance. There might be no bias on all variance, or no variance on all bias, or some amount of each. Okay. So one thing that you might want to do when you're doing regression in practice is measure bias and variance, not just error. Because underneath the error, there could be very different things happening, as we just saw. And if instead of measuring error, you measure bias and variance, you actually have a powerful hint about what's really going on. Okay? Questions about this? All right, so the next step is to apply this to other loss functions. Okay? So now let's look at how we did this for squared loss, which was the first one, and try to figure out how we might do it for other losses, in particular for things like absolute loss and 0-1 loss and whatnot. Right? So here's my expression, right? Notice that this is all in terms of squared differences, because it's for squared loss, right? I would like to do this for arbitrary loss functions. Okay? So let's try to map these quantities that we have here to things that are for any loss function, not just for squared loss. Okay? So obviously, things of the form a minus b squared should become the loss between a and b, right? Where, for example, tomorrow the loss between a and b might just be the absolute value of a minus b, or anything else. Okay? So wherever we have a minus b squared, we probably want to have something like loss between a and b. Okay? You see the strategy that we're following here? Okay, so let's keep going, right? So this was my, loss, right? So now, what is my expected loss, right? My expected loss is just the expectation of this value, right? Which means that now I want my expectation of the loss between t and y, right? So my expected loss is the expectation of my loss between the target value and the y. Right, whatever particular form that loss might take, squared, absolute, 0-1. Okay. Okay. So So this is my expected loss, right? Remember, this is one of the things that we're interested in. Here's the expected loss, right? And now let's see what's the generalization of bias and the generalization of variance. Okay. So t minus y bar squared, right, is really what? It's just the loss between t and y bar. You agree? If at any point you disagree, just yell. Okay. So this is my bias generalized. Okay? The expectation of y bar minus y squared, right, is the expectation of the loss between y bar and y. Right? So this is my generalization of the variance. Okay? So it looks like we're making very good progress, right? Now we have a more general, definition for expectation, for expected loss, a more general definition for bias, and more general definition for variance, but there's still something missing here, which is, what is this y bar exactly? Remember, in squared loss, y bar was the mean, right? You add them all up, you divide by the number, right? But is this still going to be the same for absolute loss? For 0-1 loss? For 0-1 loss, it's immediately clear that it probably isn't, right? And for absolute loss, probably also not, right? So what is this y bar exactly, right? We also need to generalize y bar, right? So here's one way to generalize y bar, right? Let's define this thing and call it the main prediction. The main prediction is the prediction with minimum average loss relative to all the predictions, right? What is, think of the mean, right? What is the mean? The mean is actually the value that has minimum squared loss to all of the other points, right? Right? If I give you a bunch of points and I ask you, give me another point that has a minimum value of the sum of square differences between that point and all the others, that will be the mean, right? This is one of those, stats 101 things, okay? So this is what we want in general, is we want the prediction with the minimum average loss to all the predictions from all the different training sets. In the case of squared loss, this is just going to be our good old friend, the mean. What is it going to be in the case of absolute loss? Again, this might come back from your very rusty stats 101 or, where else you might have heard of this, right? It's actually the median. Now, does everyone know what the median is? Right? So for squared loss, it's the mean. For absolute loss, it's the median. What about for 0-1 loss? Right? Remember, for 0-1 loss, there's only two predictions, 0 and 1. Right? So what is the prediction with minimum loss to all the predictions that you made?
most.
Right, suppose that I had 1 million training sets and 600,000 of them the value was 1 and 400,000 the value was 0, right? What would be the prediction with minimum loss, minimum 0-1 loss? The most common one, right? It's very simple. So, the technical term for the most common is the mode. Okay? So this notion of main prediction applies whatever your loss function is, right? If you have a loss function, you can define the corresponding main prediction. Okay? And in these three cases, it's these three very well-known things, right? The three main measures of concentration of location is the mean, median, and mode. Okay? And now we actually have a complete definition. Now we can go back to these things, and now we know what they mean, right? For example, my bias, right, for 0-1 loss, right, is the loss between the actual value, which is either 0 or 1, and the most frequent prediction of all your classifiers learned from random training sets, which is either 0 or 1. Therefore, your bias is also going to be either 0 or 1, right? Your bias is going to be 0 if what?
All of them are same class.
Yes, but that's a little bit extreme, right? What you're saying is true, but there's a more general statement, right? So think of all my classifiers that I learned from all different random training sets, right? When is my bias going to be 0?
They all have same.
Yes, that's what you just said, right? If they all predict this, actually, it's not. Actually, let me give a counterexample to that, right? Let's suppose that the true value is 1, right? And my classifiers all predict 0, right? What is the bias there? It's 1, right? It's a difference, right? What is the most common prediction, right? The main prediction, right? In this case, is just the most common one, right? So if they all predict 0, the most common prediction is 0, right? But if the truth was 1, right, then the bias is the loss between those two, right? What is the 0-1 loss if you predict 0 and the truth is 1? By definition, it's 1, okay? But if this is actually what I thought you were saying, probably is what you were saying, right? If they all said 1, right, and the truth was 1, right, then the bias is 0, right? Because the mode is 1, right, and when you predict 1 and the truth is 1, the loss is 0, right? But more generally, right, your bias will be 0 when what? Let's suppose that of those 1 million training sets, 600,000 said 1 and 400,000 said 0, and the truth was 1. What would the bias be in this case?
0.
0, because?
The common outcome was 1.
Right, the most common prediction is 1, right, because 60% of them predict 1, right? And since the most common is 1 and the truth is 1, the bias is 0. Okay? Everybody got this? Okay, very good. And same thing with variance and so on. Okay? So far so good, right? But now, let's see where we are so far. Now we've managed to generalize our definitions of bias and variance to any loss function. Very good. Using this notion of main prediction, right? But we still don't have a bias variance decomposition, right? You can define bias and variance any way that you want, but the point is to, at the end of the day, have a decomposition of the error into bias and variance, okay? And this is actually a lot trickier, right? So let's see now if we can get, let's see if we can decompose 0-1 loss into bias and variance as defined in this way. So before we do that, notice the following, right? So in general, what is bias, right? Bias is the loss incurred by the main prediction. Okay? You agree? Right? We just saw this for the case of 0-1 loss, it's also true for absolute loss and so on and so forth. What is variance? Right? Variance is the average loss incurred by the prediction from a particular training set relative to the main prediction. Okay? Remember the squared loss case, right? This is just a generalization of that. Okay? And these definitions have all the properties that you would like, bias and variance to have. Like, for example, the variance is independent of the truth. Right, it's a little counterintuitive, but remember, we're trying to separate, just flailing around from missing the truth, and variance captures the flailing around part. So the variance, defined in this way, obviously is independent of the truth, right? It's just a function of your predictions, right? T does not enter into the definition of variance, right? And the variance is 0 for a classifier or for a learner that always makes the same prediction, right? Irrespective of what the loss function is, if you always have the same prediction, the variance is 0. Okay? Likewise, the bias, right, is really independent of how much you flail around, right? The bias is just a function of where you are on average relative to the truth. Okay? So there's all these sort of like properties that you would like bias and variance to have, and these generalizations have that. Okay? So in particular, for 0-1 loss, the bias is 0 if the main prediction is correct and 1 otherwise. Okay? We just saw an example of that, right? What about the variance? Right? What is the variance for the 0-1 loss case? Right? Now this is a little less obvious, right? What does it mean to have high variance? Right? So let me give you 2 examples, right? Let's suppose again that the truth is 1. Right? This example's, true class is 1. It's positive, it's true. Right? And now in one case, 60% of my training sets say 1. Right? Training sets meaning I learn a classifier, and then for this example I predict 1. So in one case I predict 60% of the time 1, 40% 0. And so the bias is
1.
If it's not 1, it must be. Hey, this is 0-1 loss, right? So I predicted the truth was 1, right? This was a trick question. Right? So I predicted 1. The truth is 1, and I predict 1 60% of the time, right? So the bias is 0, right? And let's suppose that I have another one where I get 1 80% of the time, right? So what is the bias in this case? The truth is 1, and I predict 1 80% of the time. Yeah, you know why this is a trick question? Because you're hearing 1, 1, 1, 1, right? And I asked, what is the bias? So, the natural answer is 1, right? So I could have done it the other way. But anyway, right? So in both of these cases, the bias is 0, right? So 60% of the training sets lead to a prediction of 1, or the correct prediction, if you will. And in the other one, it's 80%. Okay? But now the question is, which one do you think has the greater variance? The 60% or the 80%? Actually, let's do an extreme case, right? Let's suppose that we had the case that you had of it always predicts 1. What's the variance in that case? 0, right? So which one has the higher variance? 100% 1 or 80% 1? 80%, right? So which one do you think has the higher variance? 80% or 60%? And what is the highest variance that you could possibly have? Yeah, 49.9999, or actually 50, right? If really came out 50-50, right? You should use an odd number of training sets for this to make sure that doesn't happen. Right, so what is the variance? The variance, right, is the probability that your prediction differs from the main prediction. I mean, you can do the math for this, it's very simple, right? But it should be intuitive, right? If your prediction always agrees with the main prediction, as in the, always 1, then the variance is low, right? If your prediction is like, 1 50% of the time and 0 50% of the time, then your variance is very high, okay? So for 0-1 loss, the variance is just the probability that y is different from y bar, okay? You have a question?
So, yeah, when we're talking about bias and variance here, are we talking about for one individual
Yes.
item or?
Yeah, remember, so what we're talking about here is always for one particular point.
Okay.
But it applies at every data point, right? So if you go back to our, regression example, right? I'm always looking at, like, there's a bias at this point,
Right.
which is different from the bias at this point. Okay? The bias here happens to be large, and the bias here happens to be 0. Most of the time, when you measure these things in practice, as you will in the assignment, what you're going to measure is the average bias over all the examples, because you don't want to be zooming in on one region or another. In some cases, that might be useful, right? You might have a lot of bias somewhere in the space, but not elsewhere. But usually, people just measure the average bias over all data points. But for everything that we're doing here, we're always looking at one specific data point, and what we're averaging over is training sets. So my training set varies, as a result of which my classifier varies, as a result of which my prediction on this point varies, but it's always just on one point. Okay? All right. So, we have our definitions of bias and variance, but can we decompose 0-1 loss into them? Let's try to do that and see what happens. Something very interesting is going to happen. So to simplify, let's suppose we just have a 2-class problem, right? 2-class problem, now let's look at 2 cases. Bias is 0 and bias is 1, right? After all, that's all it can be, okay? It's easy to show that if bias is 0, then the loss is indeed equal to bias plus variance. Okay, so the usual decomposition applies. Okay? Why is that? Well, what is the loss? The loss is the probability that y, the loss for a particular point, right, and a particular classifier, right, is the probability that the y predicted for that point differs from the true t for that point. Okay, so this is my loss, right? My variance, right, is the probability that y differs from y bar, right? And now if you think about it, since bias is 0, right, what does bias being 0 mean? It means that y bar is equal to t, right? And that's what bias being 0 means, right? It means that your main prediction is equal to the truth, right? Well, then if you think about it, if y bar is equal to t, right, then I can replace y bar by t here. You agree? At which point these two things are the same. They're both equal to the probability that y is different from t. You agree? Therefore, the loss is equal to the variance. But the bias was 0, right? So the loss is equal to the bias plus the variance. Okay? Everybody agree with this? Very good. So far so good, right? So when the bias is 0, the loss is equal to the bias plus the variance. Okay? But now comes the shocker. The shocker is that when bias is 1, the loss is equal to the bias minus the variance. This is a little disturbing. So, but first of all, let's convince ourselves that it's true, and then let's try to understand what it means. And in fact, it actually means something important, as we will see shortly. Clearly, this is a big difference between classification and regression, right? And this big difference is going to have consequences. So, but first of all, let's see whether this is true or not. So, remember the loss, right, is the probability that y is different from t, right? The probability that the prediction is different from the truth, which is 1 minus the probability that y is equal to t, right? Again, if at any point you disagree with something, just stop me, right? Well, remember, we're in a two-class problem, right? So if y bar is different from t, which is what happens when bias is 1, right? When bias is 1, y bar is different from t. Therefore, y equal to t is the same as y being different from y bar. You agree? Okay, therefore, 1 minus p of y being t is 1 minus p of y not being y bar. You agree? Right? P not being y bar, I just showed, is the same as p of y being equal to t because bias is 1. Okay? And notice 1 is the bias, right? That's our premise. And p of y, not being equal to y bar, by definition, as we just, developed, is the variance, right? Therefore, I have that my loss is equal to the bias minus the variance. So, shocking conclusion, increasing the variance can reduce loss. Right? We used to think that, bias and variance were bad, right? You want them to be always as low as you can. There's a machine learning researcher who, upon looking at this, famous guy, Tom Dietrich, they said this is a lot like good and bad cholesterol, right? Cholesterol, there's, LDL and LHL, right? LDL is actually good cholesterol. It turns out that in classification, unlike in regression, there's actually good and bad variance. Okay? So, but why would variance ever be good in classification? Can anybody guess at why? This seems unintuitive at first, but actually in retrospect the reason is very simple. Right? Let's look at this, right? So let's say that so first of all, when bias is 0, definitely you want variance to be low, right? Because your error is your variance, right? But why might I want to have high variance when my bias is 1?
Gives you some probability that you might guess the right answer.
Right, let's look back at our example, right? When the variance could have been, remember, I was making the right prediction 60, 80, or 100% of the time, right? But now let's look at the opposite case. Let's suppose that I was making the wrong prediction 60, 80, or 100% of the time, right? 100% of the time, my variance is 0, right? Meaning that I always make the wrong prediction. 80% of the time, right? Actually now, my variance is actually the cases that I get right, right? Bias means that I get it wrong, but now the more that I increase the variance, the more cases I get right. Right? Because the variance is just the cases where you differ from the main prediction. So if the main prediction is wrong, the more often you differ from it, the better, meaning you want more variance. Right? When the bias is 1, every little bit that you add to the variance becomes a bit that you subtract from the error until when? until you get to 50%, right? Because at that point it flips. And now your bias is 0, which is good, but now your variance starts to be bad. Okay? Did everybody get this? And intuitive, but at first, but then if you think about it, it makes a lot of sense. And this actually has a very important practical consequence, which is the following. Classifiers, right, as you might have noticed already, and you're going to study it some more in your assignment, like, say, decision trees, have this tendency to be very unstable, right? They're all over the map, right? A decision tree learner, right, is a canonical example of this. You change the training set a little bit, and you get a totally different decision tree. Maybe the first few nodes will be the same, but closer to the leaves, it's a whole different world, right? And the mystery of this, at least if you come at it, with statistical eyes, is like, how can these classifiers vary so much and still be accurate, right? By the notion that variance is bad for accuracy, this should be terrible. This is the reason. Is that in classification, the variance is not always bad. In regression, variance is always bad. In classification, variance can actually be good, which is why classifiers can be very unstable and still accurate. Which is why maybe historically people in machine learning have always had this greater appetite for very powerful and stable learners. In regression, right, people are much more conservative and tend to stick with linear regression, let's say, because other things are dangerous. In classification, you can actually afford to be crazier because your craziness might actually pay off. It also goes well with us computer scientists and this cowboy attitude that we have, right? You go in there and shoot up the corral, and right, we have a reputation for that, but and it's true, but sometimes it pays off, right? Relative to more conservative types like statisticians. Okay, yeah.
I guess it may also help because in regression, most probably variance is going to make you choose a wrong value, but here you have 50% chance of going into the right bucket.
Yeah, I mean the thing is that regression, right, is for a continuous problem where every little bit that every time that your prediction changes a little bit, right, then your error also changes a little bit. And here we're in a discrete world; it's 0 or 1. So once your bias is 1, you actually can't get any worse, right? Think about it. How could bias, if you think about it, there's no way that bias and variance could always add up, right? Because if your bias is 1, you can't get worse than that. You're already doing as much as you can. So the only thing that variance can do in that case is reduce the error. Okay? Questions? All right, so this was for 0-1 loss. Now, is there a more general statement that we can make? Well, there is no complete general statement that we can make because, as we just saw, the simple decomposition of loss is equal to bias plus variance does not always hold, right? And in fact, what exactly happens is going to depend on the particular loss function. However, there is a somewhat more general statement that we can make that applies to a lot of loss functions, which is the following. The loss is equal to the bias plus a constant c times the variance. And when the bias is 0, c is always 1. Okay? So for a certain class of loss function, which includes the ones that we've been looking at, when the bias is 0, the loss is equal to just the variance. Okay? Not a big deal, but that preserves that additive decomposition. The interesting case, of course, is when the bias is not 0, then what is c? Okay, well, for squared loss, we know that c is equal to 1, right? It stays, the loss is still bias plus variance. We just saw that for two-class problems, c is equal to -1, right? But we actually didn't see what happens for multi-class problems, right? What if I had, a whole bunch of different classes, right? Then just because two classes are different, just because A is different from, B, it could still not be equal to C, right? Well, in that case, C is minus the probability that Y is equal to T given that it's not equal to Y bar. Okay? Again, the math for this is straightforward, right? But you have to multiply by that factor. So in some senses, it actually reduces the effect of the variance by that probability. Okay? For variable costs, right, which is actually an important case, right? Let's suppose you have an arbitrary cost matrix. Then this C is actually minus the ratio of two losses. The loss between T and Y bar and the loss between Y bar and T. If they're the same, this gets us back to being 1, but in general they might not be the same. Okay? And so on. Any questions about this? Okay, so, last thing. Even more generally, right? Can you say something about not just particular loss functions, but about a very general class, let's say, all loss functions that are metrics, right? Metric means they obey the triangle inequality and so on. Okay? Yes, we can. So in particular, if a loss function is a metric, you can show that the loss will never be more than the bias plus the variance. So this is good. You measure the bias and invariance, and that puts an absolute cap on your loss. Okay. It also puts a minimum on the loss, and the minimum is the maximum of these two things: the bias minus the variance, and the variance minus the bias. Okay. So a graphical way to look at this is that here's on the x-axis my loss, right? My bias puts me somewhere on that line, and then what I have is the variance, is kind of error bars around that. My loss could be at most the bias plus the variance, or at least it's going to be the bias minus the variance, right? So the quick thing to say is that your loss is going to be the bias plus or minus the variance. Okay? So there's this region that your loss could be in. So this doesn't, this is not an equality, but it actually still is pretty informative. Okay? All right, so that was bias and variance for you. Questions?
Do we compute bias and variance on the training examples only? Or?
Very good. So so this is all very nice, right? But now there's some logistical problems, right? We're going to ask you to, estimate bias and variance, in your assignment, right? How do you actually do that, right? I don't have the ability to generate infinite random training sets, right? So how might we do it? Give me a suggestion.
Cross-validation type of,
Yes, but here's a big problem, right? Is that when I do cross-validation, I reduce the size of my training set. And variance and bias change with the size of the training set, right? In particular, right, the variance very much depends on the size of the training set. Okay? So what might I do instead? Here's a hint. It's something that we saw when we talked about model ensembles.
sampling with replacement.
Sampling with replacement, right? Generate bootstrap replicates of your training set. Right? What we used in bagging. Remember when I said that bagging came from statistics and people use this to estimate, means and variances, in an unbiased way, right? You generate a training set of the same size as your real one, right? Except that it's a random variation of it because some things got duplicated, some things. In fact, this introduces a small amount of bias, but hey, it's all we can do, right? So one way to do this in practice is to generate, bootstrap replicates of your training set and take those as being your surrogates of generating new, training sets from your real process. Which for things like estimating bias and variance is a pretty good approximation. Okay? Good question. More questions? All right, so how do you like the theory part of this class so far? Not too bad, huh? People sometimes start their machine learning class with a theory, which I think is a big mistake, because then it's like, why are you telling me all these things? I don't care about them. Hopefully at this point we actually have met enough of the algorithms and the problems that we can see where these things might be useful. Okay? So, but now let's get to more theoretical theory. Right? Bias and variance, is still sort of like a pretty practical kind of theory. Right? But now let's get even more theoretical. But there's a reason why we're going to do this. Is like we're going to see something amazing. Right? So, and this is the notion of packed learning, right? And it must be amazing because it won Leslie Valiant the Turing Award, right? They don't give out Turing Awards for just anything, right? So packed learning is actually an attempt to answer these fundamental machine learning questions that always come back to haunt us when we're doing machine learning in practice. Like, for example, overfitting. Why does overfitting happen? Overfitting happens because what I care about is the generalization error, but what I can see is the training set error. If those two things were the same, machine learning would be easy, or at least no harder than many other combinatorial optimization problems, let's say. Okay? So the question for us is, can we infer something about the generalization error just from looking at the training error? Packed learning is a way to answer this question. Right? You can see how powerful this might be, right? What I want to do is just by looking at the training error, being able to say something about how well my learner is going to generalize. Right? Clearly, good answers to this will have a big practical impact in the design of classifiers and whatnot. And indeed, as I mentioned, support vector machines come out of this theory. Okay? So this is one question that we're going to be looking at now. The other one, of course, is this perennial question: how much data is enough data? Should I gather more data? Or, these days, I do have these bazillion examples sitting on disk, but should I burn more cycles trying to mine more of them? right? Should I be just satisfied with a random subset of 10,000 of them, or do I really want to go to 1,000,000, right? Is there a way to answer this question, or do I just have to painfully find out by trying? And then, even if you did 1,000,000, what if you went to 1,000,000,000? Can I be sure that I don't need to go to 1,000,000,000, right? We would very much like to be able to answer this question, right? So, the other thing that we're going to be trying to figure out here is how many examples are enough? Can I have some sort of a priori estimate of how many examples I'm going to need to use in training in order to guarantee that I have, pretty good generalization? Okay? So what we're going to look at here are answers to these questions. So as usual in theory, let's start with a few definitions, but these are definitions that we mostly already know. So I'll go through them quickly. X is my training set, a bunch of instances. H is the set of hypotheses that I'm going to consider, right? So the mission of my learner is to pick one of these hypotheses and tell me, I believe this is the truth, or as close as I can get, okay? There's a set of possible target concepts C, which is not necessarily the same, right? Your concept came from some set of concepts, and there's the set of concepts that your learner is looking at. They might be the same or they might not, okay? So I'm gonna call the set from which my target concept comes C, okay? And now, I'm going to assume that my training instances are generated by a fixed probability distribution on the instance space. Right? I'm going to randomly generate email messages, right? By randomly, sticking words into them. And they might or might not be spam, okay? I'm going to call that distribution curly D as usual, right? So this is a distribution over my instance space without the labels, right? So I have a distribution that generates a message, and then later I'm going to generate a class from it. Okay? But the distribution, the important thing to remember in what we're going to be doing here is that the instance is generated randomly, but then the class is deterministic. Right? We're not in here going to look at the case where this instance 80% of the time is positive and 20% of the time is negative. We can handle that case in general, but here we're just going to stick with the simplest case. Okay? And so now what the learner does is it sees a sequence of training examples C and examples X, C of X, where C is the class of X. Okay, and of course this came from my target concept C, which is a member of my set big C. Okay. So the instances come from the distribution D, and then the teacher, right? We have a teacher that says, oh, the label for this instance is C of X. Okay. Any questions? This is all straightforward. Okay.
Could you please explain what you mean by concept?
One more time?
Could you explain what you mean by concept, the C, the big C?
No, again, a concept, remember, a concept is just a binary class. When the function that we're trying to learn is binary, we call it a concept. When it's Boolean, right? A concept is just a Boolean function. Right? If you prefer, everywhere you see concept, just think Boolean function. Right? Concept is, this is a tree or this is not a tree. Right? A multi-class problem would be classify this into tree, shrub, grass, animal, etc., etc. Okay? Again, for simplicity, we're just going to consider the binary case, and that's what we call concept. Okay?
So is the classifier, like classifier outputs?
The classifier is your hypothesis, right?
Okay.
So the classifier, if it's a concept learner, right, is also going to output 0 or 1. The whole question is, how does that function relate to the real one, right? So the classifier produces a Boolean function, right, a concept, and the real concept is also a Boolean function, and we would like the two to agree as much as possible. Okay? All right. So the learner is going to output a hypothesis H, which hopefully is a good estimate of the real concept, the real Boolean function C. Okay? And the way we're going to evaluate H is by seeing how accurate it is on future instances from curly D. Right? And again, my instances are chosen probabilistically according to D, but then my classes are given by the teacher deterministically. Okay? This is just, stating in summary form the setting that we've been in all these weeks. Okay? All right, so the true error of the hypothesis, which is what we're really interested in, right, is the following, right? Let's suppose that my instance space is this rectangle, right? So we're going to use our good old stalwart, the Venn diagram, right? This is my X. And let's say that my concept C, my true concept C, is this ellipse, right? Inside it, you're positive, and outside it, you're negative. Okay? My hypothesis, however, is this ellipse. Right? Which means that it's right some of the time and it's wrong some of the time, right? Where does this hypothesis make errors? In these two regions, right? In this region, the true answer is plus, but my hypothesis says minus, right? And in this region, it's the opposite, right? The true hypothesis is, the true class is minus, but the hypothesis says plus, okay? So the true error is basically the sum of these two areas. Although in generally, what we have is a distribution, so it's basically the sum of the probability mass that's piled up on those two areas that I hatched, okay? So here's the definition. The true error of the hypothesis, error sub curly d, is the probability over all the instances in D that the class is different from the true class is different from the predicted value from H. Okay? And notice this, so this is an expectation computed according to the probability distribution over the instance space. Okay? Everybody with me? Very good. And now, of course, we have two notions of error. Training error is the probability that H differs from C on training instances. Okay? And the true error is the probability that H differs from C over future instances that are chosen at random from curly D. Okay? And what I'm really interested in here is the relationship between these two. So, I would like to bound the true error of H given the training error of H. So I've seen how often H differs from C on the training data. I want to estimate how often it's going to differ from C on the data that I haven't seen. Right? That's the goal here. But to simplify things further, let us first consider the case where I'm able to get to perfectly fit the training set. Okay? In general, you might not be able to do that, but with a sufficiently powerful learner, like say a decision tree learner, I can always do that, right? Just basically by memorizing the training examples, right? So let us for now assume that we are able to do this, right? So I have a learner that is able to perfectly fit the training set, meaning my training error is going to be 0. But of course, the real error, the true error might not be, and that's what I want to figure out. Okay? Questions? Version spaces. Remember when we defined version space? The version space is the set of hypotheses from my original hypothesis space that are consistent with the examples that I've seen so far. Right? When I see a new example, I throw out all the hypotheses that make the wrong prediction for it. And on an ideal day, at the end of the day, I have one hypothesis left in my version space, and that must be the true one. On a bad day, I have 0, and I must change my hypothesis space. On an okay day, I actually have a whole bunch of hypotheses, and then I need to, randomly choose between them or average them or something. Okay? So here's a graphical illustration of this. Each of these points is an instance in the training set. So each of these is a training example, right? And my Venn diagram now is my hypothesis space, right? So each point on here is a hypothesis, okay? And I'm labeling each point with both its true error and its error on the training set. Okay, I'm calling the error on the training set R. Okay? So for example, this hypothesis here had an R of 0.4, right? Which means it's not in the version space, right? The only hypotheses in the version space are the hypotheses for which R is 0. So this line here is meant to include all the hypotheses whose error on the training that is 0, and that's the version space. Okay, so this here is the version space. Okay? And now, truth in advertising. I'm not going to be able to predict what the error of my hypothesis on test data is going to be. This is too hard. What I'm going to be able to do, though, is to put a bound on it, which is not bad. Particularly if that bound is low, this is pretty useful. If I can guarantee that, the generalization error of my hypothesis is at most 10%, that's something to be pretty happy with. Okay? So the question for us, stated a little bit more technically, is what is the highest error among the hypotheses that are in the version space? Okay? I've seen a bunch of examples. I have this many hypotheses left in the version space. They all have training error 0, right? Because otherwise they wouldn't be in the version space. And my question is, what is the biggest error among those hypotheses? Right? Because I know that whatever hypothesis I pick from the version space, then its error is never going to be bigger than the worst one. Okay? So if I know what that worst error is, I have a bound on the true error of the hypothesis that I'm going to return at the end of the day. Okay? Everybody clear so far? Very good. So after all these preliminaries, here's the punchline. It's a very short punchline. But that punchline actually has a long setup. Like the punchline is just this little formula here. So here's the fundamental result. Let me go through it step by step. Let's suppose my hypothesis space is finite. Later we will deal with the case of infinite hypothesis spaces like, Rn and, continuous inputs and whatnot. And D, this is Roman D, not curly D, is a sequence of M independent random examples of some target concept C, right? At least one. Then, for every epsilon between 0 and 1, the probability that the version space contains a hypothesis with error greater than epsilon is less than the size of the hypothesis space times e to the minus epsilon m. This is a bit of a mouthful, but here's the important thing about this, right? In the setting that we've just described, right, my learner looks at that training set, it outputs a hypothesis, and I can guarantee that the probability that that hypothesis is bad, meaning the error is greater than epsilon, is at most size of h times e to the minus epsilon m. And notice there's good news and bad news in this. There's a spectacular piece of good news here, which is that this probability of a bad result goes down exponentially with the size of the training set. This is fantastic. By linearly increasing the size of the training set, I get exponentially better and better. Right? So this is the good news. And in fact, there's even a more general, amazing piece of good news here, which is we can have guarantees. Right? People used to think, going back to Aristotle, right, that, deduction, right? When you say all humans are mortal and Socrates is a human, then Socrates is mortal. I'm sure about that. It's guaranteed, no doubt. Induction is a shot in the dark, right? You have to get lucky. It's very random. Who knows, right? You can never be confident of the hypothesis that you've induced. Sure, Plato was mortal and a human, and so was Socrates and Aristotle, and now I've induced that all humans are mortal. But are they really all mortal? Are you sure that there aren't any immortal humans? At least on TV there are some immortal ones. Right? What this is saying is actually, hey, we can have guarantees. In the 60s, there was this earlier notion of learning in the limit and whatnot, and unfortunately that was very depressing because mostly people just came up with a bunch of negative results. You can't learn this, you can't learn that. And so things again look very bad. You could actually say that what Leslie Valant got the Turing Award for was actually showing that you can have guarantees on induction. It's a powerful thing, not just for computer science, but for, human knowledge in general. Now the key, of course, the difference between the PAC framework, or one of the key differences between the PAC framework and previous ones, is that the guarantees now are going to be probabilistic. This is the thing, you want to guarantee with absolute certainty that you've learned the right concept. That can't be done. You just want to be highly confident that you've learned approximately the right concept. That we can do. Or that we can do in many cases, right? There's also a lot of negative results in learning theory. But now actually we can have some interesting positive and negative cases. Okay? So, but before we go on, let's actually see why this is the case. And if you think about it, the most notable feature of this theorem is that the statement is longer than the proof. Which means that we've already gotten through the most painful part of this. So let's see what the proof is. Right, here's the proof. It's beautifully simple, 3 lines. First of all, let's suppose that I have a hypothesis that's bad, right? This is a hypothesis whose error is greater than epsilon. Right? I would, let's say the epsilon is 5%. What I really want is to learn a hypothesis with error less than 5%. I'm willing to tolerate 5%. I don't want 10% or 20%. Okay? But now let's suppose that I have a hypothesis whose error was more than epsilon, right? And what I'm going to ask is the question, what are the chances that this hypothesis gets a random example right? Right? Well, obviously it's 1 minus epsilon, right? Epsilon is the error by definition, right? So the probability that the hypothesis is right is 1 minus epsilon, right? Everybody agree? Okay. And now it's very convenient to upper bound that 1 minus epsilon by e to the minus epsilon. Okay? This just has to do with, the fact that, the exponential function, right? So this is e to the x, and this is 1 plus x. Okay? Actually, I put this axis in the wrong place, but never mind, right? So this is also known as proof by PowerPoint. In this case, it's not PowerPoint, but remember the important concept of proof by PowerPoint. Right? The real proof is not that hard. By the way, there's another very important kind of proof, which is, proof by intimidation. Widely used in science. Proof by intimidation is you make that thing so horrible that the reviewers of your paper just are like, okay, I'm willing to believe you. So anyway, I shouldn't be telling you this, but I couldn't help it. All right, so let's go back to more serious stuff. This is how I publish all my papers. Oops. All right, so we've just found that the probability that a bad hypothesis gets a random example right is at most e to the minus epsilon. Okay? Next and most important step. What is the probability that that bad hypothesis gets all m examples in the training set right? Remember, they're all independent, right? The probability that it gets one of them right is e to the minus epsilon, right? So what is the probability that it gets m of them right? It's e to the minus epsilon multiplied by itself, n times, right? It's like flipping a coin, right? What is the probability of always getting heads, right? If the probability is a half. Well, it's half raised to the number of coins that you flip, right? So the probability that the hypothesis is consistent with m examples is, let me actually raise that because it's getting in the way, is e to the minus epsilon m. Right? Everybody agree? And this is our great piece of good news. As I linearly increase the size of my training set, it becomes exponentially less likely that a bad hypothesis will make it through. And you see why, right? Because we require that the hypothesis be correct on all the examples. If the hypothesis is bad, right, it's very unlikely that we'll be right on every single one of those examples, right? I have 1,000 examples, right? What are the chances that a bad hypothesis will manage to get every one of them right? Very low, right? And for 1 million examples, it's, even vanishing with smaller, it's tiny, okay? All right, so that's the good news part, but we're not done, and now comes the bad news part, right? Because this was the probability that one particular hypothesis would be right. But this is not what a learner does, right? A learner does not have one hypothesis. A real learner is not a clock that's stopped at 12, right? A real learner actually reacts to the data, right? So what a real learner does is it picks one hypothesis from the hypothesis space. And the unfortunate thing is that if the learner is doing its job of fitting the training data, as long as there's one bad hypothesis in the hypothesis space, it'll take, one bad hypothesis that looks good, right? It can return that one, right? So as I increase the size of my hypothesis space, my chances of having a bad hypothesis that looks good on the training data go up. This is the bad news, okay? And now, so what is that probability exactly? Well, again, we're going to bound it, right? We're just going to bound it using something called the union bound. And the union bound just says that the size, the cardinality of the union of a set of sets is at most the sum of the cardinalities of the individual sets. Okay? And now here's a graphical, the union bound is very important in learning theory, right? People are always using it. Why is that the case? Well, suppose that the sets that I'm adding up, here's A, B, C, and D are these sets, right? This one has, some number of elements, this one has some number, this one has some number. What is the cardinality? Let's say that the cardinality of A was, 5 and 10 and 2 and 20. What is the cardinality of the union of these sets if they don't overlap? 5 plus 10 plus 2 plus 20, right? It's the sum, right? Now what happens if they do overlap? What happens is that when I just add their cardinalities, right, I'm double counting things, right? So but the moral of the story is that the cardinality of the union is always going to be less than or equal to the sum of the cardinalities, right? Sometimes a lot less. And this is the thing, is that the union bound is kind of loose most of the time. But the advantage is that now I don't have to deal with this, combinatorial explosion of inside, outside, which combination of sets are you in, and how many, think of inside, outside, right? You don't want to deal with that. So you just use the union bound, okay? So we use the union bound, and of course what we have now is the size, right? What I have is all my hypotheses in my hypothesis space, right? So a pessimistic bound, but it's still a bound, is that the probability that any one of them will be right on all the examples while being bad, right, is just size of h times the probability that a particular one of them is right. Okay? Everybody follow this? Okay, so we have a nice theorem with good and bad news. Notice what this is doing, right? It's bounding the probability that a consistent learner will output a bad hypothesis, whereby bad we mean that the error is greater than epsilon. Okay? But now, okay, fine. What can we do with this? Here's a very nice thing that we can do with this. Let's say that we want this probability to be at most delta. Right? I want to guarantee that 95% of the time I return a hypothesis that is at least 90% accurate. Right? This is where now you've actually seen the probably approximately. Right? One of them is the epsilon and the other one is delta. The approximately is the epsilon. Right? Meaning that I'm right, 90% of the time. I'm approximately right. The probably, right, is that I'm not actually even going to guarantee that I return a hypothesis that is 90% accurate. What I'm going to say is that what I can guarantee is that 95% of the time, I return a hypothesis that is 90% accurate or better. Okay? And this is what's a little subtle, right? Like back before Leslie Valiant, people didn't do these two things. They had the epsilon, but they didn't have the delta. It's by having the epsilon and the delta that we can actually have, a lot of non-trivial guarantees on, non-trivial learning problems. Okay? And actually, you might think, well, but this is kind of a big compromise. In practice, it's actually not. You know why? Because, as we will see shortly, making epsilon small is costly. But making delta small is not costly. Because I can make it very, very small, I can make it exponentially smaller by linearly increasing the size of the training set. So in practice, I can make my delta be something, 10 to the minus whatever you want. Okay? Epsilon is more of a problem. So even though we've gone from, approximately correct to probably approximately correct, the probably part can actually be with very high confidence. Okay? So, how does this come about? So I want my probability to be at most delta, right? So if I guarantee that size of h times e to the minus epsilon m is less than delta, I've guaranteed what I want, okay? Since this is an upper bound on what I'm interested in, if that's below delta, then what I'm interested in is also below delta, okay? So now I have an expression here, right, an inequality, right? And now what I can do is I can solve for m, right? Instead of having delta by itself on one side, I can just have m, the number of examples. And so what this tells me, and this in some sense are like the key contribution of packed learning, is it tells me how many examples I need to be confident to level delta that my concept is accurate to level epsilon. And that number is 1 over epsilon times log of the size of the hypothesis space plus log of 1 over delta. Okay? And now, this is not a very complicated expression, and each of these pieces, is worthy of some attention. First of all, notice that it's 1 over epsilon, right? So if I want to say, have epsilon go from 10% to 1%, I need to multiply the size of my training set by an order of magnitude. Right? So as I said, making the epsilon small does have its cost. On the other hand, this is the good news. Notice that it only depends on the log of 1 over delta. Okay? So I can afford to make delta very, very small without paying a big cost in amount of training data and processing time for it and whatnot, right? So that's good news. The bad news, unfortunately, is this log of the size of the hypothesis space. Now you might think, well, log of the size of the hypothesis space doesn't seem that bad, right? It's a log, right? Log is good. Why is this still bad news? Can anybody guess why? Or hypothesize why?
Hypothesis space grows exponentially.
No, right? Thank you for giving exactly the wrong answer.
Yeah.
No, seriously, right? Exactly the wrong answer is often the perfect step on the way to the right answer. And this is, of course, the natural answer, right? If let's say, for example, that D is my number of inputs, right? If the number of hypotheses was just 2 to the D, right? Life would be good, right? Because once I take the log of that, I would just have D, right? So my amount of training data would just have to grow linearly with the number of input dimensions, not a problem. In fact, if I restrict my hypothesis, as we will give in an example shortly, to just be conjunctions, right? Then you're in the situation. The problem is that, remember, what is the number of possible, say, decision trees over D inputs? Or no, let's not do decision trees, Boolean functions. How many Boolean functions of D inputs are there? You remember?
2 to the power D.
Yeah, this is the big bummer, right? Remember back in week 1 we saw this ridiculous thing that in machine learning we're not just dealing with an exponential problem, we're dealing with a doubly exponential problem. And so, the moral of the story is my log gets rid of one of these, that's not bad, but unfortunately the big bummer is the other one is still there. And what this means is that for powerful realistic learners like decision trees and multi-layer perceptrons and whatnot, the bounds that this theory is going to give you most of the time are still going to be too loose. You'll see what the bounds give you, and then in practice how many examples you need to have with generalization, and then tend to be much lower. Okay? So, the role of this theory is really not to predict what you're going to have or exactly what you need. It's as a guide. Right? Certainly, if you can afford that many examples, you'll have that guarantee, but you should be aware that you're probably, it's probably overkill to have, this number of examples. Okay? But then when you start applying this to different learners, you also get a qualitative understanding of what things the bound, the error, the M depends on, and that can be a guide to designing your learning algorithms. You can try to come up with clever new ways of, making this bound as small as possible, and that's actually where support vector machines come from. Okay? So even though this theory is not useful directly as a practical tool, it can still have a lot of uses in a more qualitative, indirect way. Okay? Questions so far? All right. So here's an example. I'm trying to learn conjunctions, right? And I want to know how many examples are sufficient to ensure that with probably at least 1 minus delta, every hypothesis, every conjunction left has at most error epsilon. Okay? Simple application. Here's my expression. To apply this expression to a particular hypothesis space, right? If you think about it, give me a second here. The epsilon and the delta, right, are just things that the user tells me, right? The user, who could be you, says, I want, this, I want epsilon of 10% and I want delta of 1%, right? And then you're supposed to tell them how many examples they need. The only thing left to figure out is the size of the hypothesis space, okay? Which in most cases is not that complicated. So for example, let's suppose that what I have are conjunctions, right? So Boolean input and I have conjunctions, right? Meaning my concept is just a conjunction of, for example, x1, not x2, x3. Okay? So how many of those are there? Can anybody tell me? If I have n inputs, how many conjunctions are there over n inputs?
Yeah. 2 to the n.
2 to the n. Anybody agree or disagree? I applaud your bravery in saying something that is different from what's on the slide. That is the kind of attitude we want to discuss. Yeah. So, what is your... I can imagine why you're saying 2 to the n, but why don't you tell me?
Each of the possibilities has 2 options, and there's n options.
What are the options? So I have a conjunction, and you're saying the options are negated or not negated?
Right.
Very good, but remember, for each of the variables, right, I have x1, let's say to x10, right? And for example, let's take the conjunction x3, not x5, x6, right? How many options are there for each variable?
There's a third.
There's a third one, right, which is not included, right? So for each variable, there's not include, negated, and include but not negated. Okay, so for each variable there's 3 options, so the total is 3 to the n. Okay, so all I need to do is replace size of h by 3 to the n, right? So this becomes n log 3, and I get something that most of the time is going to be pretty reasonable. Okay, So for hypothesis spaces that are not too large, packed learning gives you, a nice answer. Okay. Did everybody follow this example? Pretty straightforward, right? Here's another example, our good old friend playing tennis. Okay. Let's say for concreteness that I have one attribute with 3 values, which is outlook, 9 attributes with 2 values each, temperature, humidity, wind, etc., right? And my language is conjunctions of features, right? Outlook, etc., or nothing, the null concept. Okay. So what is the size of my hypothesis space in this case? Well, there's the null case, which is 1, right? And then for outlook, what are the possibilities? There's each of its 3 values, right? Plus, what's the other option for outlook?
No.
It's not included in the conjunction, right? So there's 4 for outlook, right? And now for each of the binary attributes, how many possibilities are there? 3, right? True, false, are not included. And there's 9 of them, so I get 3 to the 9. Okay? So my total is 4 times 3 to the 9 plus 1, which is 78,733. Okay? Easy street, right? So here's what my M needs to be. And now let's say that I want to ensure that with probability 95%, right? 95% is 1 minus delta. I want to make sure that my hypothesis has error at most 10%. Okay? How many examples do I need for that? Okay, well, epsilon is 0.1, right? Delta is 0.05. We plug that in, and we get 143. Quite affordable. On the other hand, this is a toy problem, right? On a real problem, things might not be so happy. Okay? Questions? Okay, so we have one unfinished piece of business. Well, actually, let me just say one more thing before we go on, and we will leave Vapnik-Chevenik as dimension to next time. The one thing I want to say before we adjourn is packed learning actually adds one more thing to this notion, which is that you have to be able to learn that hypothesis in polynomial time. Polynomial in 1 over epsilon, 1 over delta, and the size of the concept. And this is another important contribution of Valent, is that previous to him, learning theory was irrespective of computational considerations. And statisticians were happy with that, but we as computer scientists can't be, right? If you could approximately correctly learn a concept, but it took you exponential time to do that, this is no use. So packed learning is what we saw before, except that in addition, you have to be able to learn the concept to within delta and epsilon in polynomial time in 1 over delta, 1 over epsilon, and the size of the concept. Okay? All right. So next time we will finish learning theory and we'll talk about support vector machines. And in the meantime, have fun with your last assignment. All right. Are you ready? Okay. Hold on. Today's class is going to be interesting, in this sense of interesting. Okay, so what are we going to do today? 2 things. First of all, we have some unfinished business from last time, learning theory. In particular, we need to talk about agnostic learning, and then talk about BC dimension. And then we're going to talk about support vector machines. Okay, so today's main piece is going to be support vector machines. And it's actually a very nice segue from BC dimension to support vector machines, because support vector machines are actually based on the theory of BC dimension. Okay? So remember last time, the last thing we did was define packed learning, right? And the idea of packed learning is that it gives you the number of examples that you need to be confident that you've learned approximately the right concept. Okay? So this is the idea of packed learning. Okay? And the definition was fairly long-winded, but the basic idea is the more examples you have, the more confident you can be that you are learning approximately the right concept, right? And the approximately is captured by epsilon, and the confidently is captured by delta. Okay? And we also want this to be possible in polynomial time. Okay? So for a concept to be packed learnable, meaning probably approximately correctly learnable, right? You have to be able to get to the delta and the epsilon, delta confidence and epsilon error, right? In polynomial time. Okay? Polynomial in 1 over delta, 1 over epsilon, n, and the size of the concept. Okay? So it's both a statistical and a computational notion. So this is where we left things last time. But there were two very big limitations of this result. The first limitation is that, remember, we derived this all under the assumption that I can find a hypothesis with zero error on the training data. Right? This was all about the version space, right? And now what we're doing is like we are bounding the error of the hypothesis in the version space. Okay? But in general, the version space might be empty. Right? I might have no hypotheses that are consistent with all the training data. And in fact, this happens all the time when you don't have a very powerful learner. Right? You could have a very powerful one, like say decision tree learner, where you always, get all the examples correctly, assuming the examples themselves are consistent. But the problem, as we saw, is that for those learners, these bounds are probably not going to be very useful because of the double exponential. Okay? So these bounds will tend to be useful for learners that are, something like, say, naive Bayes or the perceptron, right? That only have so much power. The problem with those learners is that most of the time, they're probably not going to fit all the training data well, and then the theory that we just did does not apply. Okay, so the first thing we're going to do is deal with that problem. And we're going to see what's called agnostic learning. Right? Agnostic as opposed to the, believing learning. Believing learning is like, I believe that the right concept is in this hypothesis space. Agnostic is, I don't care, it might or might not be in the hypothesis space, I will still have something useful to say. Okay? So this is the first thing we're going to do. The second thing that we're going to do is, we assume, remember, our pack learning result, right, depends on the size of the hypothesis space. Right? Which is fine as long as the hypothesis space is finite. If the hypothesis space is infinite, then what? You need infinite examples? That's not very helpful. Okay? And a lot of the hypothesis spaces that we deal with are infinite, like say perceptrons, right? Or nearest neighbor, on a continuous space, Rn, and so on and so forth. So then the last thing we will do in this theory section of the class is see how we can handle infinite hypothesis spaces. And the VC dimension is this very, very clever, but also somewhat difficult idea that actually lets us do that, and we will see what VC dimension is and how it works. And as usual, feel free to ask questions at any point. Okay. So first step, how can we do agnostic learning? Right? And the idea in agnostic learning at some level is very intuitive. It's this. Suppose that I do not have the right concept in my space, right? That could happen. Right? My space is just hyperplanes, but the concept that I'm actually trying to learn is not a hyperplane. But so let's suppose, for example, that the concept we're trying to learn is like, say, a parabolic, surface, right? But all you can learn is hyperplanes. So what would you like to do? Think about it, right? What you would like to do is hopefully learn the hyperplane that best approximates the parabola that's really there, right? Or you have a surface that maybe is like this, right? It kind of curves a little bit. It's not a straight line, right? But what you want to do is hopefully try to come up with a straight line that is as close to that as possible, and that was the best that you could do. Okay? So the idea in agnostic learning is that we don't guarantee that you've learned the right concept because it might not be in the space, right? I might not get an error of 0 on the training data, right? But what I'm trying to do is guarantee that I'm as close as possible to the true concept. Okay, because that's the best I can do. Okay, so how do things change? Actually, things don't change that much, right? So if we there's one crucial thing that changes, and the rest doesn't, right? So if you think back to this theorem, right, which is really the core of this whole pack learning idea, there were two things that we used here, right? The first thing was this fact that the probability that one hypothesis that's bad, meaning its error is more than epsilon, is consistent with an example, is at most 1 minus epsilon, right? Because its error rate is epsilon and the example is drawn at random, right? This is a very straightforward idea, right? And then since I'm assuming that all the examples are independent, right, then the probability that the hypothesis is consistent with m of them is just this raised to the m, okay? So this is the part that we're going to replace. And then there's another part, which is just applying the union bound, which says that, the probability that there's, any hypothesis, any bad hypothesis is consistent is the sum of the probabilities of each one of them. So since there's size of h of these hypotheses, I'm just going to have size of h times that probability that came from the previous step. Okay? So this was our demonstration. Now what's going to happen here is like the union bound part of things is still going to be the same, which is unfortunate because the union bound is loose, but it still applies here, right? The part that doesn't apply here is that we're no longer going to assume that the hypothesis is consistent with the example, right? It might not be, right? It might not be consistent with all the examples. So what do we do in that case? Well, in that case, there's a result from statistics that comes to our aid. And that result is called Hufting bounds. In computer science, they're sometimes called Chernoff bounds. But, really they are, because, and then there's like the additive and the multiplicative Chernoff bounds, and Chernoff came up with the multiplicative ones, but the one that we're going to use here is the additive one, which was really invented by Hufting, right? It's very unfair, in science that usually the person who invented something, for some strange reason, winds up not being the one that it's named after, right? But, but hey, better to have invented it than to not have. So, what are Hufting bounds? Hufting bounds are sort of like, the two key tools of the learning or of the pack learning theories are the union bound and the Hufting bound. So what is the Hufting bound? The Hufting bound does just what we need, right? The Hufting bound, I'm not going to prove it here, you just have to take it on trust, but, if you're curious about the stats, I can certainly point you to the paper, which is not, it's a fairly short and easy to follow paper, but, it still takes some time. But here's what the bound says. This bound can be presented in many forms. We're presenting it here in the form that is most convenient for what we want to do. So here's what it says. It's a bound on the probability that the real error of the hypothesis, notice this is error sub curly d, meaning error over the true distribution curly d, right? The probability that this error exceeds the error on the training data d, right? So this one is what we can measure on the data, right? And now because we're doing agnostic learning, it is generally not going to be 0. It's going to be whatever, right? We actually don't require that it be anything in particular. And this error here is the error that we, sorry, I said this the wrong way, right? So this error here is the error that we can measure on the training data, right? This is what we know. And this is what we would like to put a bound on, the true error, right? And so now, before, right, I assumed that my error on the training data was going to be 0, and then I put a bound on what the test error was going to be, right? What I'm going to do now is I'm going to say, well, the training error could be anything, but I'm going to put a bound on how much more than the training error the test error is, okay? So if the training error is 10% and, this epsilon is 1%, well, then this is 11%, okay? So that's not bad. So what happens is that, I still get a benefit, obviously, from the error of the training, on the training data being low, right? The lower it is, the lower the generalization error will be. I just have to add this, uncertainty amount, okay? So, the epsilon is going to be the difference between my training error and my test error. And if I can bound that epsilon, I'm good, okay? And this is exactly what the Hufting bound does. So what the Hufting bound does is, let me just erase this scribbling. Good. Right, so what the Hufting bound does is say that this is at most, right, so the probability that the test error is going to be a lot higher than the training error is going to be at most e to the minus 2 m epsilon squared. Okay? So this is the part that you have to take on faith, right? We're big on faith here. Or at least in just this little section. So remember before, right, we had something like e to the minus epsilon, right? This is what we had in the, in the sort of like non-agnostic bound. Okay? So if you compare the two, right, you notice, first of all, they're similar, right? They both have this nice property that they get exponentially better with more data, right? Remember, that was the big news we had last time, was that, hey, as I grow my training set size, my probability of something bad happening goes down exponentially, and that is still here, right? So the e to the minus dependency on m is still there. Okay. What has changed is that instead of m, I have 2m. Is that instead of epsilon, I have 2 epsilon squared. Okay. So, this is somewhat bad news, right? Because it means that instead of linear in epsilon, I'm not going to be quadratic, right? So this is not great, but it's still polynomial. It's still manageable in many cases. Okay. So what we do is we're going to switch into the proof that we had before, the Hofding bound, and then we're going to get basically something that's almost the same thing that we had before again. Here's basically, once we've done this part, right, we just now need to apply the union bound as we did before and say the probability that any hypothesis is going to, is going to, match the data to this level while being bad is going to be the size of the hypothesis space times the Hofding bound. Okay? So the bottom line is that our result is really just composed of two pieces, one of which is the Hofding bound and the other one is the union bound, and you're multiplying the two, right? Roughly put. Okay. And so at the end of the day, what do we have? We have a new expression for the number of examples that you need to guarantee that you learn with, confidence epsilon and, confidence delta and error epsilon. Okay? And what does it look like? Well, notice the dependency on delta is still the same, right? That hasn't changed, right? So I can still get, very confident, without a lot of data, right? This is good. The logarithmic dependence on the hypothesis space size hasn't changed either, right? So this is semi-good news, semi-bad, right? Because it's exponentially less than the size of the hypothesis space, but if the hypothesis space is doubly exponential, this is still exponential, so this is neither better nor worse than before. The thing that's slightly worse is that, instead of having 1 over epsilon, I have 1 over 2 epsilon squared, which, comes from here. Okay? But the bottom line is, even if I don't have a perfect learner, a consistent learner, to use a technical term, I can still have a guarantee as before. Okay? Questions? Very good. So this removes one of the two big limitations of the result that we had before. And now, as long as we are in finite spaces, we're good to go, right? You tell me what delta and epsilon you want, and we figure out what the size of the hypothesis space is, and then I can tell you how many examples you need. Okay? But what about infinite hypothesis spaces, right? And as I mentioned, infinite hypothesis spaces are not exactly rare, right? Anytime that you have real numbers, at your input, you're in an infinite hypothesis space, right? At least potentially, depending on the exact language, right? But even just the simple hyperplane is already an infinite hypothesis space, right? And you see that, if you just naively apply the formula that you have here, your host, you need infinite examples. But somehow this can't be right? I mean, if you're fitting, a single layer perceptron that's just a hyperplane, you should need fewer examples, right, than if you're fitting a multi-layer perceptron which can form any, arbitrarily complicated frontier, right? So how do we do that, right? This seems like a very, big puzzle, right? Until you marry the pack learning idea with this idea of the Vapnik-Chervonenkis dimension, which actually predates pack learning by many years. This was invented in the, late 60s by, Vapnik and Chervonenkis, who it's named after. And then I think it was David Hausler who had this brilliant idea of combining VC dimension with pack learning, right? So let's see what VC dimension is and then what it does for us, okay? And fair warning, VC dimension is one of those notions that, it's a little abstruse at first. It's like recursion. But then once you get your head around it, right, it just becomes part of your toolkit, okay? So let me first of all just give you the intuition about what we're going to try to do here. And then I'll try to, step by step, see what the VC dimension is. And then finally we'll have a nice, so the whole purpose of what we're going to do here is to then have a theorem, something like this, but where instead of the size of H, we're going to have the VC dimension. And then the hypothesis space could be infinite. As long as the VC dimension is finite, we're good. We can still, have a bound on the number of examples that we need. Okay? So this is the purpose of the VC dimension. And the VC dimension is really a combinatorial parameter. It says something about the hypothesis space. So, but first of all, let me give you just a very basic intuition. And the intuition is the following, right? So let's suppose that, I have some positive examples here, right? And some negative examples here, right? And now if you think about it, right, there's an infinity of frontiers that will separate these two, right? So there's actually a hyperplane in this case that separates the two, right? In fact, there's a whole bunch of hyperplanes, right, if you swing this around, right? But then there's also a lot of curves, right? In fact, the whole problem here is that we have two infinities here, right? One is the infinity of hyperplanes, and the second one is, say, the infinity of all curves, which includes the first one, and one infinity is larger than the other, right? But, this is all starting to sound very esoteric, right? The key is to focus on what we care about here, which is we don't care about the details of these curves, right? We couldn't care less, at least as far as the training data is concerned, as far as fitting the training data goes, of whether we use this curve or this curve, right? Every single curve that I drew here, and let me draw some more to make the point even more clearly, right? And make some of them actually pretty bad, right? As far as separating the positive from the negative examples, which is what we care about for classification, right? These curves are all the same, right? So the bottom line is I shouldn't care, or I shouldn't have to worry about the details of my frontier, right? What I care about is how it separates the positive and negative examples, and more importantly, whether it has the ability to separate the positive and negative examples, right? So there's a big difference between two hypothesis classes. For example, if this is my training set, there is no big difference between hyperplanes and other curves because they can both separate the training data perfectly, right? So in some sense here, you actually don't care. If you are in a situation, for example, where now there's a positive example here and another one here, right? Now this is a big difference between the hyperplanes and the others, because with hyperplanes you can't solve this problem. But with arbitrary curves, well, sure you can still solve it. Okay? So what the VC dimension very cleverly captures is this fact that, sure, there's an infinity of curves, but we're going to bypass that infinity. We're only going to worry about how well you can classify specific training points, which are going to be finite. Right? This is the key, is that my data points are finite. I never have an infinite training set. And this is how we're going to keep things finite, is just by worrying about how you can classify the training set and whether I can find the curve that fits, that splits those examples or not in my hypothesis space. Okay? So this is the rough intuition. So now let's look at what VC dimension is, right? And we're going to do this in one step at a time. So first of all, we're going to define these two notions of dichotomy and shattering. A dichotomy of a set is just a partition of the set into two disjoint subsets. A dichotomy of a set is what we do when we label some of the points positive and some of the points negative. Okay? That's what a dichotomy is. Right? And so in some sense, what we're trying to do here is form dichotomies, right? The classifier for a two-class problem, which is all we're going to worry about here, right, is just, it's a dichotomy. Okay? So that's a dichotomy. And now, what is the notion of shattering? Shattering is a relationship between a set of instances and a hypothesis space. We say that a hypothesis space H shatters a training set S if and only if, for every dichotomy of S, meaning for every different possible way of labeling the points in S positive or negative. I can label them all positive, all negative, these positive and those negative, or, these positive, those negative, right? These are all the possible dichotomies, right? And I say that the hypothesis space shatters that set of instances for every single dichotomy. There exists a hypothesis in H that is consistent with the dichotomy. Okay? The way to think about this from the point of view of classification, right, is that H is the hypothesis space of my classifier, right? And I say that H shatters my training set if no matter how you label the training set, there's always a hypothesis that gets those labels right. Okay? Questions about this? Okay, very good. So now we can define VC dimension. Well, actually, before we define VC dimension, let's look at an example of shattering. Okay? Here's the example, but let's do it one at a time. One piece at a time. So here are three instances. Okay? So what are the possible dichotomies of these instances? Right? Well, one is I label them all negative, right? Another one is I say label this one positive and these two ones negative, right? And I can, or then I can label this one positive and, these two negative, right? And so on and so forth, right? And so, what kind of hypothesis space would shatter this set of instances, right? It has to be a hypothesis space that allows me to separate the positives from the negatives no matter what happens, right? No matter how I've labeled them, okay? So what would that be? Well, let's see. First of all, too much. First of all, let's suppose that I label them all negative, right? They're all negative, right? Then, for example, if my concept is this, right? So I'm gonna use the convention that I'm gonna draw a curve, right? And inside the curve, right, is where it's positive, and outside the curve it's where it's negative, right? And what I'm gonna show you is that the set of ellipses, or even just of circles, is enough to shatter these instances, right? You see what I'm trying to do here? Okay, so first of all, what if they're all labeled negative, right? Is there a circle that's, a circle on the plane that does that? Well, sure. I just put the circle far away from all the instances and life is good, okay? What if I label them all positive? Where does my circle need to go?
It's to surround all three of them.
Yeah, it needs to go around all of them, right? They need to all be inside it, right? Easy street, right? Well, now let's suppose that I've labeled, this guy positive and the other two negative, right? Where does my circle need to go?
The top one.
Yeah, just around this guy, okay? And, right, you see where this is going, right? And now let's suppose that I say label these two guys positive and this guy negative. Where does my circle need to go? Let's go to ellipses because it's easy to draw, although a circle will work here, right? Where does the ellipse need to go? Around these two guys, right? So if you look at, the sum total of all these possibilities, right, what you get is this. Okay? So here are my 3 points, and here are all the ellipses I ever need to use to to reproduce any dichotomy of those points. Okay? So the conclusion is that yes, the set of ellipses on the plane, right, does shatter, or at least does shatter this particular set of 3 instances. This is what we've seen so far. Okay? All right? So this is an example of dichotomy and of shattering, and now we're ready for the definition of VC dimension. So what is the VC dimension of a hypothesis space, right? Let me first just say it to you, and then we'll kind of see what it means, right? So I have a hypothesis space, H, and I have an instance space, X, right? And the VC dimension, VC of H, of the hypothesis space H, is the size of the largest finite subset of X that is shattered by H. Okay. If I can shatter arbitrary large sets, then the VC dimension is infinite. Right? I mean, if your concept class is very powerful, it can shatter anything, and the VC dimension is infinite. But of course, the interesting case is when the VC dimension is finite. Okay? So, how would you go about figuring out what the VC dimension of a particular hypothesis space is with respect to a particular set of instances? Well, notice the following. This is the size of the largest finite subset, meaning any subset will do, right? That is shattered by H, meaning that this has to work for every dichotomy, right? So one way to look at this is as a game between you and an adversary. You are trying to make the VC dimension as high as possible. The adversary is trying to make the VC dimension as low as possible, right? And you get to pick the set of instances, right? Let's say that that the instance space was this room, right? You say like, okay, I'm going to start by picking, by putting one instance right here, right? And then, of course, one instance is anything can shatter one instance, right? But start with one, right? And then your adversary says like, oh, I'm deviously going to label this instance, in order to make life hard for your hypothesis class. Okay? By saying, let's say that now I have, 3 or 4 instances, right? Now, you say like, okay, I'm going to put one instance here, one there, one there, one there. Okay, over to you. Another adversary goes like, I'm going to label this one positive, negative, negative, positive. Can you reproduce that dichotomy? Okay? And so we keep on doing this until we get to a number of instances where no matter how you pick the instances, your adversary can always pick a labeling of them that there's no hypothesis that will be able to reproduce them. Okay? This is a little bit of a mouthful, so here's an example. Linear decision surfaces, right? So let's suppose that I have, the plane, right? So my instance space is the plane, X is my plane XY, right? And my hypothesis space is the space of lines on this plane, okay? So let's play this game, okay? Obviously, one instance you can put it anywhere, no matter how you label it, it's easy, right? What about two instances, right? You put one instance here, you put another one anywhere. No matter how the adversary labels that, you can always, if one is positive and the other one is negative, you put the hyperplane between them. Otherwise, you put the hyperplane, over on one side. Okay, so that you can always do, right? Okay, now but things get more interesting once you get to 3, right? So first of all, let's suppose that these are the 3 instances, right? Can you find the hyperplane to split them, no matter how they're labeled positive and negative? Yes or no? I see some nodding, and I see some, this is what we like. Some yeses and some no's. So
you can, by splitting, you mean you can put the line in such a way that all the positives are on one side and all the negatives are on the other.
Yeah, exactly. Right.
I couldn't really tell which one of the 2 sets you were pointing at.
No, it doesn't matter, right? So, let's say that I pick these points, right? And now the adversary says positive, positive, and negative, right? So in this case, can I put a line here that separates them? Well, yeah, right? It's the line that you just saw. But this is not the answer, right? Because I have to be able to do this for any labeling, right? So, the brute force method, which is still applicable here, right, is, well, let's try all possible ways, right? And my question to you is, we can do this, one step at a time, but will there always be a way to put a line there that separates them? Yes or no?
Yeah. Unless all points are on the same line.
Well, yeah. We're going to get to that in just a second, but for these points that are not all on the same line, is there always a way to split the positives from the negatives?
Yes.
You were the one saying no, right? So let's see why.
I was looking at B.
No. But okay. We'll get to B, right? But for the moment, we're just looking at A. Okay. In A, is there always a way? Yeah, right, because if they're all positive, put them somewhere, right? If they're all negative, put it in another place. If one of them is positive and the other 2 are negative, right, just put it, between that and, right? So there's always a way to do this, okay? Very good. So I can split these 3 points. I can split, them into positive and negative any way that I want, only using hyperplanes, okay? But now, of course, there's a reason why we have this example B, right? Is that the case for B?
First and third are positive.
Right, so for example, if I do this, right, positive, negative, positive, I'm hosed, right? So, question to you, right? We already knew that the VC dimension was at least 2, right? Because we know for 2 we can always split it, right? So does this mean that the VC dimension is 2 because we already failed for 3, or can we keep going?
Keep going. 3.
Keep going because?
You just need any set that can be.
Precisely. This is the number one point of confusion when people are sort of like figuring out VC dimension, is that, yes, it does fail for this case, but it doesn't matter because there only needs to be one case for which it succeeds. Remember, I get to pick the set. And since this set is bad, I do not pick it. I pick this one. By the way, what happened, this is called general position, right? This is a very special case where the points are collinear. So what I'm going to do is I'm going to pick the points in general position, because that's the favorable case. Now the adversary labels it every possible way, but I just saw that is no objection, right? We can still do that, okay? So I just have to find one way of plunking down the points, such that no matter how they're labeled, I can split them with a hyperplane, okay? Everybody agree? So we've just concluded that the VC dimension is at least 3, okay? So now let's go to 4, right? What happens with 4, right? Here's one set, right? Again, I just picked this one. It might not be the best one, but let's look at this one, for example, right? Can I always split the positives from the negatives using a line, no matter how you label them?
No.
So, why don't you be the adversary, right? Take that fun part and label them. How would you label them to make life hard for me?
diagonals
Yeah.
remain the same.
Exactly. This is our good old friend, and not coincidentally, the eggs are, right? There is no hyperplane that will work here, right? Is there, so the adversary now has a way to basically make it impossible, right? But now the question that you need to ask yourself is like, is there some way of arranging these points such that this cannot happen? There isn't, right? No matter where you put the points, this can always happen, right? You know, for example, if you put them all in a straight line, you know, it's not any better. In fact, it's worse, right? So these points are what's called in general position, and in general position, you know, we can't do it, so we can't. Okay? So the moral of the story, so did everybody follow this? So the moral of the story is that the VC dimension of lines in the plane is 3. Okay? Right, I'm on the plane, right? And you know, I can shatter using hyperplanes at most 3 points. Okay? So the VC dimension is 3. Anybody care to guess how you generalize this to D dimensions? Right, so now my question is, instead of being on the plane, I have a hyperplane. Right, so I'm on the, you know, so the dimension here was here D was 2, right? And the VC dimension was 3, right? So what do you think the VC dimension will be for arbitrary D? Too late. What do you think it's going to be for arbitrary D? D plus 1. Right? I mean, you can see the intuition behind that, right? This is definitely not a proof, but it's something that you could, you know, try doing as an exercise. Okay? Notice that, and this brings up a very important point. There's an interesting coincidence that should happen here, right? Is that D plus 1 is the number of parameters in the hyperplane, right? Remember, I have a weight for each dimension plus what?
Plus the threshold.
Plus the threshold, right? So I have D plus 1 parameters. Okay? So now you could say, aha, what is this whole VC dimension complication about, right? It's really just the number of parameters. Like, this makes a lot of sense. The more parameters you have, the more flexibility you have. Okay? So the question is the VC dimensions just the number of parameters? And the question must be rhetorical, right? And the answer must be no, otherwise we wouldn't be doing VC dimension, right? So even though in this particular case, and in some cases, the VC dimension is the number of parameters, in general, the VC dimension could be completely different from the number of parameters. And this is the point that is not quite intuitive, but is actually very important. In fact, support vector machines, which we will study later today, are a very interesting example of a hypothesis space where the number of parameters could be infinite, and the VC dimension is still finite. Okay? And the rough idea there is that, like, sure, I have a lot of parameters, but I have somehow constrained the way in which those parameters can be set, and therefore the VC dimension is still finite. Okay? So this might be slightly surprising, but at the end of the day, it still makes sense. But now let me give you an even more shocking example, right? And I'm just going to actually let you think about it for a week, and maybe, you know, we can revisit it next week, right? I'm just going to, you know, just put that out there. You can have a hypothesis space with one parameter and infinite VC dimension. I'll even give you a hint, right? Let's say that, you know, to keep things simple, my instance space is just the real line X. Right? So what I'm claiming is no matter how, you know, you alternate between plus and minus, right? That's any dichotomy, right? You can, you know, put points on X, right? Label them with plus and minus any way that you want. And I have here in my pocket, but I'm not showing it, a hypothesis class that will, you know, put all the pluses on one side of the frontier and all the minuses on another. Okay? So, if you want a puzzle to solve, you can think about this in your free time. This is actually, you know, it's an example coming from, you know, Vapnik has a book about this, and this is an example that he has there. But you can't cheat by looking at it. You know, it's not just in Vapnik's book, right? But anyway, so, right? This seems crazy, right? How could you possibly have a hypothesis with only one parameter, not even two, that can, produce any separation of the positive and the negative example? Okay. So next week, the solution to our puzzle will be revealed. Okay. This is like those old, crossword puzzle things where, you have to read the next issue of the magazine to find the answer. Okay. Of course, these days there's the web, but let's pretend that it doesn't exist. Okay. So, and any questions about any of this? So this is our notion of VC dimension, right? And now you see what it does, right? Is that the VC dimension, in some sense, characterizes the power that my hypothesis space has to fit training sets. A multi-layer perceptron has more power than a one-layer perceptron, and the technical term for this is capacity. The VC dimension is measuring the capacity that the hypothesis space has to fit data sets. Okay? And now, of course, let's think about this, right? So now what I said, was that we're going to use the VC dimension to derive a bound on the number of examples that I need like we had before, right? And so now what do you think? Do I want a low, in order to need a low number of examples, do I want a low VC dimension or a high VC dimension? Low, right? The higher the VC dimension, the more examples I need to assure myself that I wasn't just overfitting, right? In some sense, we're, thanks to this notion, we're just back in this situation that we know very well, right? The more flexibility I have, the whole idea of pack learning is that if your hypothesis is bad, it's very unlikely that it would get, all the training examples correctly or almost all of them in the agnostic case, right? But if my hypothesis space is very flexible, meaning it has a high VC dimension, then, it's not unlikely that I would fit my training examples well because I can always do it, right? The thing is that if my VC dimension is high enough that I can reproduce any dichotomy of the training set, then once you show me that hypothesis, that doesn't mean anything. It doesn't mean that it generalizes, right? I know I could always have done that. The only case in which I have guarantees is when it's like, it's very unlikely a priori that your hypothesis will fit this training set. Like say, here I have a training set, and you're only allowed to use hyperplanes. Well, chances are the hyperplane won't fit, in which case, try a larger hypothesis space. But if in that case the hyperplane fits well, then you go like, it's very unlikely that would happen by chance. Okay, so this is what's driving this process. Okay. All right, so the punchline is, and I'm not going to show that here, but what we can get is a theorem that looks very similar to the ones that we had before for the number of examples that we need as a function of delta epsilon and now the VC dimension instead of the size of the hypothesis space. Okay? And if you look at it carefully, what the VC dimension is playing is the role of the log of the size of the hypothesis space. And again, notice that for the hyperplane, it's d plus 1, right? So it's something, this is logarithmic. Okay? Right. Now, if you look at it, let's see what happened here, right? Well, the dependence on delta is still pretty much the same, right? It's still order of log of 1 over delta. Good news, right? Now I have the VC dimension instead of the size of the hypothesis space. There's this pesky little 8 here, but there's much bigger things going on here than this 8, right? In particular, the VC dimensions of the hypothesis spaces that we're going to be looking at. And then the dependency on epsilon got a little bit worse, right? It used to be 1 over epsilon, right? This is not the agnostic case. And now what I have is 1 over epsilon log of 1 over epsilon. Okay? But this is like going from n to n log n, right? It's worse, but probably not, probably won't kill you. Okay? So this is what the VC dimension buys you, is that now I can have the same type of pack theorem for infinite hypothesis spaces. That's a pretty clever idea. Questions? Questions about learning theory in general? All right. So, you might still be wondering, well, okay, was this, is this worth it to know all this stuff, right? I mean, the bias and variance and no-frillinge theorems, these are just good things to know, even from a practical point of view. But all this pack learning theory, right, in VC dimension, I told you, if you actually plug some real numbers into these equations or inequalities, the numbers that you get are not quite realistic. So this is not actually useful as a guide for how many examples do you really need, right? So then you could ask yourself, well, what is this good for then, right? Well, it turns out that this is good for designing new learning algorithms. And in particular, it's good for designing support vector machines, which, are, the latest, greatest of the classification techniques that we're going to see here. They have a long history, but they were really only invented, at least in their present form, in the late 90s, mid to late 90s. And then, and then they took off like wildfire because they worked so well. And in fact, these days, for a lot of problems, the first thing that people use is an SVM. Okay, so it's definitely worth knowing about them. On the other hand, fair warning, this is the most mathematical topic that we're going to study in this whole class. And not coincidentally, SVMs also are known for being one of the most difficult topics in machine learning. Okay? So if you just try to learn SVMs from a textbook, it might be hard going. Depending on how much, mathematical, tools you have. So what we're going to, and then what happens is that a lot of people just use SVMs as a black box. They have some SVM implementation that's available open source and they just use it. But, and in fact, this is all we're going to ask you to do in the assignment, right? So in the assignment, you just have to apply SVMs, to a problem and compare with some other approaches and whatnot. Okay? But here's the thing: even when you use something as a black box, it's still important to at least have a rough understanding of how it works. Okay? So what we're going to try to do here is not go into all the gory details of SVMs, because that might not be worth the pain. But hopefully by the end of the day today, you will have an understanding of how SVMs work, what the important parameters are when you're playing with one of those packages, what are the important choices that you have to make, and there are some important choices to make, right? Maybe what things you might want to tweak, and so on and so forth. Okay? So we'll try to have a basic understanding of how SVMs work without, going into the, little details of the math. Okay? And by the way, the thing that makes SVMs difficult is that they do require a lot of math background. Once you have that background, SVMs kind of can be described very quickly. But unfortunately, they do require a whole bunch of math. In particular, they require three things. One of them is learning theory, which we just saw. Another one is kernel theory, which is something that people, in integral calculus and whatnot deal with a lot, but you as a computer scientist have probably never seen and never will see again. And the third one is constrained optimization theory, which is yet another thing that we haven't seen. And constrained optimization, remember when I said, every learner has representation, evaluation, and optimization, and then I said there's three major types of optimization that we use in machine learning. Combinatorial optimization, continuous optimization, and then constrained optimization. Constrained optimization we're going to see today for the first time. Okay? And learning theory, where we already saw. Kernel theory we're just, going to punt on. We can sort of ignore things there. I'll mention a couple of things without, any formality. And, constrained optimization will actually have sort of a 15-minute tutorial on constrained optimization, which is useful in its own right? You will at least have a cocktail party level of constrained optimization such that if you run into a problem that requires it, you will know, that it's there and what you can do. Okay? All right. So, let's press on. So let us demystify SVMs. Actually, just between us, right? It's not like this is going on the internet or anything. It's a part of the reason why SVMs are so hard is that, I don't know why the people who wrote the papers and books about them made them so obscure, right? But let's sort of put all of that to one side, right? And just go straight to the punchline, right? What is a support vector machine? Right? You would think that people would start out with this very simple thing, but they often don't. But that's how we're going to do it here, right? And then you'll realize that a support vector machine is actually a pretty familiar beast. Okay? So what is a support vector machine? A support vector machine is composed of three things. A subset of the training examples. These training examples that I've selected, those are called the support vectors. We will see in a little bit graphically why they're called the support vectors, but one way to think about it is that they are the vectors, vectors are the examples, right? So support vectors is the support examples. They are the ones that are holding up the frontier where it needs to be. Meaning that if I took one of them away, the frontier would fall to somewhere else. Okay? So they're support vectors because they are supporting the frontier. So this is number one. a subset of the training examples. And on a good day, this will be a very small subset of the training examples. On a bad day, it'll be a large fraction of them. Okay? Number 2, a vector of weights for the examples. Okay? So what's going to happen is that each example is going to have a weight, right? No big complication. Okay? All the examples are going to have weights, right? And finally, we're going to have a similarity function. A similarity function is something that takes in 2 examples and returns a non-negative number. Okay? Now, if the similarity function has certain properties in math, it's called a kernel. Not to be confused with an operating system kernel. Okay? This is a very different beast. Okay? But for a lot of our purposes, you can just think of kernel as another way of saying similarity function. Okay? As I said, there are some restrictions on that similarity function, but almost all the similarity functions that you would ordinarily use have the properties of the kernel, so let's not even worry about it. And even if they don't, you can actually come up with the same sorts of, formal results, or not the same, but similar types of formal results that are somewhat weaker. So, it's a similarity function. Okay? And then, so these are the 3 things. And then when a new example comes along, xq, where q, means query, right? How do you predict the class of that xq, f of xq? It's just the sign of the weighted sum over all my support vectors of the class of the support vector times the weight of the support vector times the similarity of the support vector and my query. Okay? So an even simpler way of saying this is that I'm going to predict from my query, what's going to happen is that I'm going to do voting between the classes of the support vectors. And what is the weight of a particular support vector going to be? Right? What is the weight of its vote going to be? It's going to be the weight of the vector times its similarity to the query. Right? And this makes intuitive sense. Some support vectors maybe are more important or better, so they're going to have higher weight. Right? But the support vectors that are closest to the query, that are most similar to the query, should also have higher weight. Right? And I'm going to assume that the class is, -1 or 1. We're just going to deal with binary here. And again, -1 plus 1 is more convenient for these purposes than 0, 1. Okay? So, does this remind you of something? Are support vector machines similar to some previous class of learners that we've seen? And what might that be? Instance-based learning, exactly. Right? Support vector machines are just another kind of instance-based learning. Somehow you can dig through hundreds of pages of books and articles on support vector machines and never see this simple statement. Right? A support vector machine is not a strange new object. It's just a very smart way of doing instance-based learning. Right? Why is this instance-based learning? Look, remember, in instance-based learning, there's a number of things that we can do. One is we can select instances, right? We saw instance selection and, edited, nearest neighbor, and whatnot, right? So support vector machines do a selection of instances. In fact, the selected instances are the support vectors, okay? And then we saw that you could do instance weighting, right? And that's what we're going to have here, is we're going to have weights for our instances. But we're going to set these weights in a very different way from what we saw before, right? And in many ways a clever way, right? And then we also saw that the fundamental thing in instance-based learning was your choice of similarity function. Same thing here. We have a similarity function, and the choice of similarity function is going to be very important. Okay? So, first important observation. Support vector machines at the representation level are not a new approach. They're just a kind of instance-based learning. Okay? Any questions about that?
What does sign mean?
What does sign? Sign is the sign function. Right? It's sine of x is equal to 1 if x is greater than or equal to 0, and -1 if x is negative. Okay, sorry, I glossed over that. Okay, so basically this is just a hard threshold. Okay? Which brings us to our very next point, which is, so yes, SVMs are a form of instance-based learning, but here's an interesting thing. The way they are usually presented in the literature is as a generalization of the perceptron. Remember when I said, oh, the perceptron is very crude, right? It has all these limitations, and now we're going to put it aside, and we're going to do gradient descent, and multi-layer perceptrons and MagProp are all going to be based on gradient descent. But the perceptrons, despite their perceived naivete, can actually be extended to something much more powerful. This is it, support vector machines. It's actually kind of a delicious irony, right? That the dumb old perceptron that got so panned by Minsky and Papert, has come back, 30 years later, as like the latest, greatest, most sophisticated, most powerful machine learning technique. I mean, support vector machines, as we'll see, are really perceptrons with a few, specifically 3 crucial things added, each of which kind of really magnifies the power. And in a way, what we're going to see here is those 3 things. And I can tell up front what they are, and then one of them is this idea of kernels, which is the first one that we're going to look at. The other one is the idea of maximizing the margin, which is a different kind of objective function. And the third one is this idea of select variables to allow for noise. Okay, so these are the 3 things that we're going to see. Okay, but for the moment, right, here's the puzzle for us. So we just saw, right, that support vector machines are kind of instance-based learning, right? And I also just claimed that they're really, a glorified perceptron. So how come, right? If you think about it, perceptron and, say, nearest neighbor, these are very, very different things, right? But somehow they must be kind of the same thing. Otherwise, the SVMs couldn't be both, right? So here's my question to you. What do you think is the relation between perceptrons and IBL? And really, this is the seed from which our whole understanding of SVMs is going to grow, right? Think about it. Nearest neighbor, on the one hand, is very powerful, right? You can form arbitrarily complicated frontiers provided you have enough data, right? They're going to all be like little chunks of hyperplane, right? Remember the Voronoi cells, right? There's these straight lines that separate, the region where one instance is from another. And perceptrons, is just, a single hyperplane. So how could they be, what could the relation between them be? You were raising your hand?
No.
Oh. Bummer.
They both have a linear or surface where they divide.
Yeah, sure. This is true, but this is you could say the same with decision trees, right? Decision trees is also linear surface, right? So actually, let me slightly refine the question and put it this way. I claim that the perceptron is a special case of instance-based learning. And this makes sense, right? Because in instance-based learning, you have, many different, pieces of hyperplane, and in a perceptron, you just have one, right? But concretely, right, how is perceptron a special case of instance-based learning?
Similarity coefficient is 1, I guess, for all the inputs. Then you could have weights for each input. So
not quite, at least at first sight, right? Because remember, in the perceptron, you're actually getting to the heart of the matter, but notice, in the perceptron, the weights are on the features. Right? If I have a data set with n instances and d features, in the perceptron there are d plus 1 weights. Right? Whereas in distance weighted nearest neighbor, the weights were on the examples. Right? In fact, there's going to be a very interesting relationship between these two in SVMs, but we're not there yet. Right? So, so hold that thought, right? So that doesn't seem to quite be the answer, right? So let me give you, anybody want to try something? This is a hard question, right? It's actually not obvious at first sight. So, anybody care to suggest something? Okay, so let me give one more hint, right? Well, let's just think of k nearest neighbor, right? Or even weighted k nearest neighbor. We don't have that many free dimensions to play with, right? But there's a very big one that we haven't touched on yet, and this is the similarity function, right? If you use Euclidean distance as the similarity function, right, you do get these Voronoi cells and this potentially very complicated behavior at no cost to you, right? But Euclidean distance isn't the only similarity measure that you could use, right? So here's my question to you. Can you think of a similarity measure such that k nearest neighbor with that similarity measure becomes the perceptron? In some sense, it has to be like a bad similarity measurement because it destroys the whole power of nearest neighbor, right? So what might it be, right? What could the similarity measure be that basically turns all the power of nearest neighbor into just forming a linear frontier.
Kind of weighted.
Yeah, yeah.
Weighted mean.
Yeah, kind of. Right, so let's be more specific, right? So what I'm looking for is a way to compare two examples, right? So what are some ways of comparing examples that we've seen? There's Euclidean distance, there's Manhattan distance, right? Like there's L something norms, right? Yet there's another way of comparing instances, right? Which is actually used a lot, for example, in say information retrieval, right? And in a lot of areas for different things, which is the dot product. Right? Our good old friend, the dot product. Right? I just multiply the coordinates, one at a time, right? And I add all of that up, right? But in the perceptron, the dot product, right? Everybody remembers the dot product, right? In the perceptron, the dot product was being done between the weight vector and the example, right? This is what a perceptron is, right? It's just the dot product between the weight vector and the example, right? And then with Herschel depth, right? This was the perceptron. But if we use dot product as a similarity measure in k-nearest neighbor, the dot product is happening between two examples, right? That's the difference. But number one, dot product is actually a totally reasonable similarity measure to use, right? Right? The more these things align, the more similar they are, right? Again, people use these things for information retrieval and whatnot, right? Also known as the cosine similarity, right? Because the dot product, after you normalize it, is really just the cosine of the angle, right? So the dot product is really, after normalization, is really saying, well, I will say that your examples are similar if you think of them as vectors. The angle between the vectors is small, right? This makes a lot of sense, right? However, using dot product as the similarity measure in nearest neighbor is a terrible idea because it makes the power of nearest neighbor go away. Right? Because, as we just claimed, right, once you use dot product as the similarity measure, you've lost the ability to form very complicated frontiers. It all just becomes one simple linear frontier. So let's see how that happens. Okay? So we're going to do nearest neighbor, right, with dot product as the similarity measure. Okay, so how? Actually, let's go at this from the other end. Let's start from the perceptron, right? And then see how this can come about, right? So my claim is the perceptron is just k nearest neighbor with dot product as the similarity measure, right? So that's the claim. Now let's see why that claim is true. Well, first of all, here's my definition of perceptron. Okay? My class of my query example is the sign of the sum over all features of the weight of the feature times the value of that feature in the example, right? Everybody remember? This is the definition of the perceptron. I do the dot product of the weight vector and the feature vector. I put that through a hard threshold. If it's above 0, I predict 1. If it's below 0, I predict -1, right? So this is what this formula is saying. Okay? Now notice the similarities and the differences between this and what we had back here, right? Right? Here's my f, here's my sine of a sum of something, but now the something is different, right? So, we're partway there. And, the support vector, we saw that, this is IBL, right? So if we reduce things to that form, we're good, right? But here's the key observation, right? This is the key observation. This is really going to be important for support vector machines. What are these weights? Where did they come from? Right? That's the thing, right? Something is happening inside these weights. And it's by figuring that out that we're going to arrive at the instance-based form, right? The key thing to realize is that, remember the perceptron training algorithm? The perceptron training algorithm worked as follows. If I classify this example correctly, what do? Right? I present the examples to the perceptron one at a time, right? And then I check whether the predicted class is the same as the real class. And if they're the same, what do? One word answer. Nothing, right? I do nothing, right? It's error-driven learning. If you're getting your examples right, go home happy, right? Don't go fixing what I broke is, what's behind that type of learning, right? What happens, however, when you get the example wrong? When the example is wrong, some weights change, right? In particular, the weights of the features that agreed with the class go what? Up or down? Those go up, right? And the features that disagree with the class, those go down, right? Because I want to make this thing be above threshold when it was below before, or vice versa, right? So if you think of this as what's happening to the weight vector, right? I have a weight vector, right? And now along comes a new example. Let's suppose that I get it wrong, right? And what this causes is some change to the weights, right? But what is that change to the weights? If you think about it, that change to the weights basically consists of adding the new example to the weights with a weight that's going to be the learning rate. Remember the learning rate, right? If the learning rate is 1, actually I'm just adding the example, right? But each feature is going to be added with a sign that depends on whether it agrees or disagrees with the class. Okay? So this is the key realization, is that the weight vector at the end of the day is just a weighted sum of examples that you've seen. The weights are going to depend on the learning rate and are going to depend on the classes. But here, is in a very short expression, what's really going to happen at the end of the day is that my weight of feature j is going to be the sum over all my examples of alpha I, which could be 0 if the example was not used, right, of the value of the feature times the value of the class, right? Because all that's going to happen at each stage is that you're going to add this, right, to the weight of the feature, right? If you don't add it, the alpha I is 0, right? If you add it, you get a contribution of eta, the learning rate, right? So this alpha, right, is just going to be eta times the number of times that, I had to make corrections, i.e. the number of mistakes that I made, as my perceptor was learning, okay? Did everybody get this? Right, so this weight, right, this innocent looking thing here, is really, at the end of the day, right, the weight vector is just a weighted sum of examples. Okay, any questions about this? Okay, so if you believe this and you believe this, then let's combine the two. Let's replace wj in here by this expression, right? So here it is, right? I now have the sign of the sum over the features of this thing, which used to be wj times xqj. Okay, so I just replaced one into the other. Okay, and now let's try to simplify this. Let us, switch the ordering of my summations, which I can always do, right? Because addition is commutative, right? So I can push this sum over j inside the sum over I, and in fact I can push it past the alpha I and past the yi. Why is that? I can push this summation all the way to here, right? Why can I push the summation over j past alpha I and yi?
Because they're constants over j.
Exactly. Alpha I and yi do not depend on j, right? So they can be put outside any sum over j. But then here, now I hit xij and xqj, and that definitely depends on j. Okay. So what do I get? I get sum over I of alpha I yi, sum over j of xij xqj. And what is the sum over j of xij xqj? It's just the dot product of of xq and xi. Right? You agree? Right? Sum over j of xij xqj is just the dot product of xq xi. Right? Remember, j is ranging over the coordinates. Okay? Everybody agree? So now look at this very interesting phenomenon. This formula now looks just like the formula that we laid out in the beginning for SVMs. Right? What is f of xq going to be? It's going to be the sign of the sum. And notice this is now a sum over the instances, not a sum over the features, right? This is what we wanted, because that's what happens in instance-based learning and therefore in support vector machines, of weights times classes. And now the only difference is that before, right, we had a kernel xqxi, right, the similarity between x and xi. And now we're just using the dot product as the kernel, right? So, very contrary to appearances, the perceptron is really just a special case of instance-based learning. Okay? Questions about any of this? And this is going to have powerful consequences for support vector machines. In particular, so here's the idea, right? Perceptron, right? Poor thing. It can only learn linear frontiers, right? Well, here comes the first big trick, known as the kernel trick. right? This is the technical term, is the kernel trick. The kernel trick is, I'm going to take my dot product, and I'm gonna squint at it and say like, oh, you, my friend, the dot product, you're really just a kind of similarity function. You're just a kernel. But now I can look at this expression and say like, well, why use only the dot product, right? Let me replace the dot product by any kernel, right? And suddenly my perceptron has become a very powerful thing. But all of the things that I knew about learning perceptrons in various ways will transfer over to this more powerful case. So in a way, the perceptron's revenge, right? The reason it has come back, morphed into a super, algorithm, whereas before it was like this, little turtle crawling along on the ground, is that now I've embedded the kernel in there. And by embedding the kernel, I've gone to only being able to form linear frontiers to being able to form, very rich and complex frontiers. Okay? And, we will see all this play out shortly. So, kernel matrix. Right, so here's the idea. We take the perceptron. So this is actually the traditional way that people derive support vector machines is they start with the perceptron and they say, let us replace the dot product by a general kernel. Okay? And then we have something much more powerful. And in particular, so why is it more powerful, right? And how can we understand what's going on? This is also a very interesting part of this, right? Well, the key objects to think about is what's called the kernel matrix. Everything in support vector machines revolves around the kernel matrix. The kernel matrix is just a matrix of n by n. If I have n data points, the matrix is a square matrix of n by n, and the ijth entry is the similarity between the ith and the jth training example. Okay? So k of x prime is the value of the similarity assumed non-negative between x and x prime. Okay? Right, so this is my kernel matrix. And if you can do things efficiently with kernel matrices, you can learn support vector machines efficiently. Unfortunately, you already see one source of inefficiency for support vector machines is that when your training set is large, this thing is going to be quadratically large. So, scaling out support vector machines is its own interesting problem that we won't get into here, but there's actually, some good solutions to it. However, at the end of the day, support vector machines are not the most scalable machine learning algorithm around. But if you have the cycles to apply them, and and your training set is compatible, then support vector machines might be a very good thing to use. So let me now, remember I said, well, there's all this kernel theory underlying what we're going to do here. Here's where we're going to use something from kernel theory. But I'm just going to say it and hope that you believe me. And it involves a little bit of jargon. But hey, that's life. So let me make the claim first, and then let's see what it means, right? And what it means is actually very interesting. Let's suppose that I have a kernel matrix that is symmetric, right? So I'm assuming that it's symmetric, right? So kxx prime is equal to kx prime x, right? Well, for a similarity function, this makes sense, right? Let's suppose that this matrix is positive semi-definite, right? This is actually something from linear algebra. This means that the matrix has non-negative eigenvalues. If you don't remember your linear algebra, just forget I said that. If you remember your linear algebra, you can go like, okay, I know what you mean, right? But either way, then this is the thing that's like not obvious at all, but very important. My kernel matrix, you can think of the kernel, like the kernel is something that is defined over all space, right? And you can use it in doing integrals and whatnot. But a matrix is just sort of like a finite instantiation of the kernel, right? It's just the similarity for this particular set of data points, right? This is still a dot product. This interesting thing is that we started out with our good old friend the dot product, and then we replaced it by a kernel, made things much more powerful, but we can still squint at that kernel and say, you're still a dot product. You're just a dot product in a different space. The reason this is important is that linear algebra is easy. If we can do everything with matrix multiplications and dot products, life is good. Right? I mean, again, it doesn't scale ideally, but it's very simple. Much simpler than things like multi-layer perceptrons and whatnot, right? That are really hard to, understand what's going on when you're learning. So the claim that I'm making is that any kernel right, with these properties can be expressed as follows. As the dot product, so the kernel between x and x prime can be expressed as the dot product of phi of x and phi of x prime, where phi is a transformation that takes your original features, let's say your D features that you were using to describe your examples, and computes a new set of features from those. That could be fewer or more, they could even be infinite. I could be computing an infinite number of new features. This is one of the things that gets some people really sort of like, enamored of support vector machines, is that this is all happening in infinite spaces, also known as Hilbert spaces. In fact, that doesn't really make too much difference to our daily life, but the interesting thing is that support vector machines are going to effectively be doing dot products in infinite spaces in finite time. Okay? So I've just made this claim so far, but I'm not going to prove it in general, but we will see an example of how this comes about, right? But nevertheless, right, the importance of this is twofold. One is that I've gained all this power, but I'm still in familiar land, right? I'm still doing only linear algebra types of things. This is one very big gain, right? The other very big gain is in this formulation, and one thing follows from the other, I still have a convex weight optimization problem. When support vector machines came along, the main thing that they competed with, and in many cases displaced, was backprop. The thing about backprop is that, well, it's an optimization problem with lots of local optima. You have to fight with it to make it work, and you'll get one result, I'll get another result. With support vector machines, that all goes away. It's a single global optimum. As long as we both got the same problem statement, we will get the same result. So this is, and we don't have to worry about getting stuck in local optima. Our optimization is now much simpler. Of course, there's no free lunch, and we will see where where you're paying the price for this. But nevertheless, in many ways, compared to something like backprop, this is a great gain. Okay? Questions about any of this? Now, here's something to just, a side note that's not going to be important to the rest of the class, but is worth bearing in mind, is that the kernel trick does not just apply to SVMs. People started out doing it in SVMs, but then they went, hog wild, and they started applying the kernel everywhere. The way you can apply kernels everywhere is by saying let me look at my machine learning algorithm that was using a dot product somewhere. I'm going to take that dot product, I'm going to replace it by a kernel, and I'm going to say, you're still a dot product, just in a high dimensional space. So I think pretty much these days, any machine learning algorithm that uses dot products has been kernelized, as the lingo goes. Okay? So this idea was important not just because it led to a better classifier support vector machines, but it's been applied in many other areas. Like, for example, next week we will talk about dimensionality reduction. You can use the kernel trick to do nonlinear dimensionality reduction. Okay? So this is a very powerful thing to have. Okay? All right. So let's see an example of kernels, and then we'll take a break. Okay? So I've just made this claim to you that sounds, very appealing, right? But why should you believe it? Okay? Well, let's see, number one, what some of the kernels are that you might want to use, and number two, how things actually work out concretely. Okay? And by the way, when you see people, in, say, one lab, I actually know examples of this. Like, there's some problem that the company needs to solve, right? And there's the neural network aficionados, and there's the support vector machine aficionados, and they're competing to see who comes up with the best solution, right? What they're doing, right, is they're doing different things. The neural network people are playing with the kinds of parameters and choices that we saw when we talked about neural networks. The number one thing that the support vector machine people are likely to be playing with is the kernel. They're going to be trying different kernels. And this shouldn't surprise us because, after all, SVMs are instance-based learning, and we saw that the key thing, in instance-based learning, the place where you put all your, understanding of the problem and knowledge and whatnot is in the choice of similarity function, which in SVM lingo is the kernel. Okay? Nevertheless, so in practice, when you use SVMs, choice of kernel is one of the main considerations, and people these days, people have come up with amazingly clever and sophisticated kernels. You can have kernels to compare graphs. You can have kernels to compare strings and do NLP with them, right? You can have kernels to compare any object in the world. Okay? But, having said that, just as in, nearest neighbor, Euclidean and, Hamming distance, or value difference metric got you, pretty far in many applications, there's a few standard kernels that, people use all over the place. And, they're probably what you want to start with. And the three most popular ones are linear kernel. Linear kernel is just another way of saying don't do anything. Just use our good old friend, the dot product. And you're like, well, really? You just kind of poured scorn on that and said it's not very powerful, so why bother, right? Well, here's why. Support vector machines, were a theoretical notion, and then they took off when they had successes in three important areas that we've already met. One is comp bio, another one is digit recognition, and another one is text classification. And in a way, text classification is the most revealing one because that's actually where the biggest gain happened. Suddenly you're doing much better text classification. And previous to support vector machines, kind of the best algorithm, to people's surprise, was naive Bayes. Right? And we saw why naive Bayes might do well at text classification, but here's the thing, is that in text classification, the dimensionality of the space is so high, right? I could be using 10,000 words as my features, or even just 1,000. I mean, even 1,000 is a huge dimension, right? That even naive Bayes starts to overfit. How can naive Bayes that's just a hyperplane or a perceptron overfit, right? Suppose that one of my words, just by coincidence, correlates very well with the class, right? It's just, a random event in the training set. If I'm giving myself 10,000 words, and I don't have a lot of examples, let's say, to exert things a little bit, that I have only 100 examples, right? The chances are not bad that, some one word will always, appear in documents of class, interesting, and not appear in documents of class boring. Right, so even if the dimensionality is sufficiently high, even naive Bayes is prone to overfitting. And support vector machines avoid that overfitting, and that's why they do better than naive Bayes. Okay? And we will see how support vector machines avoid overfitting. So the moral of the story is, even just the dot product SVM can be a very good thing to use if you're in very high dimension. And these days, big data, etc., high dimension is very common. Okay? So linear SVMs are widely used, and in particular for things like, say, text applications. Okay, but that's not very interesting. Let's look at a slightly more interesting one, and this is the polynomial kernel. Okay, the polynomial kernel is a very simple idea. I just take my dot product and I raise it to a power. Okay, now just taking the dot product and raising it to a power doesn't give me a complete full polynomial of that degree. In general, you might want to use that polynomial of any degree. But for our purposes, this is easier, and for many applications, it's enough. Okay, so a polynomial in general is literally any polynomial, but in particular, it can just be the dot product raised to some power. Okay, so very innocent thing that we did, but as we'll see, just by raising the dot product to some power d, which by the way is not the dimensionality of the data, it could just be 2, for example, is suddenly going to give us a lot of power that we didn't have before. Okay, and finally, what perhaps is the most widely used type of kernel is, again, a good old friend of ours, the Gaussian. Right, remember radial basis function networks? Right, we saw that radial basis function networks are both a kind of neural network and a kind of instance-based learning. Well, the SVM analog of radial basis function networks is Gaussian kernels. And for a lot of things, SVMs with Gaussian kernels are a better thing to use than radial basis function networks. RBF networks can be trained in a whole variety of ways, some of which for some problems are better than SVMs. But nevertheless, if I had to tell you which one should you try first, RBFs or Gaussian SVMs, I would say, well, this is Gaussian SVMs. They're easy to train and they'll probably do quite well. Right? In a way, a Gaussian is a very natural, similarity function to use, right? It just says, well, you're maximally similar if you're at the same place, and you have this nice bell-shaped, degradation of similarity as the two examples become more and more different, right? So what exactly is the Gaussian kernel? It's just the exponentiated norm, or Euclidean distance squared between the two examples, okay, divided by sigma, which is your kernel width. Okay, and this, guess what, is a parameter that you have to set by cross validation, and will make a lot of difference to whether you overfit or not, or underfit. Okay, so if sigma is very small, right, that means that even a small difference in your examples means the similarity is going to be very low, right? It means that your Gaussian is very narrow, right? A high value of the variance, right, means that you're allowed to vary a lot, means that the similarity decays only slowly with Euclidean distance, right? So you take Euclidean distance, you put it through this exponential, and you get the Gaussian kernel, okay? The Gaussian kernel is also cool because in this case, you are in infinite dimensions. Right, remember, this is actually a very strange statement to think about. Like, really, you're saying that this thing is equivalent to just doing some dot product of some features? Really? This is not obvious at all. Well, it is, but it's of an infinite number of features. Okay, and there's a fairly straightforward proof of that, but we're not going to worry about that here. Let us look at the simplest interesting case, which is polynomial kernels. Any questions so far? Okay, so let's look at, in particular at the simplest polynomial kernel, which is just the dot product squared. Okay, let's see how that works. And let's, as an example, right, this is going to illustrate why it is the case that a kernel can still be seen as just a dot product in a different feature space, and what power that gives us. So, let's suppose that I have two vectors. These are, two examples, right? They're one of them is u1, u2, and the other one is v1, v2, right? So these are just on the plane, right? Low dimensional, right? This is just a toy example, but it'll illustrate something important, right? So my example u is u1, u2, right? And my example v is v1, v2, okay? Well, now let's compute the kernel, over these two, right? It's going to be u dot product v squared, okay? So u dot product v is just u1, v1 plus u2, v2. You agree? Right? That's the definition of dot product. And now I square this, right? This is where my new extra power comes from. So what is this squared? Well, I get, u1 squared v1 squared plus u2 squared v2 squared plus 2u1 v1 u2 v2. Okay? Right? If you take this squared, you get this, so on and so forth, right? So this is just expanding the square. Okay? So now, this is the key step. It's going from here to here, right? This is so what is a dot product, right? It's a sum of products of corresponding terms, right? That's what a dot product is. So if we want to show that this is still a dot product of something, we have to reduce it to that form. Okay? Well, so let's do that, right? Well, I still have a sum of three things here, right? And the key thing is that I have to be able to split each of these things into a part that depends only on u, or a coordinate of u, right? Times a part that depends only on the corresponding coordinate of v. Right? So let's do that, right? Well, this guy here obviously is just a product of u1 squared and v1 squared, right? So the first component of my vector, right, is going to be u1 squared, right? And now here it's just the same thing for u2 and v2, right? So what I'm doing here is constructing my new feature representation of u and v, right? And so far all I've said is I'm going to replace u1 by u1 squared and u2 by u2 squared, right? I'm just squaring the coordinates. Nothing exciting happening here so far, right? I haven't gained any power with that, okay? But now comes the trick here and interesting part, right? What about this term, right? 2u1 v1 u2 v2, right? I can still squint at this and see here a product of two things, one of which has only to do with u and one of which has only to do with v, right? Namely, square root of 2 times u1 u2, right? Notice, I have here u1, u2, right? Those go to u, right? Go to the, feature vectors for u. Same thing for v, right? And now I have 2, right? But I need to split the 2 into things that are the same in both vectors, right? Well, that would be square root of 2, right? Because I'm going to multiply them, okay? So basically what I've shown here is that I can express this as a dot product of the following vectors. u1 squared, u2 squared, square root of 2u1, u2, and the same thing for v, okay? And you can certify yourself by doing the dot product of these two things, right? Well, this times this gives that, and so on and so forth. Okay? So, if I just call this guy phi of u, right? And the same thing for v, I've just shown that, u dot product v squared is really just a dot product of two different feature vectors for u and v. And you just need a recipe to compute the new feature vector from the old one. Now, in practice, in SVM algorithms, we're not going to bother to do that, right? Because, as I said, the feature vector might even be infinite in length, right? But the main point is that we know that this equivalence is there. So I can still apply to this all the math that I apply to dot products. Okay? And now you might ask yourself, okay, well, this is all very interesting, but what did I gain with this? And here's the amazing thing is that I've gained a huge amount. Because with u dot product v, all I could do was form linear frontiers, right? But now I have quadratic terms at my disposal. And in fact, with a full polynomial, I can have any polynomial expression. So before, let's suppose that this was my positive class, right? Well, I couldn't represent that. Now I can. A circle, well, it's a quadratic equation. I can implement it using this. Or a parabola, check. Or a hyperbola, check, right? Now I can represent quadratic frontiers. And, remember, this is in hyperspace, right? So, there were all these problems that, the perceptron couldn't do that just because of this, now it can. Okay? And if I go to higher order polynomials, I can represent, higher order curves and so on and so forth. So now instead of those jaggedy nearest neighbor frontiers, I can have very beautiful, smooth frontiers between positive and negative, right? It's much more aesthetically pleasing, right? There's these like Java applets on the web that you can play with that, they're so beautiful they'll bring a tear to your eye. Not ugly like, nearest neighbor or even decision trees. It's very nice. Okay. Of course, in some cases decision trees and nearest neighbor are still better, but nevertheless. Okay. The main point here is that this trick, the kernel trick, borrows a lot of power. Right? We can now we can now at least represent a lot of things that we couldn't before. And because we have a nice quadratic optimization problem, a lot of the time we are going to be able to learn that in practice, and we will see that starting at 8:13. Okay? All right. Okay. Let us continue. So, what we've done so far for support vector machines is the same thing that we've been doing all along for all the representations that we introduced. Is we saw what they are, and then we saw what they can and can't represent, right? And the news so far is pretty good, right? They're powerful. They can represent a lot of things, and create beautiful, smooth frontiers that separate the positive and negative examples nicely. And we're even going to be able to learn them, without local optima, right? We can learn a powerful representation without falling into local optima, right? This is, it's a good thing to have. And we're even going to have some sort of theoretical guarantees on how well they generalize, right? So this is all very nice. Of course, this will all work well if you have a good choice of kernel, but, there's no free lunch. Okay. You have a question?
Yeah. So irrespective of what kernel you use, you're guaranteed to have one global optimum?
Yes.
Okay.
Exactly. You pick, it has to be a kernel, right? So there's some certain benign properties that it has to satisfy. But at the end of the day, right, the whole idea here is that what we're going to be learning is just a good old hyperplane, right? So remember the whole, quadratic optimization problem that we looked at when we were looking at, doing gradient descent for the perceptron, right? The whole idea here is that it's still the same thing. Where we gain the power is that we are now doing this in a different space. Where, say, in addition to linear terms, I also have quadratic cross terms, right? I have x1 squared and x1, x2. So a hyperplane in this space could be a circle or a parabola or something complicated in the original space. But in this, transformed space, it's still just, all the linear problem and the quadratic function that you're optimizing. Okay. I haven't formulated the problem yet, but that's what we're going to do here next. But the answer to your question is yes. Yeah. It's a very good thing to have. It's even worth putting ourselves through some mathematical pain just to be able to have this. And if you like math, this is the greatest playground, right? There's another thing that happened in machine learning when support vector machines took off was that there was this influx of mathematically oriented people and unemployed physicists into the field. And, they brought some good things and maybe some, less good things, let's say. But anyway, so how do we learn SVMs? Right? That's the next question for us. Well, remember, an SVM is three things, right? It's a kernel, right? It's a set of examples, and it's a set of weights for the examples, okay? So, question one is, how do we choose the kernel? Well, there's a lot of actually literature on how to automatically, synthesize kernels from other kernels and figure out what the right kernel should be and whatnot. But, none of that truly works in practice yet or is widely used, right? And, even if it did, the bottom line here is black art. This is where you put, or, another way to to look at it is like, this is where the fun part is, right? This is where, you have something interesting to do, is figure out what is a good kernel for my problem. Okay? So that you will have to choose for yourself by being creative, by trying different things and so on. Okay? So let's suppose from now on that you have chosen a kernel. Let's say we're using a Gaussian kernel or, whatever your, choice of kernel for the problem is. The next question, of course, is how do I choose which examples are going to be support vectors and which ones are going to be forgotten, right? Having support vector machines is that you give me this huge training set, but hopefully then I just pick, a few hundred or a few thousand support vector machines, and those define my classifier, right? So the next question is, how do I choose those? Well, the happy answer to this question is that the choice of examples is going to fall out of learning the weights. So all we really have to worry about is learning the weights. And why is this going to happen? Because as we shall see, even though we're ostensibly learning weights on the features, right? This is a perceptron, right? There's this equivalence by which we're really learning weights on the examples. We saw an example of this, correspondence in the case of the perceptron, but we're going to talk more about it, shortly. But the bottom line is, when I learn my weights, basically the selected examples are just going to be the ones whose weight is greater than 0. Right? One of the big advantages of SVMs is that, or at least of the way of learning that we're going to look at, is that they tend to produce sparse models. Meaning, there's a tendency for a lot of, and we will see why, there's a tendency for a lot of the examples to wind up with 0 weight, meaning you can get rid of them. Okay? So, all we need is a way to choose the weights. And out of that will fall a choice of support vectors. Okay? So how do we choose the weights? Well, this is where the second important idea in SVMs comes along. We're going to do it by maximizing the margin. And interestingly, again, this notion of margin that we're going to introduce now, and then this, what we're going to focus on, it goes back, all the way to the 60s and to, people doing mathematical analysis of the perceptron and whatnot. But unfortunately, that only led to a practical algorithm, 20-something years later, okay? Or almost 30. Okay? So let's see what that idea is. And it's a very natural and intuitive idea. And it's the following. Let's go back to our, canonical example. So here I have a bunch of positive examples, okay? And here I have a bunch of negative examples, right? And let's think first of what the perceptron is going to do here, right? We're going to start with the perceptron, initialized to 0 or to some random weights, right? Then it's going to, incorrectly classify a lot of examples. And then as we iterate through the algorithm, that, hyperplane is going to move around, right? Until it settles in some position that separates the positive from the negative examples, assuming that that's possible. If it's not possible, then it's going to oscillate forever, right? And that's one of the, problems, okay? So let's suppose that, that frontier was, let's say, the following. Right, this works, right? And, the thing about the perceptron is that it doesn't care which hyperplane it chooses. As soon as it finds ones that works, right, there are no more errors, right, and it stops, right? But here's the question, right? What about this hyperplane? What about a hyperplane like this, right? This one works too, right? And with another run of the perceptron, maybe you would get the blue hyperplane instead of the red one. Okay? So here's my question to you. Which one do you, equipped with your super powerful visual system and human intuition, which one would you prefer? The red or the blue? The blue. Anybody want to say the red? Okay. Why the blue?
Got the largest margin around it.
Yeah, right. So you've even used the technical term. So to unpack that a little bit, right? What is going on here, right? The thing about what makes you feel more comfortable, what makes you feel safer with the blue hyperplane than the red one, right? Is that the red hyperplane passes pretty darn close to some of the instances, right? And on this training set, it's okay. It's still separating them. But remember, what we really care about is what's going to happen on future examples. And if there's a negative example here, right, in future it wouldn't surprise anybody if there was a negative example there, right, or even one there. And then the red hyperplane is getting it wrong. The blue hyperplane is getting it right, right? So the intuition here is, maybe we shouldn't just be looking for any hyperplane. Maybe we should look for a hyperplane that is as far as possible from all the examples, right? Because the farther it is, intuitively, the less likely that some wrong example will turn up in the future data. Okay? So the technical way of saying this is that we want the hyperplane with the maximum margin. The margin is the distance between is the straight line perpendicular distance between the hyperplane and each example. So for example, for the red hyperplane, right, the margin of this example is this length. Okay? The margin of this example is this length. Okay? And so forth. And same thing for the negative example. And what we want to do is we want to choose a hyperplane with the maximum margin. Hence this whole class of margin maximizing methods. And again, these ideas have been extended beyond support vector machines into other things. Right? So, what is my minimum margin here? Right? Well, my minimum margin among the red examples is this margin, right? It's not so great. Right? We want to make this bigger. And my minimum margin among the negative examples is, let me see, it's this one here, right? So of all of these, the smallest is this one, right? So we would like to swing this hyperplane away from that example to make that as large as possible while not making anything else smaller, right? So that means we want to swing it towards where the blue one is, right? We want to move it away, right? We want to swing it like this, right? To move it farther away from these examples. Notice that we have a lot of room for maneuver around here, right? And likewise, we want to swing this guy over there. Let me erase those little test examples that I just made up here, right? So that we just have, so that we just have the training set. Now from the margins, I have to infer the hyperplane. Interesting exercise, right? So let's see here, right? So here's my hyperplane, right? More or less. Okay. So I want to swing the hyperplane this way and that way, right? I don't just in this case I don't just want to shift. I want there's a lot of room, to make it closer to the negative examples here, right? The basic idea is that I can keep swinging it until some other margins becomes the lowest one, right? I don't want to swing this so far that it becomes close to this example or this example, right? Likewise, I can swing this guy a pretty good distance before it starts to get too close to that example, right? So, moral of the story. I don't just want to learn any hyperplane. I want to learn a margin maximizing hyperplane. Okay? So this is what we're going to try to do here. Okay?
Is there any relationship between margin and variance? Like as we are maximizing margin, is that?
There is a relationship, but it's a somewhat indirect one. The relationship is the following, right? As we shall see, a larger margin hyperplane has lower VC dimension, and therefore it has lower variance. Now here's a more intuitive way to look at that, right? And we're going to look at this a little bit more towards the end, but here's one way to look at this, right? You can think don't think of a large margin hyperplane. Think of, instead of a plane, what you're putting there is a slab, right? It's not just this, remember a plane is infinitely thin, right? It's this, abstraction, right? But let's suppose that my plane actually had finite thickness, right? And now a large margin hyperplane is one that can be very thick and still not touch any of the examples, right? The red hyperplane, if I start making it thicker, it immediately touches an example, right? Whereas the blue one, I can make it very thick before it touches an example, right? So in some sense, the margin, or twice the margin, is the thickness of my, slab, okay? And now if you think about it, if I have a thick slab, I have fewer ways of laying it on the plane between the examples than if it was thin. Right? This is actually the key thing. This is why the variance is going to be low, and this is why the VC dimension is going to be low, right? Which is kind of, at some level, saying the same thing in different ways, right? Notice that if I only require a very small margin, right, I have a lot of hyperplanes, right? If I require a very large margin, then there aren't that many hyperplanes that I can have. In fact, if I maximize the margin, typically there's only going to be one max margin hyperplane, meaning any little swing of it, and I overtake an example, Okay? In fact, if you can still swing your thick slab without pumping an example, well, make it thicker. Right? Swing it until you're at that point. Okay? So if you think of, like my hypothesis space as not just being hyperplanes, but being thick hyperplanes, right? Then, the class of thicker hyperplanes has a harder time shattering instances than the class of thin hyperplanes. Okay? Questions? All right. So, let us maximize the margin. So here's our problem. First of all, let's define the margin. The margin, and remember, what I want to do is maximize the minimum margin, right? There's going to be a lot of very large margins that I don't have to worry about. So, my margin of the whole hyperplane for that training set is going to be the minimum of the product of the class and the dot product of the weight in the instance, right? Remember that this product of the class and the dot product of the weight in the instance is what, the perceptron was dealing with all along, right? Except that now we're going to look at this and say like, I don't just want this to be above 0. Right? This is the thing. First of all, I want this to be positive, right? Because that means that y and the output of the perceptron have the same sign, right? If y is negative, I want w dot product x to be negative as well, right? So that they're the same and similarly for positive, right? What I don't want them is to have opposite signs. This is what the perceptron algorithm wanted. In SVMs, we're going to want more than that. We're not just going to require that this product to be positive. We want it to be large, right? The larger it is, the safer we feel, because the farther it is from becoming negative, right? So that's what maximizing the margin is. Okay, so we're going to define as the margin the minimum of y times the dot product, right? Minimum over all the instances in the training set. Okay? So that's my definition of margin. Okay? And I just said, well, we want to maximize the margin, right? Well, if you look at this expression, right? Let me erase these scribblings. Wait. Right? There's a very easy way to maximize the margin, right? How do I pick weights to maximize the margin here? In fact, I can even make this margin infinite with no trouble at all. How do I do that?
Pick a large weight.
Yeah, exactly, right. The margin is proportional to the weights, right? So jack up the weights, right? If I make all the weights infinity, then my margin is infinite. Moral of the story. The margin by itself doesn't really mean anything, right? It's the margin in relation to the weights, okay? So, one thing that I could do, right, is fix the weights and maximize the margin, right? But that's not the most convenient thing to do, right? The most convenient thing to do is fix the margin, right? Let's just say the margin for everybody is going to have to be 1, right? And now I minimize the weights, right? This at first might appear a little intuitive, but remember, right? Fixing the margin and minimizing the weights is really just the same thing as fixing the weights and then maximizing the margin. Okay? You agree? If you think about this geometrically as opposed to algebraically, it's very clear what it is that you need happen, right? But to go back to this picture, right? I could make the margin large just by increasing the size of the figure, right? But that doesn't accomplish anything, right? So one thing that I can do is I can basically fix the size of the figure and then maximize the margin, right? But that would mean holding the weights constant, and that's, we want to be learning the weights, right? The other thing that we can do is I'm going to say, I'm going to require that the margin be 1, right? I can require anything, but let's just make it 1, right? You can make it 2 if you wanted, but let's make it 1. And then I'm going to try to make the weights as small as possible, which means I want to shrink the figure, right? So if I shrink the figure while keeping the margin at 1, geometrically the margin has been getting larger, right? You agree? There's this notion of the geometric margin and whatnot, but we don't need to formally define that, right? We're just going to do things this way, okay? So we're going to fix the margin and minimize the weights, okay? So I want to minimize the norm of the weight vector, right? Which is just w dot product itself, right? Like minimizing, this squared or not squared doesn't really matter, right? So the Euclidean norm would be the square root of this, but let's not worry about that, right? I'm minimizing it, okay? Subject to the margin, right, which is this, being greater than 1 for all examples, right? So for all examples, the class of the example, which remember is +1 or -1, times the dot product of the example with the weight vector has to be at least 1. Right? So this is the problem that we're now solving, is we're trying to minimize the size of the weight vector, or the norm of the weight vector, subject to all the margins being 1. Okay? Everybody agree? So this is the problem that we have to solve. Right? So notice, we've picked a representation, right? Support vector machines. We have now picked an evaluation, right? The evaluation function that we're using here is the margin of the vectors with, the size of the weights, sort of like as a counterpart to that, right? What remains now is to figure out, how to solve the optimization problem, right? Which is, well, how do you find the weights that minimize this subject to this constraint? And this is where you'll notice that we have a new type of problem here that we don't know how to solve yet, right? If all that we had to do was, minimize, W dot product itself, well, we know how to do that. But we're minimizing it subject to these, inequalities, right? This is now constrained optimization because I'm trying to optimize a function, but it's under some restrictions. Okay? So now is where we take a little break from machine learning and do 15 minutes of, 101, tutorial on constrained optimization. Okay? How many of you here have heard of constrained optimization, Lagrange multipliers, things like that? Raise your hand. Okay, one. And nobody remotely. Okay, so...
Not Lagrange multipliers.
Okay, so, very good. So you'll probably recognize some of what we're going to see here. But the good news for the rest of you is you're not expected to know any of that at this point. We're going to introduce it now. Okay? We're going to just cover the basics and try to keep things simple and intuitive. Ask questions if you have them at any point. And then we will go back to using that to solve SVMs, which, at some level will be very straightforward. Okay? So, constrained optimization. Okay? So let us actually start with a slightly simple... Notice that here I'm trying to minimize my function subject to these inequalities. Right? Let us first start with the classical Lagrangian case. This goes back to Monsieur Lagrange, who was actually Italian, but never mind. Despite the French name. He lived in France and they Frenchified his name. But he invented a very, he had a very clever idea, which we're going to see shortly. But it was only for solving optimization problems subject to equality constraints. Okay? So let us first solve the equality case. And this is something that, a lot of people, not in computer science, but in things like EE and, whatnot, they see this in college, right? The method of Lagrange multipliers. But then we're going to need more than that. We're going to need to deal with inequalities. So let's do the equalities first, and then go on to inequalities. Okay? So this is the problem that we have to solve. We want to minimize some function f of w subject to a set of constraints hi of w is equal to 0. Right? Hi is any function. I just have a whole bunch of these, right? Each one of them is a constraint, and I can always express the constraint as some function being equal to 0, right? Notice, for example, that there's a case of this that you probably already know, which is what? What's a very common special case of this? Is when the constraints have what form, and the function has what form? Let's suppose that the constraints are all linear, right? Simplest case is always the linear case, right? If the constraints are all linear and the function that I'm trying to optimize is linear, what is this? Linear programming, right? So linear programming is a set of techniques for solving a special case of this. But we're going to be interested in a more general case in particular, right? We're actually going to have linear constraints, but the function that we're optimizing, you will notice, is actually quadratic. Right? So we can't use linear programming. This is actually what's called quadratic programming. Okay? Or at least the particular case that's going to be relevant for us. Okay? So, how do we solve this problem? Right? Well, here's one thing that might come to mind, right? Well, these are equations, right? They basically mean that, my space of solutions is smaller, right? So if I have these equations, let me take some of my variables, right? Express them as function of the others, by solving the equations, right? Let's suppose that I had a problem over, variables x1 and x2, right? If I have a constraint over them, right, that means that I'm no longer on the plane, I'm on a straight line, right? So I can express x1 as, ax2 plus b, right? And now I just have a problem in x1, right? So you could, naively say, well, the constraint optimization problem is not a big deal, right? I find expressions for some of the variables as a function of the others based on the constraints, and then I just solve an unconstrained optimization problem, right? Did everybody get this idea? The problem with this is that it gets very complicated very quickly, right? Especially since these equations could be nonlinear and whatnot, right? So most of the time, this is not a very good idea. You could try it, but most of the time, it's going to be very difficult. Unfortunately, Monsieur Lagrange had a much better idea. So let's look at what that idea is. And in fact, let's illustrate this with a nice little example on the plane. Nothing like a simple example to hopefully make things clear. Let's suppose for just a moment that I just want to minimize the function x1 squared plus x2 squared. Okay, with no constraints. Okay, just in 2 dimensions. Okay, let's draw a little diagram of that here. Okay. So here's x1, and here's x2, right? And let me draw contours of constant value of the function, right? What are they going to be? What's their shape going to be? They're going to be circles, right? So it's going to be a bunch of circles like this, right? So this, for example, is x1 plus x1 squared plus x2 squared equals to 1, and then this is equals to 2, and equal to 3, right? And so forth, okay? So what is the solution to this problem? What is the x1, x2 that minimizes x1 squared plus x2 squared? Just by looking at it. 0, 0, right? The solution is the origin, right? I said I was going to make it simple. Okay. Now this problem can be solved by inspection, as they say, right? But in general, how do you solve problems like this? It's like we saw when we were looking at neural networks, right? Is by forming the gradient, right? The derivative of the function with respect to x1 and x2, right? And then equating to 0 and solving, right? In this case, it's very simple, right? Because the derivative of x1 is just 2x1, right? And then I equate that to 0, and I get x1 equals 0, right? So this unconstrained optimization problem is as easy as they get, right? But now let's look at the constraint case, right? So let's say that my constraints are that x1 and x2 have to be such that x1 plus x2 is equal to 1, right? So this is my constraint. And what this constraint means is that I can't just go, optimize this function any way that I want. I have to stay on that line. That's the key, right? Notice the line is a lower dimensional space compared to the plane, right? I've lost degrees of freedom. In particular, let's suppose that, this was x1 over here, and this was 1.5, and so on, right? So let me try to draw this, right? Here's my line, right? Forgive my poor drawing skills, right? So, but this here is x2 equal to 1, and this here is x1 equal to 1, okay? So the problem here is that I'm trying to minimize this function that is given by these contours, right? While staying on that line. Okay? So now I can't wander all over the plane anymore. I have to stay on this line. Basically, all I can do is go up and down this line. Okay? So now, where is the minimum going to be, roughly speaking?
45 degrees.
Yeah. It's going to be here, right? You see why? The way to think about this is like picture yourself on that line, right? Think of this as like it's like a road. You can only go on that road, and there's a function, right? The function is defined on the road and all its surroundings, right? Picture like one of these straight roads in a completely flat desert, like you often see in Hollywood movies, right? Somewhere in Arizona or something, right? And you go down that road, right? And this function has values all over the map, right? And maybe its minimum is over there, but you can't get off the road. You have to stay on the road. So all that you can do is drive down that road until you find the minimum that's on the road and stop there, right? So what happens when you do that, right? What I'm doing is I'm going along here, right? Well, the function is going down, right? You agree? It's going down, it's going down, it's going down. Now is it going down or up? Now it has started to go up, right? So my problem is that I want to find this point over here, right? That's the problem. I'm no longer looking for this point, I'm looking for this point. And so the question for us is, how do we find that point, right? Well, let's see. What is it that characterizes this point, right? If you think about it, what characterizes, this is really the key idea behind Lagrange multipliers, is before we get into the math, is what characterizes this point, if you think about it, is that the gradient of the function is perpendicular to my constraint line at that point, right? You see why? Right? Remember, this function is defined in the whole plane, right? And it has a gradient everywhere, right? What happens if the gradient is not perpendicular to the line? It means that it has a component along the line, right? Well, that means that I can keep walking along the line and make my function smaller, right? So it has to be that the point at which I stop is the point at which the gradient of the function is perpendicular to the line, which means that in order to use gradient descent and keep making the function smaller, I would have to get off the road, but I'm not going to do that. Okay? Everybody see this? Okay, so now here's the next key step, is that how do I get from one to the other, right? So basically what happens is that I want to find a solution that makes this projection be zero, right? So if you think about it, what happens is that let's think of the gradient in some, arbitrary position, like for example here, right? The gradient, right, is actually pointing, partly along the line and partly off it, right? You can decompose into this diagonal and perpendicular component, right? Now if you think about it, I want to get from this to the part that I care about, which is the part that's going along the line, right? And the way I project this gradient onto this gradient is by, I project this line onto this line is by adding a vector in this direction. Right? Let me try another color here, right? Is by adding a vector in this direction, right? Adding that vector swings me from a bad direction to a good one, right? And it's when this vector, and I know, this is the key, I know that at the solution, this vector has become zero. Okay? So, to put that in math, right? This is where Lagrange had his beautiful idea, right? What's going to happen is that at the solution, so let's call W star my solution, okay? At the solution, now let's do this in many dimensions. Right? We will come back to this example shortly and solve it using Lagrange multipliers, but now let's look at the definitions, right? At the solution W star, I'm going to use star to always represent the solution to the constraint optimization problem. The gradient of my function, right, which is now in many dimensions and there's many constraints, right? Hi, where I could be 1, 2, 3, 4, 5, right? This gradient, it must lie in the subspace spanned by the gradient with respect to each of the functions, right? It has to be a linear combination of them, right? It has to be in that plane such that it's perpendicular to my constraint surface, okay? This is the key thing, okay? So, this is what we're looking for, right? So, Lagrange's idea is, well, let us define a new function that we can optimize that will guarantee that that's what we found. So, the whole idea of Lagrange multipliers is very clever. It's like, I'm going to turn a constrained optimization problem into an unconstrained one by adding something to the function. Right? This is a nice thing to have, right? It's much, much easier than doing a lot of complicated equation solving and substituting into the original problem and then getting a very complicated function and trying to optimize that, right? So this is what's called the Lagrangian function. The Lagrangian function, usually denoted by L, is going to be a function of two things: the weights, right, in our case, or the whatever we're trying to optimize over, right, plus a new set of variables, the betas, that are the Lagrange multipliers, right, the famous Lagrange multipliers. Usually, lambda is used for Lagrange multipliers, but in support vector machines, people use beta, right, because we're going to use alpha for something else, and then there's going to be alpha and beta, right? So, and the idea is that by optimizing this new function, we guarantee that we're finding the optimum of the constraint function. Okay? So what is the new function? It's just the old function plus a linear combination of the constraint functions. Because we know that the solution is in a subspace spanned by these, right? So, right, we're going to have to find the minimum of this function with respect to this and this set of directions. Okay? So, another way to look at this, which I do not encourage, but often I think is what people do in practice, is you can just think of this as a very simple recipe, right? Irrespective of sort of like the geometric intuition, the recipe is very, very simple. It's What do you do when you have a constraint optimization problem is you take each of these, multiply it by a beta, add that to the original function, and now just do your good old, unconstrained optimization. Okay? Questions so far? So basically, finally what we're going to solve is this problem, right? I want to find the W star and beta star that make the gradient of the Lagrangian equal to 0. Okay? So this is just the good old unconstrained problem, except it's over, the old n variables, and the function has this, new term in it. Okay? Questions? Okay, this is still probably, kind of nebulous, so let's continue with our example, right? So let us solve this example using the method of Lagrange multipliers, right? So how does it go? Well, let us first of all form our Lagrangian function, right? So what's our Lagrangian going to be? Well, it's going to start with the original function, right? x1 squared plus x2 squared plus what? Well, first of all, how many constraints are there in this problem? Just one, right? It's this here, right? There's only one h1, right? And remember, the idea is that the constraint has to be in the form something equal to 0, right? So how do I put this in that form? It's going to be what?
-1.
Right, x1 plus x2 minus 1 equal to 0, right? So this is my h, right? Another recipe, right, is that the Lagrangian, right, I'm going to have the Lagrangian multiplier, let's call it lambda, in keeping with tradition. The Lagrangian multiplier times this, right, gets added to the function, right? So what did the recipe do here, right? Let's go back to our little diagram. Like, what this condition doing here is encoding the fact that my gradient is going to have to be perpendicular to this surface at the solution. Surface, which in this case is just a straight line. Okay? So that's what that's doing. Okay? All right, this thing is going to ensure that I find this solution and not this solution. Okay? All right, so now this is my Lagrangian, right? And now we can just do unconstrained optimization, right? So but now remember, now I have three variables, right, that I'm dealing with, right? So I need to find the 0 of the gradient with respect to all three of them, right? So what's the derivative of L with respect to x1?
2x1 plus lambda.
2x1 plus lambda. You agree? Right? There's 2 coming from the 2x1 comes from the quadratic term, but now there's the lambda, right? That's why this is going to be different, right? And we want this to be equal to 0, right? Remember? This is how I find the minimum, is we equate all components of the gradient to 0, right? Just as we were doing for, perceptron, right? So 2x1 plus lambda has to be equal to 0. Same thing for x2, right? This thing is completely, symmetric in x1 and x2, right? 2x2 plus lambda is equal to 0, right? Right, this is pretty intuitive so far, right? And now what is the final condition, right? Is that the derivative of L with respect to lambda also has to be 0, right? What is the derivative of L with respect to lambda?
x1 plus x2 minus 1.
x1 plus x2 minus 1, right? It's just this expression that we had here, right? So, surprise, surprise, right? This is making a lot of sense, right? What zeroing out the derivative of the objective function with respect to the Lagrange multiplier does is just, restates the constraint that we started out with. Okay? Very good. And now, what we have here is a system of equations, right? We can solve that system of equations. It's clearly, this is not a very hard one, right? In general, you could be solving monstrous systems, but this one here, we can do by eye, right? And what do we get? We get that, x1 and x2 are both equal to a half, right? Which, if my drawing was better, would also be, obvious from looking at the graph, right? So if you think about the fact that you're at 1, 0 here, right? And sorry, you're at 0, 1 here, and you're 1, 0 here, right? It makes sense that this is at half, half, okay? So that's my solution. And by the way, lambda is equal to minus 1. But we don't care. Actually, we don't care about lambda, so in fact, one of the ways of solving this, right, is we get rid of the lambdas, and then we just solve the resulting equation in the resulting problem in the x's. In fact, Lagrange multipliers are sometimes called silent multipliers, because they're a little bit like the dummy variables in summations and whatnot. We don't care about them. On the other hand, and in complete contradiction with what I just said, sometimes the lambdas are exactly what we want to focus on. right? In fact, when it comes to solving this problem, you have two choices. Get rid of the lambdas and solve it over x. This is often called the primal problem. But you can also do the opposite. You can get rid of the x's and solve the problem with the lambdas. And this is called the dual problem. People in optimization are always going on about primal and dual, right? That's what the dual is. The problem is the same, but you're solving it over the so-called dual variables, which are the Lagrange multipliers that you've introduced. Okay? And sometimes that's easier. In particular, for support vector machines, that's going to be easier. And also, it's going to have a very intuitive meaning, right? So what would that mean here, right? What that would mean here is that I would have to express x1 and x2 as functions of lambda, right? Which is easy, right? What is x1 as a function of lambda? If 2x1 plus lambda is equal to 0, then x1 is equal to minus lambda over 2, right? Everybody agree? And the same thing for x2, right? Right? And now I can take these guys, right, and replace them into my Lagrangian, right? And then I have a Lagrangian that's only over lambda. In this case, it's actually clear that it's going to be easier because, it's going to be a function of only one variable and so on and so forth, right? So what is the Lagrangian that I get when I do this replacement? I get minus, to skip a couple steps of this math, right? I get, that the new L, right, as a function of lambda is minus lambda squared minus lambda. Okay? And now, right, this is just now an unconstrained optimization problem only over lambda. This is my dual. Okay? And now I solve it. I equate its derivative to 0, right? So what that means that, minus lambda minus 1 is equal to 0, right? You agree? Right? The derivative of minus lambda squared over 2 is 1, right? So this means that what? That lambda is equal to minus 1, right? And then from that, I immediately get that x1 and x2 are a half, because I knew what they are as a function of lambda. So I can solve this in the primal, and I can solve it in the dual. Okay? Question? We've actually illustrated a lot of stuff about constraint optimization in just these, 10, 15 minutes. Okay? Everybody happy, or anybody have doubts about constraint optimization? By the way, at the end of the day, right, you learn these, Lagrange multiplier things in school, but that's, at the end of the day, your solver, right, is going to do, its thing, right? And often it does not involve Lagrange multipliers. Nevertheless, the Lagrange multipliers are very useful for formulating the problem. And for things like, the solver is probably not going to be doing things the way we've done in this little example here, right? We will see in just a second what we might do for support vector machines. But nevertheless, this notion that you could go to this dual problem is potentially very powerful. Because in some cases, the dual problem is easy to formulate and it's much, much easier to solve. Okay? So always bear that in mind. Okay? Any questions? All right. Very good. So, that was our introduction to constraint optimization. And at this level of abstraction, we now have what we need to go forward, right? We know how to solve these constraint optimization problems, right? What does this mean for support vector machines? Okay, remember, the reason we went into this is that we wanted to solve this problem, right? Minimizing the norm of the weight vector subject to all the margins being at least 1. Okay, so what does constraint optimization and Lagrange multipliers and primal do? What does all of that mean applied to support vector machines? It actually means something very interesting. Here's what happens. Remember, my primal problem is over W, right, which are feature weights, right? Remember, this is a glorified perceptron with a kernel instead of a dot product, but these are weights on the features, right? So this is the primal problem that I'm trying to solve, right? I'm trying to find the optimal weights for the features, but wait, isn't the support vector machine weights over the examples? Yes. You know where those weights over the examples come from? They're the dual variables. Aha. Again, I'm not going to prove that here, but hopefully this, this has some intuitive value, right? What happens in the SVM is that my betas, my Lagrange multipliers, are my instance weights. This is why we can be simultaneously solving this problem of finding optimal weights for the features and optimal weights for the instances, because they're really the primary, they're duals of each other, these two problems. And in particular, it's, you can use, there's both classes of methods, but often for support vector machines, typically people use, the dual formulation. Okay? Questions? So, the feature weights, right, are my, the example weights, right? Those are my dual variables. And just as a preview of what's going to happen, the reason I'm going to wind up with a sparse solution, right, is that a lot of the dual variables are going to be zero. Okay? This is, remember, right? I said that only on a good day, only a small fraction of the examples will be chosen as support vectors, right? In optimization terms, what that means is that when I solve my dual problem, right, that dual problem, the solution to that dual problem is going to have a lot of zeros. A lot of the betas are going to be zero, okay, or alphas, as we see shortly. Okay. So, but there's a very big, detail still missing here, which is what? We're actually not done yet, right? Because, remember, let me erase this stuff. What I have here was a bunch of inequality constraints, right? But what we just saw how to solve was problems with equality constraints. Aha. So we still got something to deal with here. So now let's deal with that, right? And now I'm going to gloss things over a little bit more. The method of Lagrange multipliers is very old. It's, 200 or 300 years old. Surprisingly, the extension of that to inequality constraints was only done in the 20th century by these people called Karush, Kuhn, and Tucker. So let's see how that works, right? And actually, in terms of the basic intuitions, we actually can still pretty well understand what's going on. So here's how things work, right? Our new problem, right? So this is part 2 of our, constraint optimization intro, is I still want to minimize my f of w, right? But now I have 2 types of constraints. I have equality constraints, as before, my h's, but now I also have inequality constraints, which I'm going to call g's, right? So g1, 2, 3, 4 are going to be inequalities, right? And in fact, in our problem, we don't even have equality constraints. So, let's just look at the general case, okay? So, I am still going to have my good old Lagrange multipliers for the inequality, my good old Lagrange multipliers for the equalities. Those are going to be my betas, right? But now I also need Lagrange multipliers for the inequalities, and I'm going to call those my alphas, okay? So, here's what we want, right? And these are known as the KKT conditions. When you hear people talking about, how to solve the SVR problem, you hear KKT this and KKT that a lot. So, these conditions are the conditions that characterize my solution, right? Just like I had, conditions that characterize my solution in the case of Lagrange, of just having. Let me see here. Again, let me erase this, right? My condition, right, was that the gradient of this function had to be equal to 0, right? This is what defined my solution, okay? That the gradient of the Lagrangian was going to be 0, right? Another question is what does the job of that, right? And then what we found was a set of weights that satisfy those conditions, right? So now what are those conditions, right? Well, they're a little more complicated. They're called the KKT conditions after Karush, Kuhn, and Tucker, right? The first one is still, it's the natural one. It just says that the gradient of my Lagrangian, which is now a function of 3 things, my original variables, and my Lagrange multipliers for the inequalities and the equalities, right? This has to be 0, right? So no big deal so far, right? This is fairly intuitive. All of these guys have to be non-negative as before. These guys all have to be less than 0, but this is really just repeating my definition of the problem, right? That the g's all have to be less than 0, right? I'm arbitrarily picking them to be less than 0 because it's more convenient. So nothing very surprising or very interesting so far. But here comes the really crucial part. It's this one. Actually, let me not even put a border around this one. Right? This is the key one. This is called the KKT complementary condition or conditions because it's usually a whole bunch of them. And notice what this is saying. It's actually going to make a lot of intuitive sense. This is something surprising, right? It's not something that, the others were kind of the obvious, but this one is not. It says that for each G, for each inequality constraint, the product of alpha of the corresponding multiplier times G is going to be 0, equal to 0. Why are they called complementarity conditions? Because these two things are complementary. The alpha and the g are complementary, meaning that one of them has to be 0. We know that at the solution, either the function is 0 or the multiplier is 0. Okay? Now, why is that the case? Right? Let's think about this graphically, right? So let me do a different illustration now. Let's suppose that I'm trying to solve my problem within this region, right? I'm trying to maximize, or let's say minimize my function as before, right? You get the idea. But now I have inequality constraints, right? As in linear programming, right? So now I want to find my optimum. This is a boring case because the optimum is actually in the middle there, but nevertheless, right? Subject to say, being higher than this, lower than this, and higher than this, right? I have these 4 linear constraints that define a region, right, where I have to solve my problem. Okay? Everybody got this? Okay, now notice what's going to happen. This is the crucial thing. For each constraint, one of two things is going to happen. And actually, let me illustrate the two cases, if I can somehow draw this well enough, as follows, right? Let's say in one case this was the constraints, and in another case the constraints were, say, like this. Okay? Right, so same objective function, x1 squared plus x2 squared, right? The norm of the vector, right? Now one of two things is going to happen for each constraint. One is, and remember the constraints are these straight lines. One of the things that can happen is that constraint doesn't affect us, because I can satisfy the constraint while having my optimal solution. In particular, in this case, which I accidentally turns out to be very convenient, right? Even though I didn't draw it with that in mind, maybe in the future I will, right? All the constraints are inactive. This is really what the KKT complementarity conditions are about. They're about which constraints are active and inactive. What does it mean that the constraints are active? Is that they don't affect the solution, right? Notice that in this case, right, my solution is exactly the same as it was when I had no constraints, right? Which means that I can get rid of the constraints, right? I don't need them, which means I can make their alphas equal to 0, right? Ignore them. Life is good. Now, of course, what's going to happen more often, right, is that some of the constraints are active, meaning that they are the constraints that we're bouncing against. And remember, we're in very high dimensions with a lot of constraints. The constraints that are active are the ones that oh, there's my optimum over there. I want to get to that optimum, and then I bump into this wall, right? These are the constraints that are active. So, for example, in this figure here, right, this constraint is not active, right? Actually, let me do this. In blue are inactive constraints, right? And remember, each of these constraints is a whole line, right? These blue lines are not changing where my solution is going to be, right? So those are inactive. Their alphas, their multipliers are still going to be 0, right? But now, bummer, there's this one. This one is definitely active, right? Because what I wanted to do was walk this way until I got to there. But that one's preventing me from getting there, right? So this constraint is active, right? Everybody see this? Now, mathematically, what characterizes a constraint being active, right? It's that I am on the line defined by the constraint, right? My constraint was that g had to be less than 0, but on this line, g is equal to 0, okay? You see what I'm suggesting here? So here's the following very interesting thing that happens. This whole complicated problem, we've got lots of inequalities. At the end of the day, it just becomes a good old problem with only equalities. Because for each inequality, either it goes away because it's not active, or it becomes an equality because I'm bumping against the constraint, meaning that the equation is satisfied, right? So, let's say that this was my g1, right? And my constraint was that, g1 of x1, x2 is less than 0, right? What happens here is that g1 is equal to 0, okay? So the bottom line here is that solving this problem with equalities and inequalities is just the same thing as solving a problem where actually, this problem that I have here has no equalities, right? It's the function and these 4 inequalities, right? And what I'm saying is that solving the problem with these 4 inequalities is the same thing as solving a problem where 3 of them I just completely ignored, and 1 of them became an equality. Right? So, one way to look at this is, I can solve this by figuring out which ones I can ignore, and then I treat the remaining ones as equalities, and then I'm back to my good old, Lagrange multiplier problem with only equality constraints. Okay? Everybody follow this? Okay, now, what does this mean for support vector machines? What are the walls that I bump against? What in the case of support vector machines is an active versus an inactive constraint? This is really what it all boils down to. Remember, my constraints, right, were that the margin of each example has to be at least 1, right? And I said that my dual variables were going to be the example weights. Okay? And remember, the example weights are these alphas, right? So what is my support vector machine going to be? Right? Some constraints are going to be inactive, and some constraints are going to be active, right? What are the active versus inactive constraints? Oh, I don't have that anymore. Give me just a second here. Let's look at this figure. So here's my, my dotted line is what used to be my red line, right? So this is my bad hyperplane, right? This is my good hyperplane, right? And the dotted lines are this is, think of this, the distance between these 2 dotted lines as the thickness of the slab, right? So what are my active and inactive constraints? Anybody care to guess?
The 3 that are on your margin lines?
Exactly. The active constraints, right, are the margins of the examples that have the minimum margin. They're these guys. These are the guys that I'm bumping into as I try to swing my hyperplane. Right? I can't move anymore in this direction because that would violate the margin constraints for this positive example. Okay? So the support vectors are the ones whose margin constraints are active. They're the ones whose weights are non-zero. These guys over here, who cares? I could put them somewhere else as long as it's not inside the slab. I could, make them disappear. The solution isn't going to change. Right? So this whole idea of the dual problem and the dual variables is actually very, meaningful in the case of support vector machines, right? The dual variables are just the weights of my examples, and the reason why I'm going to get a sparse solution is actually something that we had already seen when we talked about nearest neighbors, that most of the time, most of the examples are not going to, have any role in defining the frontier. Right? I could get rid of all of them and focus only on the ones that really make a difference. And those are the ones with active constraints. Those are the ones with non-zero weights. Okay? Questions? Those are the support vectors. And this is a support vector machine. Right? Notice that if for example, I got rid of this negative example, right? Then my max margin upper plane would basically fall down like this, right? It would swing. So it's these guys that are holding it in place. These are the ones that are supporting the hyperplane, and that's why they call support vectors. Questions? So, in your daily life, you're probably not going to have to worry a lot about constraint optimization, provided you're using an SVM package. But you do very much need to understand that this is what's going on. Right? This is what's happening. When you get a bunch of support vectors out, you know what those support vectors are. They're the ones that are basically, that have the least margin and that you can't move, or the hyperplane would change. Okay. Now here's a question to test your deep understanding of machine learning. What is going to happen to the number of support vectors as the dimensionality of my space goes up? If you can't answer this question, don't worry, it's late in the day, and this is not a trivial question. But if you can answer this question, kudos to you. You're really ready to get 4.0 in this course. Right. Let me give you a hint. Remember when we talked about instance-based learning? And by the way, the answer is not overfitting. Right? But remember that when we talked about instance-based learning, we saw this very big problem, which was what? The second biggest problem in machine learning after overfitting.
Curse of dimensionality.
The curse of dimensionality, exactly. So where does that come into here, right? So far, we seem to be doing all these things where we're not affected by the dimensionality, right? But we know that, that sounds a little suspicious, right? Because the curse of dimensionality always kills you in the end. So my question to you, right, slightly more concrete than before, is how is the curse of dimensionality going to hit us here? And what does that have to do with the number of support vectors?
The number goes up.
It goes up. Why does it go up?
There are more axes that you can rotate on when you're swaying.
Yeah, exactly, right? The more dimensions you have, the more support vectors you need, right? And now you might think, well, does it just go up linearly with the number of axes? Well, no, right? You need examples to define in hyperspace where this plane is going to be, right? So, unfortunately, what's going to happen is that in low dimensions, as long as the problem is, decently learnable problem, you can have a support vector machine with a small fraction of support vectors, let's say, 1%. But once the dimension starts to get to something respectable, like say 100 or 1,000, you will probably find that your number of support vectors has risen to 20%, 30%, maybe even 70 or 80%. At which point your support vector machine is not looking so clever, at least from the point of view of scalability, right? You didn't throw away that many instances. You have like this heavy thing to move now. And as usual, there's ways to combat that, but it's good to remember things that way. Here's another way to look at this. Remember all these examples that we saw, those strange things that happen in high dimensions? One of which is all the examples start to be near the frontier, right? Remember the hypercube, and in high dimensions all the examples are near the wall of the hypercube? Well, the same thing happens with the frontier, right? The support vectors, right, the minimum margin examples are the ones that are very near the frontier. And guess what? In high dimensions, they're all near the frontier. Bummer. Okay? So this big mass of stuff that you can get rid of in these like little 2-3D illustrations, in high dimensions, often that big mass isn't, has gone away because somehow in that high dimensional space, in one way or another, every example is not too far away from the frontier. And as we're going to see, this is also going to affect the kind of generalization guarantees that we can get. Okay, but in the meantime, let's see where we are right now, right? So we figured out in general how to learn support vector machines. It's a quadratic programming problem, right? It's got, these inequality constraints, and it's got this quadratic objective, which is just the norm of the weight vector. We can just use an off-the-shelf quadratic programming solver for this, right? I mean, there's people in, applied math and operations research that do nothing but come up with better mathematical programming techniques, right? This is a very, a very unfortunate overload of the term programming, right? Linear programming, quadratic programming, mathematical programming, they're really not programming in the modern sense, right? They're just optimization. But nevertheless, there's things like this that are just, available. Some of them open source, right? And indeed, this is what people first did, right? Is they formulated their learning problem, and then they threw this into a quadratic solver. The problem with that, as is usually the case in machine learning, is that just using the off-the-shelf optimization solution doesn't get you very far. In particular, think of doing a support vector machine with 1 million examples. This is doing a problem with 1 million constraints. Even for state-of-the-art, expensive commercial optimizers, this is going to be a really tough thing to deal with. Right? You might have to wait a long time, you might run out of memory, etc., etc. So the next step, as usual, is let's come up with our own optimization techniques that are geared to the problem that we're trying to solve. Okay? And then people have there's all these algorithms for learning support vector machines, which are in one way or another trying to solve this constraint optimization problem. Okay? Let me just mention what is probably the most famous one. It's something that you can get for free on the web. It's called sequential minimal optimization. It was actually invented by John Platt, who's a researcher at Microsoft Researcher, right? Or at least he was one of the people who initially developed this. So what is sequential minimal optimization? Right? It's actually in some ways much simpler than a lot of the quadratic programming techniques that it's beating. And as I said, this is not necessarily the best algorithm, but just to give you an example of how you might solve this problem in practice, here it is. There's some more scalable ones out there these days, and but for many problems, people still just use what's called SMO. let's start from, solving an unconstrained problem, right? There's something even simpler than gradient descent that, sometimes works and is very easy to implement, which is called coordinate descent. Has anybody heard of coordinate descent? Coordinate descent is actually sometimes a good tool to have in your bag because it's so simple. It's just this. I'm going to optimize along one coordinate at a time, right? I want to find my minimum of the function. Don't compute the gradient, right? Let's suppose that computing the gradient is too hard for some reason in our case. Then what can I do? Well, one thing I can do is coordinate descent, which is that, I want to find the minimum along x and y. Well, let me first minimize according to x. And then I minimize along y. And then x and then y, and hopefully not too many steps, right? Of course, in many dimensions, I'm going to minimize along, d things in turn, but that's coordinate descent. Now, you can already see that in many cases, this is going to be ridiculously slow, right? But in some cases, it's okay. And it's very, very simple. Now, let's suppose that we wanted to use coordinate descent for, support vector machine optimization, right? There is a very big problem in this, which has to do with the fact that, in fact, gradient descent would suffer from the same problem, which is I can't just do that, right? Because I'm going to, jump out of my constrained surface, right? I can't just be doing coordinate descent, on one coordinate at a time along my, of my goal function, right? Because I have to keep the constraints in mind. What this means, right, is that I cannot update one alpha I at a time. Right? Coordinate descent is like improve one alpha at a time, meaning optimize the weight of one example, supposing that the weights of all the others are constant. Right? Let's suppose they're all 0, and I'm going to optimize this one to kind of put the hyperplane in the right place relative to it. And I'm just going to iterate through the examples doing this. Right? The problem, though, is that this does not work because it's going to violate my constraints. Right? I have to keep satisfying my constraints. So the SMO is really the answer to the following question. What is the least thing that I can do that is as close as possible to coordinate descent while making sure that I'm always satisfying my constraints? Okay? And it actually is the following. And again, I'm not going to show this, but hopefully it won't be too unintuitive, right? Here's the idea. I'm just going to do the following. I'm going to find an example that violates the KKT conditions. Remember, we saw that this solution has to satisfy the KKT conditions, right? So if there's an example whose constraint is currently not being satisfied, meaning it's violating its margin constraint, well, I better do something with respect to that example, right? But that's not enough, right? That would be coordinate descent. The other thing that I have to do, and this is sort of like what's new and clever about SMO, is that I'm going to select a second example using some heuristics, which I won't go into, but the whole idea here is that I can't optimize one example at a time while staying in this surface, but I can optimize two. Basically, I can change the weight of this example as long as I have some other example whose weight I change to compensate, such that the total value of this thing stays the same. Okay? Roughly speaking, that's the idea. And then what I do is I jointly optimize over alpha I and alpha j, meaning the weights of the two examples. So instead of, coordinate descent, this is descent along pairs of coordinates. And the thing is that, descent along pairs of coordinates is just solving a problem on the plane. It's no big deal, right? And what I'm going to do is basically iteratively solve these problems on planes until finally I converge to the optimum. I know that I've converged to the optimum when all my KKT conditions are satisfied. Okay? In particular, the complementarity conditions are satisfied, meaning that for each example, either its weight is 0 or it's on the margin, meaning its margin is 1. Okay? Questions? Okay, very good. I realize this was a lot of stuff. There's a couple more things to do that we will do next time. They have to do with handling noisy data, right? Here's the thing to leave you, in suspense for the next week, right? Is everything that we've done so far is actually pretty much useless as far as the real world goes, because we still haven't fixed the biggest problem that the perceptron had, which was it couldn't handle noise. Right? One bad example made it go crazy. We still don't know, despite all their beauty and power and max margin and kernels and whatnot, we still can't deal with noisy examples. So the first thing that we're going to see next time is how to deal with noisy examples. And the second one is actually what kinds of generalization guarantees we have on support vector machines coming from learning theory. Okay? And then we will look at dimensional reduction in clusters. Okay? And in the meantime, now you can do the rest of your project. So have fun. Okay. I have sad news for you. All good things must come to an end, and this class is no exception. Time flies. Only yesterday we were just learning about machine learning for the first time, and now you're an expert. You will never have that glorious experience of learning about machine learning and data mining for the first time. Of course, I hope that this class sparks a lifelong interest in machine learning and that you'll continue to learn about it, but that thrill of the first time will never be with you again. I see you all look very relaxed, which I take to mean that you've all finished the assignment on time. Right? Yeah, I see everybody nodding, right? And nobody's laughing ironically, so, so we're good.
My boss told me yesterday I was getting laid off.
Oh, okay, well then there's nothing left to lose, right? Then now's the time to enjoy life, right? And now that you know machine learning, finding a new job will be, easy as pie. Right? Right?
Hopefully.
Hopefully, yes.
Yeah, I'll get, if I don't find a new job before the June 29, I'll be deported.
Oh, well, you can do data mining anywhere in the world these days. There's always a rosy way to look at things, right, if you try hard enough.
But yeah, I did finish the homework.
That's the most important part, right? That's the spirit. That's the spirit. Okay, so today, as the final, item on your menu, we're going to look at actually a whole area of machine learning, which is unsupervised learning. Right? Remember when we talked about supervised, unsupervised, reinforcement learning? Today's class is about unsupervised learning. Okay. Before that, we're just going to finish up with SVMs, which will be quick, and then it's going to be fun because we're going to look at a whole smorgasbord of unsupervised learning algorithms. In particular, we're going to look at some clustering algorithms and some dimensionality reduction algorithms. And then finally, in the last 20 minutes of the class, we'll do the class evaluation, meaning that it's payback time. And you'll finally get to write down all the stuff that you hated about this class. Aren't you looking forward to that? There we go. So, part one. Let's finish SVMs, right? So there were two very important, or there was one very important thing we left hanging last time, and another one, somewhat important thing. The most important thing was that, we saw all these amazing things about SVMs, right? How you can extend the perceptron by, adding kernels, which makes it much more representationally powerful, and also how you can make the learning be much better by doing this notion of maximizing the margin as opposed to just picking any hyperplane. But all of this is still useless, because we still can't handle noise, right? The thing that really killed the perceptron was that, even one little noisy example was enough to make it oscillate forever, and we haven't seen how to do that in SVMs. And in fact, SVMs only took off when in 1990-something, Vladimir Vapnik, who was, the inventor of SVMs, finally came up with a way to make, SVMs actually handle noise. So what is that way? It's actually a very simple idea. I'm just going to give here the general, intuition and sort of like the basic formulation, and then you can basically do what you can basically do is you have this slightly modified problem, and then you put it through the same quadratic programming solvers or SMO type algorithms that you had before. Okay, so let's see what the problem is with noisy data and what we can do about it, right? So here's our good old data set to split, right? So there's some positive examples, right, and some negative ones. And here's my max margin hyperplane, right? So far so good. But now suppose that there's a noisy example over here, right? In the perceptron case, what this would mean was that the perceptron frontier would oscillate, trying to move closer to that example, and then move back towards the other examples forever, right? In the case of SVMs, what's going to happen is one of two things, right? Let's say you have an SVM with a linear kernel. Right? And you pass this to your constraint solver, right? What's your constraint solver going to say? Your constraint solver is going to say, sorry, no, we can't deal with that. Your constraints are not satisfiable, right? There is no feasible region. This is the technical term. There's no feasible region. However, let's suppose that you have something a little bit fancier, right? After all, that's what SVMs are about. Let's suppose that you have something like the Gaussian kernel, right? What is the SVM going to do here? What is the optimization algorithm going to do here? Any rough guesses? Remember, the idea of Gaussian kernels is that you have something like a kernel, let's say, around each, vector, right? Or at least around each support vector, right? So what's going to happen? What's the new frontier going to look like? it's going to have to have the plus on the positive region, right? So it's going to look something like, let's say, roughly speaking, like this. Right? Hey, I split the positive from the negative example, right? Using this kind of, higher order curve. Except that, of course, this is nothing like what we really want. Okay? So, the question is, what can we do about this? And here's where our next idea comes along, which is the idea of slack variables. So what is a slack variable, right? Let's look at the geometric intuition first. And again, the intuition is actually quite simple. What we really want to do with this example, right, is allow it to stay there, let it be, right? It's a negative example. We're not going to change the frontier to, try to, put this example on the right side, right? That would be a mistake, okay? So what this means is that we have to allow for examples with negative margin, right? If you think about it, what this example has is a negative margin, right? Because if you notice, right, this example is, if you project this example to the hyperplane, right, along the perpendicular, right, which this is not quite the perpendicular, but forgive my bad drawing, right? If you project this example to the and this is not the max margin hyperplane either, so let me actually draw that again. This was just to check whether you're carefully following. And I knew you were, but you knew it was beneath you to say something about this, so you did. So let's actually try to do this a little bit better now. Like, so here's the hyperplane, right? And like here's the perpendicular distance, right? And now if the example was so actually let me ask you, where in here is margin 0?
On the line?
It's right here, right? So this example actually has a negative margin, right? But in fact, we want to do more than that, right? We'd actually like all the examples, remember, to have a margin of at least 1, right? So we would like the example to be over on this side of things, right? But it's not. So here's the thing. In order to allow noise, we're going to let the example be on the wrong side of the hyperplane, right? But at the same time, we can't just let that, happen with any example. Otherwise, it's a free-for-all, and now the opposite thing will happen with the optimizer, right? It will just, plunk down any hyperplane at all, right? And say, well, there's a bunch of examples that violate the margin, but so what, right? So what do we need to do here? We need to allow examples to violate the margin constraints, right? Otherwise, we can't handle noise. But we need a penalty for violating the margin constraints. Right? This is sort of like a general strategy in machine learning. We're going to allow the noise, but we're going to pay a price for the noise, right? So what we're going to try to do is have as few examples violating the margin as possible, right? And more than that, right? If you think about it, what do you think is worse? Is if this guy is the wrong example, or if, let's say, like this guy here is a negative example, right? So here are two possible noisy examples, and which one would you prefer? Right? Which one is the worst? Right? Is it this noisy positive example, or is it this noisy positive example, or is it this noisy negative example? Which one is the worst of them? It's the positive one, right? Because it's way off the hyperplane. So, what this is telling us is that we don't just want to penalize the number of examples that violate the margin constraints. What we want to penalize is for each example how much it violates the margin constraint by, right? So this example is worse than this example. Okay? So what is a natural, measure of how much the example violates the margin constraints by? Yeah, you just said it to me, visually. So what is that in words?
The distance.
The distance. Very good. So we're going to penalize by the distance to
The zero margin.
This was a trick question, right? So you could penalize it by the distance to here. That's not, a bad thing. But what about the distance? What about this part? Notice that the example here, right, from here on, right, the example is on the wrong side of the hyperplane, right? So that's clearly bad, right? But what happens with an example that's here? It's on the right side of the hyperplane, but it's violating the margin constraint, right? Because it should be at least here, right? So would you care to revise your answer? How about we penalize each example by the distance to?
boundary of the margin.
Yeah, exactly. By the distance to this line, as opposed to the distance to this line. Right? Well, that distance is called the slack. Slack is actually a technical term in mathematical programming. It's how much you allow things to be off by. Okay? So that's what we're going to do. Each example is now going to have an associated slack variable. That's what we call it, a slack variable, right? And that slack variable could be anything, but we're going to penalize the sum of the slack variables. Okay? And that's really the whole idea. So here's how we handle noisy data, right? We introduce the slack variables, which for some reason are represented by the Greek letter psi, right? One of the most abstruse Greek symbols you ever saw, right? So for the ith example, it's psi I, right? It's an abstruse symbol because we don't like the slack variables. We wish they were small, right? So we don't want it to be a letter that we like, right? So we introduce our slack variables psi I, and then what we do is, notice the following. Before, right, we were just minimizing the norm of the weight vector, right, or the square of the norm of the weight vector, right? Now we're going to minimize a sum of two things, right? As usual, machine learning, we wind up with a trade-off between two things. One is the norm of the weight vector, and the other one is the sum of the slack variables. Okay? Subject to the same constraint as before, which is that all the examples have to, have a margin of at least 1, except that now the margin doesn't have to be 1. It's 1 minus the slack variable. Okay? So an example can have a margin of 1 minus psi I, which means it could even be negative, right? Which is what's going to happen if it's on the wrong side of the hyperplane, right? So that's going to be allowed, but we're going to pay a price for that here. Okay? Did everybody follow this idea? It's a fairly straightforward idea, right? And now, of course, there's this magic coefficient here that usually shows up in machine learning when you're trading off two things, which is your, penalty for the slack variables, right? And, here's the question to you. What is going to happen when C is very small? Actually, let's say we make C 0. What's going to happen in that case?
No noise allowed.
No one is allowed to violate the margin constraints, right? So I'm going to overfit profusely if there's noise, right? On the other hand, what's going to happen if C is infinity? We don't care, right? So what's going to happen if C is infinity is that actually, I'm in the opposite situation. I'm going to greatly underfit, right? Because what's going to happen is, the only thing that I care about is the slack variables, right? I'm not caring about minimizing the norm of the weight vector. So, my whole SVM fitting procedure goes out the window. So bottom line, this C is our usual overfitting control parameter, or if you will, the bias variance trade-off parameter, right? And how might you set the value of that C, right? Now this is a question for you, right? When you use the SVM learner, is how do you set this value, and how would you set it?
Cross-validation?
Cross-validation, exactly. See? Yeah, you know these things right off the bat now. Exactly, you set it by cross-validation. Again, there's some theory on how to do these things, but in practice, the easy and effective thing to do is set it by cross-validation, right? You do a bunch of runs because it depends on how noisy the data set is and whatnot, right? So you do a bunch of runs with with cross-validation and use that to pick the C, and then you run another whole data with that C. Okay. Now, of course, what we have here now with the select variables is just a new quadratic programming problem, right? This is still a quadratic programming problem, right? Because there's still this quadratic term here. This here is just a linear term, so it doesn't make things worse, right? It's still a quadratic function. And my constraints are still, inequality constraints, of a linear form as before, okay? So now you can use your quadratic programming solver or, a special purpose algorithm for this. And this is how we handle noise, okay? And when finally this ingredient was added to SVM, suddenly they were, beating the state of the art in a whole bunch of important problems, and they took off like wildfire. Okay. Questions about this? Yeah.
So if the distance is very high, let's say, there's a data point that's far out because of some random noise, then that means that we won't try to fit that, right? To minimize. Well,
I may or may not, right? So let's suppose that there was a point way over there, right? What that means is that my SVM would try harder to fit that, would prefer, for example, a frontier that fit that point over one that actually, it would allow itself, for example, to get, let's say, a whole bunch of examples wrong on this side, right? That example would count for more than a lot of examples where the margin constraint was only being violated by a little, right? But let's take this all the way. Let's suppose that this example was really, really, really far away, right? And let's suppose that I had a linear SVM. The SVM would put the hyperplane between that example and everybody else and say, well, all you guys, you're gonna be wrong, right? Of course, what that means is that you need to change your C to tolerate that example, or even better, you need to detect that example and throw it out of your data set. Okay? So this is another problem in machine learning that, in data mining that we haven't looked at, which is outlier detection, and there's a number of things that you can do, right? So one of the things that you can do when outliers are making your life very hard is, just find them and get rid of them, and there's a number of ways to do that. But often what happens is not so much that you have one or two outliers, but there's just this sprinkling of noise throughout the data. And in that case, you really have to do something like, slack variables. Okay. More questions? Okay, so there's one more point here, which is the following. I said, right, that, SVMs came out of that whole learning theory that we did, last time, or actually, 2 weeks ago, right, of, VC dimension and pack learning and whatnot, right? But so far we haven't actually seen how, right? Where does that come in? Okay? So I left that till last, but, it's still something worth knowing about the theory behind SVMs, right? And this is what, Vapnik was interested in for the first, 30 years, right? And then finally he got around to actually making a practical algorithm, which, was very much worthwhile, is the following, is that you can show that there's a connection between the margin and the VC dimension. The larger the margin, the smaller the VC dimension. Excuse me. And this makes, so I'm not going to prove that here, right? But this makes sense for the following reason, right? If you think of the margin as having a thick slab instead of a thin hyperplane, right? Now it makes sense that a thicker slab would have a lower VC dimension, right? Because the thicker the slab, the less you can move it around. The less able you are to shatter any data set that might come up, or any labeling of a data set that might come up, okay? So large margin means thick slab, means less freedom, means less capacity to overfit, means lower VC dimension, okay? So if we take the mathematical relationship between margin and VC dimension, right? From the margin, I can figure out the VC dimension, and I can then plug that into the kinds of theorems that I had before, right? And now I have a theorem for the number of examples that I need, for example, as a function of epsilon delta and the margin, okay? There's an interesting twist here in that I don't know the margin a priori, right? I priori can say something like, if this is the margin that you're going to get or you're going to shoot for, this is what you're going to need, right? But in reality, this becomes actually what is called a data-dependent bound, which is a bound that depends on quantities that you only get after you run the algorithm, okay? Which leads to a bunch more interesting theoretical notions, but nevertheless, this I think is worth knowing about because it kind of completes the story. However, as the very last chapter in the story of SVMs, at least for this class, there's another type of bound for SVMs that is actually much less well known than the margin bounds, which after all is where SVMs came from. But in fact, first of all, it's much simpler to understand, number one, right? The demonstration is actually something that we can almost do, verbally. And number two, those bounds actually tend to be tighter. The margin bounds, like most packed learning bounds, tend to be very loose, right? In fact, they're often what's called, vacuous bounds, meaning that they tell you that the error is going to be below 4,000%. Well, I already knew it was going to be below, at least it was going to be at most 100, right? The bound that we're going to see next, though, is never vacuous. It's always, at most 100%, but it could be a lot less. And you know what that bound is? First, let me tell you what it is, and then let's see if you can guess why that bound would be the case. It's a joyfully simple bound. It just says that your expected generalization error, right? Notice this is my error on curly V, which is the real distribution, right? It says that my expected error, right, is going to be at most the number of support vector machines over the number of training examples. So, for example, if only 10% of my training examples wind up being support vectors, I can say with high confidence, subject to the variance in these means, that the real error rate is at most 10%. Isn't that amazing? This is actually a pretty darn good bound, better than many bounds that are much more complicated. And the other thing is that this is easy to measure, right? You run your SVM optimizer, you count the number of support vectors, that over your training data set size is your guarantee on the generalization error. Now, this is worth having, right? But now comes the interesting question. Why do you think this bound holds? Can anybody guess? Why would there be a bound on the expected generalization error that's the number of support vectors over the number of examples? Or another way to put this is like, why does the error go up, or the potential error go up with the number of support vectors? Okay. Here's a hint. Imagine doing leave one out cross-validation on an SVM. Right? You remember what leave one out cross-validation is? Right? It's cross-validation except that each fold is a single example, right? So what I do is I take out one example and I relearn my classifier, and now I see what I get wrong and what I get right. Okay? Or actually, for each example, what I see is whether I get it right or wrong when I hold it out. Okay? And I do this over all the examples, and I see what I get wrong and right. Right? So what happens if you do leave one out cross-validation on an SVM? Let's look at two cases. Case one is, let's say that the example that I leave out is not a support vector, right? So let's say that, again, let's not suppose that this guy wasn't noisy, right? And let's suppose that, I leave out, say, this example. What happens to my hyperplane when I leave that out? Nothing. Fantastic. Which means that this example is correctly or incorrectly classified by this hyperplane. Correctly, right? Good. Now you see where this is going, right? What happens when the example that I leave out is a support vector? Right? What happens, for example, if I leave out this example? What's going to happen to my hyperplane?
Okay.
It's going to swing, right? And in particular, it's going to swing past this example, right? In fact, it might not always swing past the example, that depends, right? But at least it could swing past the example, right? So what is the moral of the story? Is that when I do leave one out cross-validation, if the example that I'm leaving out is a non-support vector, life is good. I will never get that wrong because of this. If the example is a support vector, then I might get it wrong or I might not. But what this means is that the upper bound on the number of examples that I might get wrong is what? The number of support vectors, exactly. Right, the leave one out cross-validation estimate of the error is never going to be more than the number of support vectors over the number of examples. Right, very simple argument. Okay. Now notice that, this is just an estimate obtained by leave one out cross-validation. And notice an interesting twist that we have here is that in order to do these leave one out estimates, I don't actually need to run the support vector machine n times, right? I run it once and then I can actually basically, by inspecting who's a support vector and who's not, figure out this bound, right? And this bound has some uncertainty because, the leave one out estimate has some uncertainty, right? Only if I had infinite, data points, infinite examples, would my uncertainty become zero. But, nevertheless, if your training set is fairly large, that uncertainty will be, insignificant, and this is actually going to be a very reliable bound. Okay? So there's the margin bounds, which are what everybody always talks about, and there's actually the leave one out bound, which is in some ways the better one. And again, this gets us back to where we started, which is like, there's the view of SVMs as a perceptron and the view of SVMs as instance-based learning. This leave one out type bound is actually a kind of thing that you can do with instance-based learning. Okay? Same with nearest neighbors, right? Remember my Voronoi cells, right? And the whole thing, well, let's take this one out and see if it's still correctly classified. It's the same idea that we have here. Okay?
Question?
Mm-hmm.
Can you show an example where you take out a support vector and it doesn't get incorrectly classified? And would that mean it was redundant to begin with?
Yeah, sure. So, the reason why it might not get so here's an example, right? Let me put another support vector, like right here. Okay? Actually, not another support vector, another example, right? And so now what happens is that, and I'm going to try to draw this roughly correctly, right? But now what happens is that this hyperplane is going to swing until this other guy is at the margin, right? You see what's going to happen here? So the hyperplane moves, right? So now this example is violating the margin constraint, but it's still not being incorrectly classified. Okay? So what happens is that the support vector is now violating the margin constraint, which is bad, but it's still not being incorrectly classified. Okay? If this example was not here, the hyperplane would swing until this guy was incorrectly classified. But in general, like we have a lot of support vectors around, so this might happen. Again, in higher dimensions, you're more likely to get the error than in lower dimensions. Okay? Good question. Any questions about support vector machines? Or supervised learning in general?
So how did we end up generalizing that number of support vectors in the training set is the upper limit that we get over the entire universe of?
Oh, I mean, remember, a cross-validation estimate, right, is actually an unbiased, it's a validation estimate, right? So it's an estimate that doesn't suffer from overfitting. Right? It's actually a fit. The whole thing about cross-validation, and in particular about cross-validation, right, is that it's a fair estimate of your error on the examples that you haven't seen. Because it is error on examples that you haven't seen. Okay? There's an error in that I'm using, so think about it this way. There's the error on the training examples, right? This, is biased because we're conducting a search to fit those examples well, right? There's the error on the true distribution, which is what we're interested in. What leave one out cross-validation gives us, or any validation set gives us, is the error on a finite set of examples that you didn't see, right? Now the important thing is that you didn't see them, so you didn't overfit them. So this estimate is unbiased, right? Now because the set is finite, it's going to have some uncertainty, it's going to have some variance, right? But that we have to deal with. The important thing is this is not subject to overfitting into the, basically, we fit those examples, we didn't fit these, right? The interesting trick here is that, these guys, we only did one run here, right? But what I'm saying is that we can fish out of it what would happen if we had actually done the leave or not cross validation. Okay? And in fact, this idea can be applied to, to a number of other, learning algorithms as well, so it's another good thing to have in your toolbox. Especially if you're trying to do this on a large data set where, you don't want to do many runs of cross validation and things like that, right? In a way, the thing that comes out of this support vector machine is like sometimes there's a way to do cross-validation on the cheap. We're actually having to do 10 runs or n runs. You can figure out from your results what the results of the cross-validation would be, or at least a bound of them, and then hey, you might as well use that. More questions? Okay, so let us then go on to unsupervised learning. And as I said, unsupervised learning is a very large subject, probably almost as large as supervised learning. But we're only going to devote this one session of the class to it. And part of the reason is that you can't do everything. The other part is that this is substantially more difficult and less mature than supervised learning. So it's worth knowing about, but maybe not something that's quite as easy to use as the rest of the stuff that we've seen. Okay. So we're going to look at two main types of unsupervised learning: clustering and dimensional reduction. And in each of these, we're going to look at a series of different approaches, increasingly powerful, or in some cases just of different types. Okay. So for clustering, we're going to look at k-means, mixture models, and hierarchical clustering. And then for dimensional reduction, time permitting, we're going to look at principal component analysis, multidimensional scaling, and isomap. These are all things that are very widely used. Okay. So these are some of like the standard tools of the data miner. Okay. So what is the general motivation for unsupervised learning, right? In supervised learning, it's like, well, I want to predict whether this is a spam or not, or whether this person has pneumonia or not. Tell me the right answer, please. Right? The motivation in unsupervised learning is somewhat different, right? In many ways, what we're looking for when we do unsupervised learning is not a precise result, but is a better understanding of the data or a better way to look at the data. Okay? So in particular, right, the problem that we have in many areas these days is that we have too much data. It's not that we don't have enough data, it's that we have way more data than we can look at, right? You'll Walmart and you have, all the customer baskets, every time that a customer at Walmart has gone through the checkout, this has produced a record, right? They probably have, billions of these by now. What are you going to, nobody can look at that, right? So what can you do? Well, you can reduce the amount of data, right? what I would like to have is something that, I, human being, can look at and play with and understand, right? That's much smaller than the original data, but that hopefully still captures the essential of what's going on in that data, or, has the same features, the same phenomena, and so on. Okay? So that's the idea. And now clustering and dimensional reduction are sort of like two complementary ways to do this, right? If you think of data as a big table, right, of examples by dimensions, right? So each row here is an example, like say one, basket from, of goods purchased at Walmart, in one day by one person. And these are dimensions, right? Right out there is like a big table, right? Then the idea in clustering is that we're going to reduce the number of examples. We're going to aggregate the examples into super examples, also known as clusters. I'm going to say like, oh, these 3 people over here, they're very similar. And these 4, they're also very similar, or these 4 million. And these 2 are also very similar. Right? Marketers really like to do this. They call it segmentation. Right? Marketers call clustering segmentation. It's one of their key tools. Right? You run your clustering algorithms to see what are the main groups of your customers. Right? And this is how Nike found out, I'm guessing, I don't know the details, that, their 2 main clusters of customers are teenage boys and middle-aged women. Right? That's the technical part. Then comes the creative part, which is naming these clusters. That we haven't solved yet. We're going to need some more AI for that, but that's also important. And many expressions in common use today actually come from naming, some of these segments, like soccer mom, right? The expression soccer mom was invented by marketers as a category of customers, like suburban women, middle-aged that have children, and take them to soccer, among other things, right? So that part can also be important. Nevertheless, we're just going to study the more technical side of things, which is coming up with those clusters. Okay. The other option, of course, is reducing the number of dimensions, right? And you might even want to do both, right? So the idea of dimensional reduction, I'm going to say like, these 200 properties of a person, I'm just going to summarize them as, this is how much this person likes books. And this is how much this person likes, videos in general. Like this person watches a lot of video and never reads, for example. Okay? I mean, often those dimensions are kind of more interesting than this, but, just to give you an example, right? So you can think of what we're going to do here is like we have a very big table of data. First, we're going to look at how to reduce it to a small number of examples, and I go like, oh, here's the soccer moms, here's the, they have all these dimensions like the patios and pools crowd, and here's the, et cetera, right? And then I'm going to look at how I can reduce things to a small number of dimensions, maybe even 2 or 3 dimensions, such that I can actually look at it, right? I want to be able to look at a graph of this data, maybe even a 3D plot, and move it around. But again, I get it back down to a number of dimensions where my visual system can actually handle it. Okay? So the 2 most popular numbers of dimensions to reduce things to are 1, 2, and 3. 1, because what is 1? What is the point of reducing things to 1 dimension? Is that I want to know what is the main, phenomenon in this data. What is the main, thing along which, my examples vary, right? What is the dominant trend or the dominant phenomenon? 2 is because I want to be able to look it on the plane, and 3 is because I want to be able to visualize it in 3D. Okay? You may also use 4D where you use time as one of the dimensions. Yeah?
Is it's like the most important dimension or whatever. Is it similar to like the attribute with the highest information gain?
Yeah, great example. So you could say that doing selection of attributes by information gain is one way to do dimensional reduction. So yeah, actually, great example. So you can think of that as one example of dimensional reduction, but here's the big difference, and we'll see in a bit how this works out, is that what they did was just select one of the existing dimensions. The idea in dimensional reduction is that I'm going to do something much more interesting, which is I'm going to invent new dimensions that are somehow combinations of the old ones. Right? It's not I'm going to select the 100 most informative words, right? Is that I'm going to select the 100 dimensions that are, say, a linear combination of words that have to do with, how much this document is about sports versus, politics, etc., etc. Okay? So another way to look at this is, let's say that my points were in 3D, right? I want to reduce them to a plane. And, the information will just be, well, the plane can be this or the plane can be this. But I want to allow, planes in any direction because that may be where the data actually lives. Okay? Good question. More questions? Okay, so let's see how we do this. So first of all, what is clustering? What is the problem? I'm given a set of examples, and I want to divide them into subsets of similar examples, right? That's the idea. Objects that behave similarly should go in the same cluster. Right? So in a way, this has some reminiscences of instance-based learning. In fact, even the algorithms sometimes, have a certain parallel. And of course, just as in instance-based learning, then this, immediately brings up the key question: how do I measure similarity? This is a difficult question. It's also an important one. Again, there's many generic ones like, Euclidean distance and whatnot. But in general, what you have to do is think about your problem, right, and figure out what to you makes, say, two people similar, right? If you're doing clustering for medical purposes, it's probably one thing. If you're doing clustering for, marketing purposes, it's probably a completely different thing, right? If you're doing, clustering for marketing drugs, right, it might be some combination of these two, probably more weighted towards money than health, right? But anyway, I digress. Okay? The other question is, and this is actually a question that bedevils all unsupervised learning, is how do I evaluate the quality of the results? This is one of the main reasons why unsupervised learning is harder than supervised learning, is that in supervised learning I have a very clear criterion about what is a good model and a bad one. The good model is the one that makes accurate predictions on data that I haven't seen, right? When the next, email comes along, am I accurately predicting whether it's spam or not, right? Here, it's much more nebulous, right? What is a good clustering? People have come up with all sorts of measures of what's a good clustering, but you may or may not like them. So, there's no universal agreement on this, so it's also hard to have sort of like a universal set of, techniques that optimize these measures. So, things are kind of a bit more fuzzy and difficult, okay? So some people kind of look down on unsupervised learning because they think it's sloppy. On the other hand, that is a big mistake, because you know why? Even when people do supervised learning, a lot of the time what they're really looking for is not like, oh no, I want these 2% more of accuracy. What they're trying to do is understand the phenomenon, right? And if your goal is to understand the phenomenon, then unsupervised learning is just as useful or more useful than supervised learning, okay? So, you have to be forewarned that things are a little bit trickier here, but nevertheless, this is also important, okay? So, the first algorithm, k-means clustering. The simplest, clustering algorithm there is, probably the first one you'll use for any problem. This is like the nearest neighbor or the naive Bayes of clustering. Okay? How many people here have actually heard of k-means clustering? Okay, that's actually a few of you. Okay? So what is k-means clustering? It's a very simple idea. You can program it in, half an hour, right? First of all, you just pick random examples as your initial means, right? So k-means, or k-means clustering, at least in its basic form, is an algorithm for classifying for clustering numeric examples, right? So you're in Rn, right? And my goal is to find k-means, right? So each cluster is going to be represented by a mean of some set of the points, okay? So I'm looking for k-means. Okay, so what do? How does the algorithm work? I pick, let's say, some set of random examples as initial means, or some other criterion that you might have, right? I need to pick initial positions for my means, okay? And then I just alternate between the following two things. I assign each example to the nearest mean, okay? So let's say that my examples were here in this room, right? And I say like my initial, mean is one here and one is over there, right? So if there's an example over here, it's closest to this mean than to that mean, so it gets assigned here, okay? So basically, I divide my examples into k subsets. Each subset is the examples that are, in the Voronoi cell of one of the means. Okay? Simple idea. And then what you do, right, is you compute the new mean as the average of the examples that were assigned to it. Right? Now there's this mean here in this and it's winning these examples, right? But maybe it's a little off from their mean, so what I need to do is compute their mean and I'll move my new mean to that. Okay? Now, of course, since my mean has moved, maybe now it's going to win some new examples and lose some old ones, so I need to do this again. And when finally I converge, meaning that on two successive iterations I get the same mean, I'm done. Okay? Simple algorithm. Okay? And the running time is actually not too bad, right? The running time of this is just order of k, right, which is the number of means, times the number of examples, right? Because I need to compare each example with each mean, right? Times the number of dimensions, right? Because computing in distance, has cost number of dimensions. Times my number of iterations, which I don't know what it's going to be, but let's hope that it's not too large, right? Okay, so, this is not great, but it's not too bad either, right? There is one question here that immediately arises, which is what? Is there a question that comes to your mind apropos of this algorithm?
How many k?
Mm-hmm. Oh, how do you pick k? Yeah, exactly. How do you pick k? Right? Did somebody tell you what the k was? Well, yeah, on a good day, somebody will tell you. Actually, here's the interesting thing. For example, marketers, and actually oftentimes people will tell you what k is. Not because it's the real k in the data, but because it's the k that they want. Like say, I know someone working with marketers at a company that I shall not name, where they told them that they wanted 7 clusters. And I said, but I've really clustered this well, and there's, I don't remember, like 20-something. Like, we do not care about your 20-something clusters. We want 7. And it's easy to smile at this, but the thing is that, like, if they have 7 clusters, they can say develop 7 different marketing strategies. They are not going to develop 20 different market strategies, right? So, maybe it makes sense. On the other hand, if your question is like, how many clusters are there really in the data, right? Now we get to this from, well, what does it mean, really in the data, right? There's no clear answer to this. Okay? So what people often do is like, you can try different, case, right? And then you look at the results, and once you have a result that you're happy with, you take that. You can say like, oh no, this thing is really singling out very small clusters, not good. Or, like, this is really glomming together things that shouldn't be glommed, I need to refine it, right? So you need to play with k. This can be done automatically, right? But the thing is that if you do this fully automatically, then this k becomes n. Okay? Because you need to try from 1 to n clusters. And then, this whole thing becomes n squared, and now this does not scale, for sure. Okay? There are many algorithms, a lot of, data mining work has gone into making clustering algorithms scale up, right? We're not going to look at that, but they certainly exist. Okay? So this is k-means. Easy algorithm, widely used, probably one of the first things you should try. Questions about k-means?
Is there any limitation on distance between any two?
Oh yeah, so how do you measure distance is, as I said, you can pick the measure, right? Usually k-means use it with something like, Euclidean distance, or weighted Euclidean distance, or Euclidean distance where you've normalized the variables to all be between 0 and 1, right? So.
My question was, if you keep changing the mean, will that...
Oh, I heard this. If you keep changing the mean, yeah? Then what?
Can the distance between any 2 points become larger than this?
Become larger than what? Sorry?
When we're clustering and you're keeping moving the mean, then the distance between any 2 points, any 2 extreme points might get larger. That's fine, I guess.
Sorry, can you speak louder? Larger than what?
Like, say we want to cluster all these points into one, and other set of points into other clusters.
Mm-hmm.
But if we keep changing the mean, there might be an option like it keeps growing.
The distance between...
The output is just the clusters of points. Is that what you were saying? That you don't actually... What the output is not a bunch of clusters, it's actually just the single points that represent each mean.
Well, you can return both, right? So when I'm done, right, I know 2 things. I know where my means are, right? This is usually what people ask first, right? Where are my means? Or there's one mean here, and there's one mean there. But you can also ask in like, for each object, right, what mean was it assigned to, right? And then you can return both of those things. Right, and remember, k-means is a greedy algorithm, right? So usually what is going to happen is that the distances are going to, on average, are going to keep shrinking, right? So you'll get better and better clusterings if you measure that by, the average distance between the points and their centroids. Is that what you were asking?
Yeah, that's fine.
Okay, good. Now, we are not done, right? K-means is our first clustering algorithm. It's not our last one, right? So the next question to ask is, when is this going to work versus when is this not going to work, right? First of all, as with a lot of these algorithms, you probably want to try a number of different random initializations because one of them might just, behave badly, right? But even beyond that, there's a whole bunch of situations where k-means is very likely to misbehave. In fact, the set of conditions where k-mean will usually give a good result if, properly taken care of, is quite narrow. So in particular, k-means needs all the following conditions to work well, and we're going to see the reason for each one of them. It works well if the clusters are roughly spherical, not very elongated, say, and they are well separated. There's one cluster over here and one over there. They're not kind of like, all of intermingled and you can't tell very well where one ends and the other one begins. It works well if the clusters are of similar volumes. K-means often runs into trouble if like one cluster is all bunched up here and then another one is very widely distributed. And finally, it works well if the clusters have similar numbers of points. Notice that this is different from volume, right? Because you could have larger or smaller, higher or lower density, right? But if one cluster has, 10 data points, another one has, 1 million, this is going to be trouble. Okay? So first of all, let's see why, these things are the case, right? And then let's see what we can do about them, right? So here's an example to illustrate why clusters need to be spherical, right? Let's suppose that, and I'm going to use ellipses to represent my clusters, right? Let's suppose that these were my two clusters. Right, so picture a bunch of data points in this cluster and and a bunch of data points in this one, right? So these clusters are very much not spherical, and this happens a lot in practice. And again, remember, it's not just a matter of rescaling the data because the clusters, this thing could be in any direction, right? So just rescaling thing doesn't necessarily solve this problem, right? So what do you think K-means is going to do here, right? How is it going to fail?
But we're going to cluster them across both.
Exactly. K-means is going to say like, oh, there's a cluster here and there's a cluster here, right? And this, if you look at the world through the eyes of K-means, this is very natural, right? Because, you're using Euclidean distance, right? And the truth is that, like this guy, right? This guy here is a lot farther from this guy than it is from this one, right? So guess what? This is what K-means is going to do. Disaster. Okay? Everybody got this? So, disaster number 1. Disaster number 2, the clusters need to be well separated. Right? Why do you think things are going to misbehave? So the clusters being well separated means, like there's one cluster over here and there's another cluster over there. Of course, I'm exaggerating, right? But in this case, clustering is not too hard, right? Because it's kind of obvious what the clusters are, right? The hard case is when you have something like the following, right? Here's my, blue cluster, and here's my red cluster. It's actually not too hard to see why K-means might have trouble with this, right? Because, even you and I might have trouble looking at this and, deciding where the clusters are, right? In this case, I kindly drew the boundaries, but if this was a bunch of points, right? Nevertheless, it might be, this happens a lot, right? There are generally different clusters there. And in fact, when we look at the better methods for clustering, we will see, how that comes about and how we can detect it. But if you don't have a lot of data points and things are overlapping a lot, it's very hard to tell exactly where one cluster ends and the other one begins. Okay? So this is problem number 2. Problem number 3, right, is a slightly more insidious one. It's that the clusters had better be of similar volumes, right? So suppose that, my blue cluster was like this, let's suppose that my red cluster was like this, and my blue cluster was like this. Right, blue and red are marketing names, right? But the content doesn't change, right? So why might this be a problem for K-means clustering? What do you think might happen here?
Some of the blue examples are nearer to red, so it might get included in red.
Yeah, exactly. So number 1, right? You might get clusters like this, right? I get a cluster that actually captures some of this chunk, right? And then, the blue cluster is, is the other one, right? Because that cluster just looks like a few more data points off of the big cluster that's in the blue, right? So this is one thing that can happen, right? But in fact, things actually here could go bad from the start. You know why? Right? It's one thing to say like, oh, your clusters are going to converge to the wrong thing, right? But this actually can be worse. The clusters could start off in the wrong place and never recover. Why might the clusters start off in the wrong place here? Right? Remember that what I do is I first, pick my, let's say I'm doing 2 means clustering, right? So I'm going to pick 2 data points at random to be my, cluster mothers, right? So where are those points going to come from?
The big blue block.
Well, actually, I lied, right? This is the 4th problem. Right? This was testing the distinction between those two, right? So everything that I said about the 3rd problem, or that you guys said about the 3rd problem, was true, right? But this is actually a problem with the 4th. This is actually the 4th problem, right? If clusters have very different numbers of points, right? Notice that the problem with volume, right, is that again, when I'm clustering things by distance, right? Well, I'm easily led astray, right? But when clusters have similar numbers of points, let's suppose that the clusters are of similar volumes, but they have different numbers of points, right? Another problem comes in that it's a very lucky day where I actually choose one centroid from one cluster and one centroid from another cluster. And on a good day, I could start off wrong and actually converge in the right direction. Actually, that can happen. On the other hand, it might also not happen. Okay? So what will typically happen is that I will start with both of my centroids being from one of the clusters, right? And then what needs to happen is that one of them needs to walk over to the point where it just becomes responsible for the little thing over there. Well, unlikely that it'll happen, but a lot of the time it won't. Okay? So these are the pathologies of k-means. Any questions about any of this? Okay, very good. So, what do we do about it, right? We better have some solution to this because most problems are not like this. So what can we do? Well, this is where mixture models come in. Mixture models are, one of the real workhorses of the machine learning professional. They are used all over the place, right? So this is very, well knowing about. Mixture models actually solve all the problems of k-means. With mixture models, at least in principle, right, subject to having enough data and all of that. With mixture models, the clusters don't have to be spherical, they don't have to be well separated, they don't have to have similar volumes, and they can have very different numbers of points, right? This sounds like magic, right? Well, if you have a lot of data, a lot of computing power, that magic will become available to you. Otherwise, you might still have, some difficulties. But nevertheless, let's look at what mixture models are and how we learn them, right? So what is a mixture model? A mixture model actually has a whole bunch of desirable features. One of which is it answers brilliantly the question of what is similarity and how do I evaluate the quality of my clustering. If you go, with mixture models, all those questions are answered for you. You don't need to worry about them, right? This is a big headache, to avoid. So what is a mixture model? A mixture model is a statistical model for the data. It's actually a type of, probabilistic learning, of statistical learning like we saw, a few weeks ago, when we talked about, these different Bayesian methods and whatnot. Right? So mixture model says that there's a probability distribution over my data points. Right? So think of X as a vector in Rn as a point in this room. Right? And what I'm going to assume is what's called a generative model. It's a model of how God creates the data, of how nature generates the data. Okay? And the generative model is like this. The way I'm going to generate the data is first, I'm going to pick a cluster. There's say 10 clusters, A, B, C, D, E, and I say, oh, the next data point, you're going to come from cluster B. And then once you've come from cluster B, each cluster has a model, like say a Gaussian distribution or, a product of multinomial something. And then I generate the point from that model. Okay? So there's two steps, picking the component and then picking the data point according to that component. Okay? Now, how do I pick the component? This is where my P of Ci comes about. P of Ci is the probability of the ith cluster. For example, if there were 10 and they were all equally likely, the P of Ci's would all be 0.1. Okay? But in general, some might be larger and some might be smaller, right? So I can handle clusters of, different, sizes or, densities. Okay? And then, so what is my probability of a point is the sum over all clusters of the probability of picking the cluster times the probability of generating that point, given that I'm in that cluster, right? This is our good old rules of probability being applied here. Okay? Remember our example of, total probability, what are your chances of getting run over by a car if it's red or blue or if it's red or green, right? Clusters might be blue, but traffic lights not yet. Okay? Right, so this is what we do. Everybody got this idea? This is really what we're going to be talking about for the next, 15 minutes. Okay. So there are many reasons to like this, one of which is it is not clear what my objective function should be. It's just the log likelihood of the data, right? Same as when we were doing Bayesian learning or, statistical learning more generally, right? So I have a set of data points. I want to find the clusters and the model for each cluster according to which my data is as likely as possible, right? That's what maximum likelihood means, right? My clustering is likely if it makes my data set likely, okay? So that's good. I now have a nice, measure of, so this is not explicitly a measure of similarity, but implicitly it's going to be, and when we look at some concrete examples, we will see how this works out as a similarity measure. It's also an objective way to evaluate my results. right? Once I've learned the model, right, I can now I can actually do this good old thing from, supervised learning of having a holdout data set, right? And now I take this holdout data set and say, like, how likely are these points according to my clustering, right? If I have the clustering that was like, overfitting my data, right, these points will not be very likely according to that clustering. So it's a bad cluster. If I've generated clusters and now my data points tend to be, in the high probability regions, near the centers of the clusters, then it's probably a good clustering. Okay? So this solves the problem of a similarity measure, and it solves the problem of evaluating the quality of my clustering, right? Pretty good. And here's another great advantage of this, is that notice that I didn't specify what this distribution is. Right? I didn't specify what the distribution of the data, given each cluster is. And this is a great thing because what it means is that I can plug anything that I want into here, and the techniques that we're going to see here still apply. So, we're going to see some standard cases of these distributions, but, the higher level lesson here is like, you can define your own convenient distribution for what you want tomorrow. Usually, it can be a simple distribution because the power comes from considering, a whole bunch of these. Okay? So this is actually very general. Like this, in some sense, this is not just one clustering algorithm, it's a whole class of them that could be very different depending on the domain. Okay? So, so this is the general idea. So first of all, let's look at specifically what kinds of models you might have here, right? And then how you might learn them. Okay? So any suggestions for what my, P of x given Ci might be? Anything that comes to mind? Closing your eyes so that you both don't look at the slide and can concentrate. How about
Gaussian?
Yeah, Gaussians, exactly. Right? Each of these guys can just be a good old Gaussian, right? What could be a better model for a cluster than a Gaussian, right? It's like, oh yeah, these points are clumped over here, but then they kind of spread around a little bit, right? Yeah, mixtures of Gaussians. So if you have real data, that is the number one thing, is mixtures of Gaussians. Probably more than 90% of the mixture models that have been built in this world, and there's been a whole lot of them, are mixtures of Gaussians. Okay, so that's actually the case that we're going to focus on, when we look at how this is learned. Okay. Mm-hmm.
Do you remember any examples where it's other distributions?
Yeah. So I'm going to mention another distribution, and then we can talk about even others, right? So the second most common one. So this is mixtures of Gaussians. Probably the second most common one is actually the easiest thing to do for discrete data, and this is to have a naive Bayes model. Remember our good old friend naive Bayes, right? Let's suppose that we have naive Bayes, so the same model, except that the class of the example is never observed, right? It's naive Bayes, but I've hidden the class, right? This is a very natural notion of unsupervised learning, right? It's like supervised learning, except nobody told you what the classes were, right? Nobody gave you the supervision, right? So the next most popular alternative, and the most popular for discrete models is, we're just going to look at this whole thing and think of it as a naive Bayes model. In which case, this P of x given Ci is what? We apply the naive Bayes assumption, right? And it's just the product over all the attributes of the probability of the attribute given the cluster. Okay? The class has become the cluster because it was unknown, but you can still think of it as a class. Okay? Everybody get this? Right? Simple idea. Now we're ready to start fitting things. In fact, there's a classic clustering system called autoclass. This was developed at NASA initially for clustering stellar objects like stars and galaxies and quasars and whatnot. And then they made it available open source for people to cluster whatever they wanted. And by now people have clustered just about everything using it. So and you can download it and play with it as well. What autoclass is actually autoclass can also handle continuous data, and it can handle count data and whatnot. What it does is actually a very nice thing. Is it's naive Bayes with a whole slew of options for which model you use for each x. So if some components are discrete, I could use, say a Bernoulli model for binary x's, a multinomial model for x's that have 10 or, a discrete number of values, maybe a Poisson model for an x that's count data, and the Gaussian, a univariate Gaussian model for data that's numeric, right? So it gives you a whole bunch of things to play with. And it also has some Bayesian, techniques for figuring out the number of clusters, right? So it's a very nice thing to have. Okay? So if you want to download the clustering system from the web and play with it, autoclass is probably a pretty good choice. It's not the latest, greatest clustering algorithm, but on practical terms, if k-means isn't working out for you and you're in a hurry, you might do worse things than just use autoclass. Okay? So in general, we can have any distribution. So what are some, what's an example of a distribution that's neither naive Bayes nor Gaussian? Anybody have any ideas of, what it might be for some particular domain? Right, this could be the moment where you invent an amazing new machine learning solution to your problem. Or maybe that'll happen when you go home tonight and are like, opening the refrigerator and getting a beer. In the movies they have this expression, the refrigerator door questions. Have you heard of refrigerator door questions? This is like when you go see a movie, right, and the look looks very good to you, and then when you go home and you're opening the refrigerator, you go like, but wait a second, how come he did this after that? It doesn't make any sense, right? And the thing is that Hollywood screenwriters, they don't care about refrigerator door questions, right? They only care about the questions that come to mind when you're there watching the movie, right? And things are happening very fast, so your brain is just trying to keep up, and you can get away with murder. In fact, another heuristic is that the closer to the finale you're getting, the faster the movie is going, the more implausible things can become. You've probably noticed that, right? But it's like, your brain is getting more and more overloaded, right? So, those phenomena are also relevant to machine learning, right? So what might be the refrigerator door question for you here? It's like, well, let's pick an example of a problem, right? You are trying to cluster visitors to your website, right? E-commerce, right? What I want to know is, how do people travel through my website and how can I cater to them, right? How do I make them go to this product that I want them to buy? How do I, route the right people to the right product? How do I make sure that they don't leave my website, right? What you want to do in that case is you want to cluster people by their sequential behavior. On each page, to which page do they go next, right? So some folks at Microsoft Research, together with a summer intern from, I think, UC Irvine, they built a very nice system that actually clustered, in their case, visitors to the Microsoft, to the MSN website, but you could apply to other websites as well. They clustered people by their sequential behavior, right? Where do I go from the home page? Where do I go if I start out on the news page, right? I want to cluster people by that. And what was the model that they used here? It wasn't Gaussian because the data wasn't continuous. But it wasn't naive Bayes either, right? Because you're really interested in the sequential behavior. What they used here was a Markov model. Well, we're not covering Markov models here, right? But I mentioned them briefly as they're probabilistic models of sequential behavior. That kind of thing gets used in speech and in compile a lot, right? You can also think of a Markov model as the random choices, right, are which link you follow on each page, right? So there were Markov models before, and there were mixture models, and what they did was a mixture of Markov models, right? So that's the kind of thing that you can do. Okay. Questions about any of this? Okay, but now comes the most interesting question of the whole quarter. How do you learn these things? And the reason this is interesting is that this sounds like a difficult new question, right? But it's not. We already know the answer. So, I want you to give me the answer, and the answer has to be 2 syllables. Give me the answer in 2 syllables. How do we learn mixture models? EM, exactly, see? If you constrain the problem enough, right? This I was also trying to illustrate the problem of constrained optimization, right? If you constrain it to 2 syllables, then the optimization problem is not so hard anymore, right? Because you reduce the space. Well, yes, EM, brilliant answer, right? How did you come up with that?
Well, we have the objective function there to maximize the log likelihood.
Very good. So EM, right, is an algorithm for maximizing log likelihood. In what circumstances?
Assuming you have some function that you need to maximize already.
Okay, but remember, we saw EM apropos of learning Bayesian networks with missing values, right? When there were missing values in the data, right?
Sure.
So EM is an algorithm for maximizing likelihood in the presence of missing data, right? So, where's the missing data here? I have my full table of examples, right? It's not like any values of the examples are missing, let's suppose, right? Where's my missing data?
Parameters to the distribution.
No. My parameters are not the missing data. Remember, if I had the missing data, I can infer the parameters and vice versa. But the missing data is like something that's missing in my, data set.
The clusters.
The clusters, exactly. I don't know which cluster each example belongs to. That's my missing data. and now bingo, we can just apply EM. Right, think of the naive Bayes case, right? The naive Bayes case is actually what makes this, connection clear. Naive Bayes case, the way I introduced it was like, let us just do a naive Bayes model where the class is always missing, right? Of course, in the Bayesian network case, it was more like, well, some data points are missing some of the values, right? But nothing says that we can't have a value that is always missing. And that's actually what, naive Bayes mixture models are, right? They're a problem where there's this one variable called the class or the cluster that's always missing. But hey, we can use EM for that. We're going to infer that missing variable, and by inferring that we can infer the parameters and vice versa. Okay? Did everybody get this? This is the key idea in mixture models: is you can just learn them using EM. Okay, so here's a little refresh. Well, so. Let's see how this is going to work for the particular case of mixtures of Gaussians. Okay, so we're going to see what a mixture of Gaussians is, right? And then we're going to see, remind ourselves what EM is, and how we apply it here, right? So we will sort of like first, bring back the general scheme of EM, and then see what it means in particular for learning something like a mixture of Gaussians, right? We're using mixtures of Gaussians as our, example because A, it's the most widely used, and also it's a very nice way to illustrate how this all works. Okay. So what is a mixture of Gaussians? Well, so each of these lines here, right, is a Gaussian, right? So here's one Gaussian, right? And here's another Gaussian. Are these two Gaussians well separated or not so much? Not so much, right? So this is an example where the data is not well separated, but yet, like EM can learn this, easily, provided you have enough data. Okay? So this is, this is going to sort of how to solve yet another of the problems of k-means, right? So the equation for each of these Gaussians, if you remember, is this normalizing constant times x of blah blah minus x, the data point, and right now I'm just doing this in one dimension, right? But in general, this could be in many dimensions, right? X minus the mean of the cluster divided by the variance if you put the square down there as well, okay, or the standard deviation squaring the whole thing. Okay. And here, to simplify things, I'm going to assume that the variance is always the same, right? Which is basically, the variance always being the same is actually assuming, here's a nice question to test your understanding. What in terms of the various restrictions of k-means and of clustering, what does having the same variance for all the clusters mean? Is that they have the same what? Rachel, let me ask you, well,
same volume, maybe? The same... Right.
Yeah, so if a cluster has a low variance, right, that means that it's very concentrated, right? Whereas another cluster having a high variance means that it's very spread out, right? So what I'm assuming here, but it's just to simplify our life, is that the variance is the same for everybody, right? But then there's another issue, which is like the covariance, right? Right? There's the covariance matrix, right? And what does it mean for the covariance matrix to be diagonal? Meaning these guys here are zero. This means that the clusters are what? So this means that the variance is the same in every dimension, right? Actually, I'm actually superimposing two things here. Let's first of all suppose that what I have is the same value, sigma, for all the sigma ii's, right? So this is the variance of each dimension, right? What would it mean for the variance to be different along different dimensions? This would mean that the clusters were, or actually if the variance is the same along all dimensions, what does this say about the shape of the clusters? That they're spherical, right? If the variance is small in one dimension and large in another, this means that the cluster is elongated, right? So very good, right? So you can see how you can start from the k-means case and then make things gradually more relaxed by, among other things, playing with the covariance matrix, right? But now what would happen? So what does it mean, however, that these guys are all zero? Right, so now I'm allowing these things to be different, these sigmas to be different, right? But these guys are still zero. So I can have very elongated clusters, but what can they not be? There's no covariance, right? What does that mean geometrically? No, not non-overlapping, right? They could overlap all over the map, like these two clusters here, right? They overlap a lot. What am I forbidding by making these guys zero?
independency between the independency between those two dimensions.
Yeah, absolutely, right? So, probabilistic, what this means is that they're independent, right? In geometrical, what does that mean? Is that I can have a cluster like this, I can have a spherical cluster, I can have a cluster like this, but I cannot have a cluster like how?
Like tilted.
Tilted, exactly. A tilted cluster is one where there's covariance between, two or more dimensions. And that's what I'm disallowing by having these guys be zero.
So it's either this way, it's either along the x-axis or
Yeah.
along the y-axis.
Yeah. But I remember, in general, you have many dimensions, so it can be along any one of those many axes, but that's all, right? So notice, this is a very big restriction, right? In general, most clusters are not going to be, parallel to the axis like that. However, the great majority of the time that people use mixtures of Gaussians, they use a covariance matrix of this form. So they use it even when it's wrong. And again, this is very common in machine learning, is to use the wrong model. And it's better to use the wrong model. Why is it better?
Overfitting?
Overfitting, exactly. I knew you were hesitating because that answer felt too obvious, but overfitting is never a bad answer. It might not be the whole answer, but it's never totally wrong. In this case, it's totally right? You see what the problem is with allowing these guys to not be zero, is that now instead of n parameters, you have n squared. And if you're Walmart and you have 10,000 products in your supermarket, that vector has 10,000 dimensions. So now instead of 10,000, I'm not claiming that Walmart uses mixtures of Gaussians on there, that actually think they use other things, but anyway, right? Now you have 10,000 times 10,000 parameters. Ouch. Okay? So a lot of the time people just do things this way because that's what you can do. And often, you can do, well enough that way, right? But notice how this overcomes yet another problem with k-means, right? K-means couldn't handle any of these variations. Okay? So, that's mixtures of Gaussians for you in all their multiple flavors. Okay? So now the question is, how do we learn them? Well, as we said, we learn them using EM, right? So here's a reminder of how EM works. You initialize your parameters ignoring the missing information, right? This is, so like the option that we looked at before. It's actually not going to be the best one for us here, but let's hold off on that for a second. And then you repeat the following until convergence. We compute the expectations of the unobserved variables assuming the current parameter values, right? Assuming the current parameter values means that I know for each cluster the mu, the sigma, or the mu's and sigmas, right, if these are vectors and matrices, right? And I know the cluster priors. Right, by the way, having different clusters priors allows me to have clusters with different what? Numbers of points, right? So that's how that limitation of k-means gets addressed, is by having cluster priors, right? In a sense, k-means is kind of assuming that all clusters have the same prior, that idea, okay? So anyway, but let's say that I know my complete model, right? Then the E step is to figure out from that model what? Which my missing variables, right? What are my missing variables? It's for each example which cluster it belongs to, right? So that's what I'm going to do here. I'm going to figure out which cluster each example belongs to. Am I going to make a hard decision like k-means saying like, oh yeah, you belong to this cluster, or you belong to that cluster, or what am I going to do? Remember what EM did with the missing values? It didn't just, assign them, like, oh yes, you're true and you're false, right? What did it do?
Some fractional value.
Exactly, fractional examples, right? It said like, oh, you have a 0.63 probability of being red, right? So I'm going to create 0.63 of an example, and I'm going to, make that the red example. Same thing here. I'm going to say like, oh, your probability of coming from cluster A is 0.6. So I'm going to assign 0.6 of an example to cluster A, right? And then, as usual, we can compute our sufficient statistics, using fractional examples. That's, that doesn't really complicate our life that much. Okay? So my E step is given the model, figuring out how much each example belongs to each cluster. This is often called the responsibility. It's like the responsibility of each cluster for the examples. Okay? Notice how this helps us to deal with clusters that overlap a lot, right? Because for clusters that overlap a lot, if I have an example that's here in the middle, right? I'm not going to say you're red or you're blue. I'm going to say, well, you're red with 0.55% probability and blue with 0.45, which is really what we want to do, right? When you have a point out there in the middle, we can't really decisively say what cluster it belongs to. We can probably say more than just throwing up our hands. In particular, if the point is not over here, well, now it's less likely to be red and more likely to be blue. Okay. So that's my E step. Right? Any questions about the E step? Now, what does the M step do? Right? Remember, the whole idea in the M was that it solved this chicken and egg problem. Right? If you have the chicken, you get the egg, and if you have the egg, you get the chicken. Right? And now what happens after the E step is that I've assigned all my examples to their clusters, right? So now what is the M step? It's estimating the parameters, right? Well, how do I estimate the parameters of a Gaussian given the examples that belong to it? Well, that's really easy, right? You compute the mean. That's the mean of the Gaussian, right? In many dimensions, it has many dimensions, right? And then you compute the variances, right? All these things are very simple, right? That's my estimate of the covariance matrix. Okay? And how do you compute the cluster priors? How do I estimate my cluster priors? Right, that's the other set of parameters that I have to estimate, right? How do I estimate my cluster priors, right? I filled in my missing data, right? And I'm trying to compute my cluster priors. How do I do that?
I guess the probability of encountering that example given the Gaussian that you just solved.
Exactly. So for each example, right, it belongs X% to each cluster, right? So what is my cluster prior, right? It's the sum over there of all the examples, right? If I hard assign the examples to the cluster prior would be the fraction of the examples that it wins, right? There's 1,000 examples, it wins 200. Well, then the cluster prior is 0.2. In general, the examples are fractional, but that doesn't bother us, right? So I just sum up all the fractions of the examples that belong to this cluster, right? Divide that by the total number of examples, and that's my cluster prior. Okay? And now I have a new model, and now I can keep going around this loop, right? And that's my EM for a mixture of Gaussian. Okay? What would change if instead of a mixture of Gaussians we were, say, estimating, a naive-Bayes mixture model? What would change here? Some things would not change and some things would change, right? What would change? Or, if you prefer, what would not change, right? And then we can do the Sherlock Holmes method of figuring out what remains, right? What would not change? I would still run EM, right? And I would wind up with fractional assignments of examples to clusters, and those would give me my cluster priors, right? Remember, the cluster priors are, our general part of the model, right? They don't depend on, the cluster model that you have, right? What has changed here is the cluster model that I'm using, right? So now instead of estimating the means and covariances, what do I need to estimate?
Probabilities.
Exactly. I need to estimate the probability of each example given my cluster. Okay? So how many times does this word occur in this cluster, which maybe is going to be the cluster of sports pages and so forth. Okay? Questions?
So we already knew how many clusters are there.
Oh yeah, so good question. The same problem applies here, right? Everything that we're doing here assumes that the number of clusters is given. If you don't know how many there are, you need to search for them. For example, you could do cross-validation. Try different numbers, right? And now you can choose whichever one gives you the highest likelihood on holdout data. Right? So again, because of the fact that we're building a probabilistic model, there is now an easier way to do this, which is kind of analogous to what you did with supervised learning. There's one thing here which is, usually the way we do this for mixtures of mixture models is not, we don't start by initializing the parameters, ignoring the missing information. You know why? Well, the missing information is missing for all the examples, so how are we going to do that, right? I can't really initialize anything while ignoring the missing information. I don't know what examples belong to this Gaussian, so how can I estimate the parameters of my Gaussian, right? What you can do is initialize my expected values, ignoring the missing information. I.e., I can say randomly assign my points to clusters. You know what people often do, that's actually a good rule of thumb, is they initialize EM using k-means, right? Because k-means is a lot faster than EM, right? The EM is more powerful, but there's a price to pay for that. So what you do is you do a few runs of k-means to find good initializations for the clusters, right? And then you start, turning the EM crank, okay? Or, if you have knowledge or suspicions about who belongs where, this is a good place to bring it in. Questions? All right, so now let's see, in more detail how you actually do this for mixtures of Gaussian. Okay. So initialization, I say choose the means at random. And now what is the E step, right? The E step means I need to compute my probability of each mean given each example, right? This is my filling in the missing data part, okay? So now, I'm going to go through this fairly quickly, but, if you have any questions, please interrupt me, right? So how do I compute this, right? I want to compute P of mu given X, right? But notice that what I have in my model, right, because I have my model at this point, right, is P of X given mu. Okay, so next interesting question for you. If I want to compute P of mu given X, but what I have is P of X given mu, what should I use? What is the famous result from probability theory that answers this question for us? Bayes' theorem. Anyone disagree? Right, so Bayes' theorem says that P of mu given X is P of mu. We know that, right? Times P of X given mu, we can compute that because we have all the parameters of the Gaussian, right? Divided that by P of X, right? So now the only remaining question is like, what is P of X? Do I know how to compute P of X? Remember, P of X is my probability of X irrespective of which cluster it was generated by, right? So how do I compute that? Well, by summing over all the clusters weighted by their priors. So this is not, so what needs to go in here is actually none other than my mixture model, right? So I know how to do the E step, right? So at the end of this step, I fractionally assigned each example to each cluster. Okay? Question? All right, so now I need to do the M step, which is even easier, right? Now that I've, like the whole problem, right, is the missing information that, I don't know, for any given example, which Gaussian it came from. But if I now know which of these examples are red and which ones are blue, or, how much each example is red versus blue, right, then, after that, computing my estimates is straightforward, right? So what is my cluster prior going to be? We already saw what it is, right? It's the sum of the fractions of examples that go to that cluster divided by the total number of examples, right? What is my mu? It's the average of my data points, right? But with one twist compared to the usual just average of my data points, which is what? Right, usually to estimate, the mean of a Gaussian, I just sum the values and divide by n, right? Here I can't quite do that. What do I need to do instead?
Weighted by the probability.
Exactly. I need to do a weighted average, right? The examples need to be weighted by what? By the fraction of them that went to that cluster, right? If I'm an example and only 60% of me went to this cluster, I only count as 0.6 of an example, okay? So my estimate of the mean is just the weighted average of my example values, where the weight is the probability, of the example being in that cluster that I, computed in the previous step. Okay, everybody got this? Okay, and the variance is the same thing, right? Except, so now I'm again going to compute a weighted mean, a weighted mean, right? Weighted by the example fraction as before. Except that now instead of x, what I have is x minus mu squared, right? So notice what I have here is the usual definition for variance, right? And more generally for the covariance, but I'm just showing the simple case here, right? Except that it's weighted by the probability. And that's it, right? So this is your EM algorithm for mixtures of Gaussians.
Is the denominator should be 1, right? Usually. The probability of mu I given xk summed over all.
No, you mean this denominator?
Right. That's.
Should it be 1?
So that's
this
the
is a natural question to ask, right? But let's look at it carefully.
It has the probability that xk belongs to class I.
This is the sum over all the examples of the probability that they belong to that class. So this will generally not be 1, right? If this was 1, that would mean actually disaster. It would mean that all my examples have converged to one cluster, which, by the way, can happen. EM, with mixtures of Gaussians has all these degrees of freedom, which is good, right? Because it's flexible and doesn't have all those pathologies. On the other hand, there's all sorts of ways for it to go wrong. One of the ways in which it can go wrong is, everything starts to collapse together. These guys merge, right? Another bad one is that just in terms of likelihood, right? I could put, a centroid, at each data point, right? And then the likelihood is infinite. Oops. That's not the question that I'm looking for, right? So, it takes a little bit of work often to get a mixture model there, but it's often worth that work. As usual with EM can take, EM for mixtures of Gaussians, as for other things, can take a while to converge, but the first few iterations are usually very, very fast in terms of convergence, and then after that maybe you can just stop, right? So you don't necessarily need to wait, 10,000 iterations for the absolute optimum. You can just make do with the first, 10 or 20. Okay? Questions about mixture models? So actually, let me ask you a couple of questions, right? So, what is, let me, okay, I'm giving you like 2 seconds to look at this very quickly. What is the relationship, right? There was one character there that you have to have noticed, right? That's why I let you look at it for longer than usual. What is the relationship between k-means and EM? Notice that they look kind of similar, right? If you look at the algorithms, you initialize randomly and then you alternate between these two steps, right? So they look kind of similar, right? Is this just an accident, or is there a deeper relationship between EM and k-means? See, the crucial character that you had to see was this one, which means special case of. Right, this makes sense, right? You saw that k-means is making all these restrictions, but what is this? So let's try to look at k-means as a special case of EM, right? So what would the cluster priors be? All the same, right? And what would the covariance matrix be? Identity, right? It's the identity matrix. They're all the same, right? And there's nothing off diagonal is allowed, right? And the means are the means, right? The means of k-means are the means of the Gaussians, okay? And now the whole thing of choosing who to assign to the means and re-estimating my means is the same as before, right? Except for one big thing, which is that big difference. Right, if you look at EM, so what we're saying is k-means is really EM for mixtures of Gaussians with a particular form of the model. The priors are all the same, and the covariance matrix is diagonal, right? The clusters are spherical, and so on and so forth. But there's still a big snag here, which is what?
No fractional values.
Exactly. In EM, we're doing fractional assignment, right? And in k-means, right, the assignment is hard, right? So there's two ways to look at this. One is to say that k-means is what's called hard EM. Hard EM is EM where instead of soft assigning things, you just assign each thing to the most likely cluster. Okay? Or you assign each variable to its most likely value. Okay? And this is not as sound, as EM in particular. There's no guarantee that you'll convert to an optimum, but often it's a very good thing to do. Okay? The other way to look at this, however, is to say k-means is EM in the limit of something becoming very, 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 very small. And what might that something be? Actually, let me give you a hint by putting the covariance matrix here again. So I just said that in k-means, my covariance, if k-means is a kind of mixtures of Gaussians, learned using EM, right? Then I'm using a diagonal covariance matrix, right? So that the classes are spherical and then, have the same size, etc., right? So how do I make k-means converge to a mixture of Gaussians? Right, there's only one free parameter here, and it's my sigma, right? So what happens if I make my sigma very, very small? This means that the classes are very, very narrow, right? Right, the variance is very small, meaning that, right? And now you see what happens is that my fractional assignment is going to convert to something that's not a fractional assignment. If my two Gaussians are like this, right? Any data point, wherever it is going to end up being, 99.999% assigned to one cluster. In the limit, if I let my covariance go to 0, right, my clusters are totally sharp and my points do get 100% assigned to one or another, right? Everybody agree? Okay. So that's the relationship between k-means and EM. So now here's another question. What is the relationship between mixture models and Bayesian networks? Right, we saw that we could use EM to learn Bayesian networks with missing information, right? We saw that mixture models are also kind of probabilistic model, right? And we can use EM to learn them, right? Is there a relationship between mixture models and Bayesian networks? What might that be? And again, you know, I'm going to just give you a powerful hint right here. What might that relationship be? One is a special case of the other, right? Clearly, it has to be mixture models that are a special case of Bayesian networks, right? So here's the more interesting question. If mixture models are a special case of Bayesian networks, what is the graphical structure of the network? Right? Here's my class variable or cluster variable. Ooh, I just gave it away. Darn. Here's my cluster variable, but maybe you didn't notice that, so I'm going to press on. Here is my cluster variable, right? And here's my x1, x2, n, right? What is the structure of this Bayesian network? Actually, I'm being a little, I'm going a little too fast here. Let's take a simpler case, and actually even more interesting case than mixtures of Gaussians. Let's consider the naive Bayes mixture model, right? What is the graphical structure of the naive Bayes mixture model? We already know the answer to this, right? It's the same as the naive Bayes mixture model when the class is known, because whether or not the class is known doesn't change the structure of the model, right? Remember, it's an arrow between the class and each of the variables, right? And which way does the arrow run? From the variable to the class or from the class to the variable? From the class to the variable. Anyone disagree? Oh, that homework is now long forgotten. Because you already aced it, so, right? And you can always go back to the book if need be. Okay? So here's the structure, right? And everybody agree? Right? So a mixture model is actually a very simple type of Bayesian network. So everything that we know about Bayesian networks applies to mixture models as well. Right? But now, like this was a mixture of naive Bayes models. Right? What about, let's say what we have is a Gaussian, right? Mixtures of Gaussians. And let's say that this is my covariance matrix, right? What is the graphical structure going to be? Or, how is it going to change from this one? Let me ask the question in a slightly different way. Is it going to change from this one? Somebody actually has said something here like 10 minutes ago that actually is what we need to answer this question, right? Which is, what does this covariance matrix mean in terms of independence between the variables, given that you're in the cluster? All the covariances are 0, right? So what does that mean about the variables, dependencies?
Trying to fit.
Yeah, condition on the cluster, right? Condition on the cluster, you have this covariance matrix, right? So what dependencies between the variables are there? None. There aren't any, right? They're independent. So the shape of this is exactly the same. You agree? Now, if these guys are not 0, then things start to get interesting. Now I can start to get errors between these guys, and in the worst case, I have errors between all of them, right? I could still summarize this by saying, well, it's always going to have a structure like this, right? This is actually something that's valid for any mixture model with Gaussians of any covariance matrix or whatever. This is my C, and this is my vector X. Right? That vector X could have a lot of internal structure, but, there's one arrow going from C to the vector. Right? So if I think of my X not as, 10 separate variables or, or D, but just one big variable, it's a very simple Bayesian network with an arrow from the class to the variable, right? I have my prior on the class, and I have my probability of the variable given the class. Okay? Questions? All right, so, we've covered a lot already in this class. When we come back in 10 minutes, we're going to look at agglomerative clustering and then at dimensionality reduction. Okay? So it's 8:10. Let's restart at 8:20. Okay, let's continue. The final stretch. There's one very important type of clustering that people often want to do that we haven't talked about, and that's hierarchical clustering. Often what people are looking for is not just a flat set of clusters, meaning a partition of the instance space into clusters, but something hierarchical. think of something like, Yahoo or DMOZ, right? You don't just have one level of topics. It's not like, like politics, sports, science. Then, politics might be divided by country, science could be divided into, physics, biology, etc., right? And this could actually have many levels, right? So how do we induce a hierarchical clustering? Okay. Well, again, there's many algorithms for this. Let me just mention the two most basic ones. And again, they're pretty straightforward. One is agglomerative clustering. The idea, as the name implies, is that you start with each data point as a cluster, right? And then you repeatedly merge the two closest points by some distance into a larger cluster, right? And now that cluster becomes its own, let's say, new center, then you keep on repeating this, right? Now, how exactly you merge the two nearest clusters, you could actually use different criteria. It could be, the minimum distance between the points in the clusters, the average distance between the centers of the clusters, even the maximum distance. And these will all lead to different behaviors, and, it depends on what you want. But the basic idea is actually fairly simple. And then what you get at the end of this is what's called a dendrogram, right? You often see dendrograms a lot in like science papers, where they've clustered, genes or whatever. And a dendrogram is really just a way to represent a hierarchical clustering. It's like this. Here are my data points, right? And what I've done is I said I'm going to start by merging these two. Okay? And then I'm going to merge those two, and I'm going to merge this one with this one, and then this one with this one, and then these, right? And then finally, when it's all one cluster, you end, right? And then the dendrogram actually gives you a sense of, how things get grouped together. In many areas, this is actually a key tool of analysis. Okay? Important note, right? Dendrograms are not as stable as they might seem. A lot of scientists don't actually seem to know this. Right? It's like decision trees. You perturb the weight a little bit, and you could get a very different dendrogram. So don't just believe the first dendrogram that comes out. Do many different dendrograms with, bootstrap resamples of the data, and then see what clusterings there really are stable, and those you can believe. Okay? Any questions about agglomerative clustering? See, this took like 1 minute to explain, right? It's worth knowing, right? And guess what divisive clustering is? Divisive clustering is the same idea, except that instead of going bottom up, you go top down, right? So you start out with all of your clusters in one big cluster, and then you find what is the best way to split this cluster into two? Okay? And then you split each one of those into two, and you wind up with a dendrogram instead of having gone bottom up, you've gone top down. But at the end of the day, it's still a dendrogram. Okay? There is a tricky thing here, which is this operation of splitting things into two could be very expensive. Right? Here's 100 million data points. Please split it into two clusters. How do you do that? In a way that's not too expensive and that's reliable. Not an easy question, but one, as an example of something that you could use something like a min-cut algorithm, right? Think of the data points as a graph, with the weight on each graph being the distance between them, right? And then you find the min-cut, right? Or the minimum weight cut, right? You're going to try to cut the edges that have the smallest total weight, meaning that represent the smallest amount of similarity between the things on their ends, right? So in some sense, what you do is you're going to form the two clusters that have lost the smallest amount of similarity when you decide to split these things. Okay. Again, there's a whole literature on this, but even just a simple version is something that you could implement and use. Okay. Any questions about clustering? Okay, very good. So let us then go on to our final topic, which is dimensionality reduction. So here's the general framework, right? We're given our data points in D dimensions. This is our raw data. And D could be, very large. It used to be that, anything above 3 is considered large because you can't visualize it, right? So, 10 used to be considered large and 100 used to be considered very large. These days, 100,000 is not uncommon, right? Let's say you're clustering your customers, right? On your website, every click is a dimension, right? So if they've clicked, 100,000 times, that's 100,000 data points. Okay? Sorry, 100,000 dimensions for that data point. Okay? So you start out with D, and the goal of this is to convert them to data points in R dimensions, where R is much smaller than D. Okay? And as I mentioned before, the goal here is not just to select the most informative dimensions. is to find new dimensions as a function of the old ones such that they maximally express how this data behaves. Okay? Intuitively, when you go to lower dimensions, you probably are going to lose information, right? Probably a lot of information. So one way to look at it is like, I want to find the dimensions where I lose the least information if I project all my points onto those dimensions. Okay? So that's my goal, is to have minimal loss of information, at an intuitive level. Okay? So that's the general goal. So now let's look at the first algorithm to do this. It's called principal component analysis. How many people here have heard of PCA? This is also called PCA for short. Nobody, which is actually interesting. You have? If you guys were statisticians, which none of us are, you for sure would know PCA. And in fact, for a lot of people out there, both, I don't know, from scientists in various areas, economists and whatnot, the two statistical tools that they use all the time, right? One is in their right pocket and one is in their left pocket. One of them is linear regression and the other one is principal component analysis. So this is what they know how to do. Supervised learning is linear regression, unsupervised learning is principal component analysis. They have something in common. They're both linear. Right? Linear regression is easy because, you're only finding a straight line. That also means that it's very limited, right? Because, you might, the real function might be a very, curvy line. Same thing with PCA. PCA, as we'll see, is linear in the sense that we'll see shortly. Again, that makes life easy. On the other hand, people use PCA for all sorts of things that it's not appropriate for, because the phenomena that's going on there is nonlinear. Okay, so let's see what this all means. Okay, and how you do PCA. But again, like PCA is one of those things that you should always have in your toolkit. You should also know when it is and it isn't appropriate. So here's an illustration of what happens in PCA. Let's suppose that, and I'm going to take the simplest possible case of this, which is when d is equal to 2 and r is equal to 1. Okay? So my high dimension is 2 and my low dimension is 1. Right? I can only see things in one dimension, so I need to reduce my data points in 2 dimensions to 1. Okay? So here's my question for you. So here's my x-axis. I'm going to deliberately draw this slightly so it doesn't interfere with things too much. And here's my y-axis, okay? And now what I have is a lot of, can you see these dots? You have a lot of points like this. Some of these are not quite points, but you get the idea, right? Right? And you want to express these points in one dimension. Meaning right now the points live on a plane, right? You want to make them live on a line. And the question is, what should that line be? Where would you put that line? Will you make it the x-axis, for example? This is what variable selection would do, right? Projecting this data onto the x-axis is going to, confuse a lot of things, right? So what line in the plane would you project this data onto?
The regression line?
Yeah, I will not pursue the detailed technical meaning of that because since that's what we're trying to do. But this is exactly the answer, right? Like what you mean by the regression line, right? Is at a geometric level is basically this line here, right? Notice that it's a diagonal line, right? But it's the line that all of the data is kind of close to, right? It's not so much that we're looking for y as a function of x, right? This is not what we're doing now. So strictly speaking, it's not the regression line, but kind of looks like it on this diagram, right? So this is the intuition, right? This is a good line, right? So what would you think if instead of this line we chose this? Give me a second here. What would you say if instead of that line we chose this one? Would you like that? So notice what all there is to know about PCA at some level is right here, right? So you want to lose as little information as possible, right? So if my line is the blue line, right, what happens is that this point got projected over there, right? And this point here got projected over there, this one got projected over here, right? Now, if there was another point here, it would also get projected over here, right? And that's the information that we lost, is how far from that line you are, right? So in some sense, what I want is a line that kind of, is as close as possible to all these points, right? And, here's the thing, right? What would happen if I was projecting onto this line, right? Now this point would become this point, right? There'll be a whole pile of points that would basically now bunch up on here, right? So if, moral of the story, if I pick the red line, there's a lot of information loss, right? In some sense, I want the line of least information loss, right? Everybody got this intuition, right? And notice that picking the x-axis, is kind of intermediate between this. It's not a total disaster, but clearly we can do better, right? We can use the blue line, okay? So that's the geometric intuition, right? Now the question for us, like, well, how do we formalize this, and then how do we solve the problem, right? In some sense, so let me actually look at this in a way that we haven't before, but it's sort of like, really what's at the heart of PCA is like, let's think of this in terms of the variation of the data, right? I want to find the lines that best account for the variation in my data, right? The data is varying in 2 dimensions, but if I only let it vary in 1 dimension, how do I best find the line that captures most of the variation, right? This is the problem that PCA is trying to solve, and in fact, by variation, what we mean is variance. Right? This data has a lot more. This is technically what's going on here, is that the direction that I want to pick is the direction of maximum variance. Right? We were just talking about, Gaussians and the covariance matrix and whatnot, right? This is the direction in which the variance of the data is highest. Right? Which means it's a direction that leaves the least variation for the others. Okay? So that's what I want to do. I want to find my directions of highest variation, or highest variance to be more precise. So how do I do, any questions? So how do I do that? Well, here's what you do. And again, I'm not going to do, sort of like the detailed, derivation of this, but, I'll tell you what the algorithm is, and hopefully it'll make some sense. A lot of it will not surprise you. Number 1, I'm going to compute the mean and the covariance of the data, right? Surprise, surprise, right? Since this is really what, I'm going to be playing with, right? Everything is going to follow from the mean and covariance of the data, right? Depending on the covariance, the mean of the data tells you where that cloud is, right? And the covariance data tells you which way it's pointing and where it's long and where it's short, right? That's actually what, what we really care about is, this dimension, has a lot of variation, and this dimension doesn't have so much variation, okay? And notice now the next key thing is that how do the red and the blue dimensions relate to the original dimensions, which are y and x? But this is what I need to do, right? I need to go from y and x to my new, let's call them y prime and x prime, right? Or in this case, right, this is, I just want, let's call this a z, right? I want to try to find my z as a function of y and x. So what is z as a function of y and x? It's a linear function, right? Z is, a translation, rotation, scaling of the axis, right? How do we find the new axis as a function of the old ones, right? What we're doing here is really just linear algebra, right? Again, here I'm just trying to find one, but in general, I would have many dimensions and I'll be finding a new set of them, right? What I'm going to have is a matrix, right, that transforms the first set of coordinates, or points in the first set of coordinates of dimension d, right, into points in the second set of coordinates with dimension r. Okay? So this is what I'm trying to do here. I'm trying to find the transformation, right, that produces these new dimensions, and that captures most of the variation. Okay? So, how does this happen exactly? Well, so first step, I've computed the mean vector in the covariance matrix, and now this is where linear algebra comes in. The next thing I have to do is compute the eigenvectors and eigenvalues of the covariance matrix. And now we have, an if-then statement. If you know what this means, you're probably happy. If you don't know what this means, don't worry about it, right? Think of it as, you throw this into a linear algebra package and outcome the eigenvectors and eigenvalues, okay? It'd be nice to explain this at a deeper level, but we don't have time for that here, and then at some level it's not necessary. Let's just say that, what do the eigenvectors and eigenvalues represent? They represent exactly what we want. Again, I'm not going to show that here, but hopefully, there's some intuition, right? The eigenvectors are going to be the directions, the successive directions of greatest variation of the data. So in particular, blue is going to be the eigenvector with the largest eigenvalue. And then red is going to be the eigenvector with the second largest eigenvalue. And so on if there were more dimensions, but in this case there aren't. Right? So notice that the first thing that I'm doing here is actually just re-expressing the data in these new axes, right? So I used to have, x and y, and now I have, let me actually, instead of calling them z, let me call these, oops. U and v, right? U and v is just a new set of axes, and I can compute these axes from the old ones by, a linear transformation. Okay? But so far I haven't, noticed there were two of x and y, right? And there's one of u and v, so there hasn't been any dimensional reduction so far, right? But this is where the key step happens. Everybody with me so far? Okay? What is the key step? The key step is that now I select the top R eigenvectors. Right? I select R is my target dimension, right? Let's say it's 3. I select the 3 eigenvectors with the largest eigenvalues. Why? Because those are the ones that, according to what I just said, actually capture the most variation. Right? In particular, in this example, right, if I wanted one vector, right, I would select U because it has the largest eigenvalue. Okay? Now, if your linear algebra is a little bit rusty, it might not be completely, clear to you why this happens. So, just believe me that this is what the linear algebra is actually doing for you. Okay? And, and if you want more dimensions, you can just take more eigenvalues, more eigenvectors, the corresponding eigenvalues. It is often the case that there's a bunch of large eigenvalues which you clearly don't want to ignore, and then it dies down very quickly, and there's a bunch of very small eigenvalues, which is kind of the noise, right? So often, if you imagine plotting, the curve of the sizes of the eigenvalues, it often looks like this, which means that that you want to remember, like maybe let's say these are the first 4. Those capture most of the variation, and the others are kind of noise. So anytime there's a knee like this in the data, you're in good shape because you kind of know what the natural dimensionality of the data is, right? Another way to think of dimensional reduction is that you're not just trying to reduce it to 3 dimensions so you can see it, is you're trying to ignore the noise, right? And if you think about this diagram here, what happens is that these points basically live on the blue line, right? And then there's some noise, right? They're a little bit above or below, but that mostly doesn't matter. The way you find the dimensions that matter is like by plotting the eigenvalues and seeing like, well, where are the big ones? And after that, I'll ignore. Okay? Everybody with me so far? Okay, so finally, I project my points onto the subspace spanned by these eigenvalues. By these eigenvectors. Okay? So I want to see my points in the new lower dimensional space, right? They were in x, y space, and now I want to put them in u space. How do I do that? Notice, I subtract the mean, and then I multiply by this A, which is the matrix of the eigenvectors. Okay? Because I'm going, again, if you remember linear algebra, this should be fairly straightforward. Like, I'm not, I used to have my vectors expressed in the x, y basis, right? I'm now expressing them in a new basis, which is formed by the eigenvectors, right? And the how are those points expressed as a function of the old ones? It's the matrix A, right? So in order to express my points as a function of the eigenvectors, given that they're expressed in the original dimensions, I need to multiply by the matrix A, right? The matrix A is the matrix that transforms points from the original space to the new space. Okay? Again, if your linear algebra is rusty, ignore all this. Just remember that A is the matrix of the eigenvectors. And very important, you have to subtract the mean. People sometimes forget this. There's actually an infamous example of someone who didn't subtract the mean, and it's the famous hockey stick curve of climate change. Have you heard of that? That hockey stick curve was a principal component analysis, where the temperature was the principal component, and the guy didn't subtract the right mean. Shocking, huh? He actually, people often forget to, subtract the mean, period. What he did was actually, he didn't subtract the mean of all the data. He subtracted only the mean of some of the data, okay? This is a paper published in Science, right? So scientists make mistakes, right? So, why is it that you need, so, if you forget to subtract the mean or subtract the wrong mean, you're in good company. Nevertheless, you don't want to make that mistake, right? Why is it that you got to subtract the mean? What is the thing that will go terribly wrong if you don't subtract the mean of the data, right? Let's suppose that my xy axis, instead of being here, were like over here, right? Let's suppose that this is my x-axis and my y-axis are these, right? In the first example that I drew, the mean of the data actually wasn't 0, 0, right? And that was devious so that, we wouldn't have to deal with this problem, right? What would happen if x and y were actually here? Right, actually, I'll even give you a better example, which is let's suppose that that the x and y axis were like way over on that corner. Right? What would be the principal components that you would find in this case? Would they be the right ones? Actually, let me. There's an even better example of this. Let me just quickly draw it. Let's suppose. Let me draw it over on this corner, so I don't erase this one. Here's my x, here's my y, okay? And let's suppose that my data are like this. Right, you see what I'm doing? I'm doing this little nebula over here, right? So the direction that I want, right, is this blue direction over here, right? You agree? However, what is the principal component that my algorithm is going to find? Right, think of each point as being a vector from the origin to where the dot is. Right, the points are all over here, right? So my principal component is going to look like this. Oh, yikes. This is totally the wrong thing. Right? If you don't subtract the mean, your principal component is just going to be the direction that the data is in from the origin, irrespective of which direction the data is actually oriented in. It's not what you're looking for. Everybody got this? So, moral of the story, don't forget to subtract the mean. Questions? Okay, so this is one technique, by far the most widely used dimensional reduction technique. Like a lot of popular techniques, it's used when it's appropriate and it's also used when it's not appropriate. But let me mention one other. So, the other thing that we saw here is like you see why PCA is a linear technique, right? It's just doing a linear transformation of the points. If you think of this as getting rid of the noise, right? This gets rid of the noise when your data is on a hyperplane, right? Right? If the data is like on a little bit above and below the hyperplane, this will project things onto the hyperplane. But if the data doesn't live on a hyperplane, if the data lives on what's called a manifold, right? Let's suppose that the data lives on a very curved surface here, right? Then PCA is, not the right thing to do, right? It's just like, the perceptron and the multi-layer perceptron, all these things, right? The linear is good, but it's limited. Often things do not live in linear land, okay? But before we go on to the nonlinear case, let's just look at one more linear technique, right? Which is probably the second most popular one relative to PCA. And in many ways, the result, they're closely related. The results that they give are often similar, right? There's in fact conditions under which they're equivalent. But, many people don't know about PCA. They use what's called multidimensional scaling. So depending on the field that you're in, right? You might see everybody using PCA or everybody's using multidimensional scaling. And what is the deep reason for the choice of one or the other? It's what they learned in school. But here we follow our usual policy of like, we give you all the tools so that you have them in your toolkit. And you know what things can be used. Okay, so how does multidimensional scaling work? It's a very intuitive idea that superficially is very different from PCA, extremely different, right? And it's the following. Let's say and again, the same high-level theme is I want to find a projection onto low dimensions that loses the least amount of information. But the way I'm going to formalize this notion of losing the least information is going to be different. In PCA, I wanted to capture as much of the variance in it as possible. Here, what I'm going to try to do is preserve the interpoint distances. Right? Let's say the important thing is how far points are from each other in the original space, right? That makes sense, right? But now when I project to a lower dimension, right, this is going to mess with those distances. What I'd really like to have, if I could, is a miniature of the exact original data set, but in fewer dimensions, right? Where the distances were preserved exactly. Right? That would be nice. Right? And in fact, if the data do live on a hyperspace of the right dimension, you can do that. In general, you can't do that, because they don't or because there's noise, right? But then what you can do is you can try to find the points in the new lower space where the distances are as similar to the true ones as possible. Okay? This is the idea of multidimensional scaling. Right? It's called multidimensional scaling because you're rescaling the data and you're doing it in multiple dimensions. Okay? Everybody got the basic idea? Okay, so here's what we're going to do. Right? Let's say that my xi's are the points in d dimensions. My yi's are the points in r dimensions. So the xi's are my original points and the yi's are my reduced points, the points in the low dimensional space. And let me call delta ij the distance between xi and xj in the original space, and dij the distance between them in the derived space. Okay, everybody with me? Okay. So now what I want to do, right, is I want to find, what am I looking for? I'm looking for the coordinates in the new space, right? So the problem is to find the yi's, right? I want to find the yi's that minimize the following error function. So this is an error function. It's a function of my y vector, right? This bold y here is like, my matrix of y points, okay? What is this? This is the sum over all data points, right? Over all data points in my space of the difference between the point in the old, between the 2 points in the old space and the difference in the new space, right? So dij minus delta ij normalized by delta ij and squared, because people, really like squared things. They, they're smooth and at the same time, they're always positive, it gets, and so on and so forth, right? You got the idea? So this is our goal, right? Our goal is to find the y's that minimize this. Okay? Now, question to you. So what do we need to do, right? So we've defined our representation, right? It's the reduced space. We defined our objective function, is this thing here. Now, how do we optimize it?
Yes, I do. How well?
I did not get any signal from that noise. What do you think? This is a continuous function, right? It's the error. It's a function of a bunch of continuous variables, right? So what do you want to do when you want to optimize a continuous function of a bunch of continuous variables?
Take derivative with it.
Yeah, exactly. You do gradient descent, right? Right? Right, we saw gradient descent apropos of learning a perceptron, right? I was trying to minimize my error as a function of the weights, right? And I take my steps in the gradient, I compute my derivatives, right? Until I'm at the optimum. Same thing here, right? Except that the error function is different. And now it's not a function of the weights, it's a function of the y's. But, the technique is still the same. And moreover, this is still well behaved because guess what? I have a quadratic function with a single global optimum. Okay? And that's multidimensional scaling for you. Did everybody follow this? It's fairly straightforward, right? It has this very nice feature that's it's invariant with respect to translations, rotations, and scalings of the data. If you think about it, right, your low-dimensional representation of the data should not depend on where they are in the original space, right? Or how large or small they are, because all you really care about is the relative distances, or of how they're oriented, right? Because the orientation doesn't depend, the interpoint distances don't depend on the orientation of the whole thing, right? And so, it's easy to see that multidimensional scaling has the property that, it doesn't care about what these things are. Okay? So you don't have to subtract the mean or renormalize or any of those things because, in a sense, the multidimensional scaling by itself does all of that. Okay? Questions?
Does it perform differently, like in terms of runtime than PCA?
Doesn't, because again, the computation that these things are doing at the end of the day is pretty similar, right? The question is, so I said, you can do this using gradient descent, right? And what happens in a PCA is that you have to do this matrix computation, right? And there's many different algorithms that you could use for that, right? In fact, you can actually use gradient descent to do that thing itself. And if you use it, then it kind of boils down to the same thing, right? So the precise answer to your question is, well, it depends on exactly which algorithm you use to do each of these things. Also here, instead of gradient descent, you could use, a quasi-Newton second order method and whatnot, right? So the short answer to your question is they're similar. The more detailed question is, well, it depends on exactly what algorithm you use for what thing, but you could actually use pretty much the same algorithm, suitably adapted for both, in which case they are similar. Okay? More questions? Very good. So now let's look at our last thing, which is nonlinear dimensionality reduction. This is what you don't learn in your, stats, multivariate, even some of your more advanced stats courses. If you're at a place with UW that has a world-class stats department, then you will learn these things, but in other places you might not, right? There's a lot of people out there, a lot of, practicing scientists and marketers and whatnot that really should know nonlinear dimensional reduction and don't. So what do? They get PCA or their, it's their hammer, and they try to hammer everything with that, everything looks like a nail. Or it looks like it doesn't exist. Just like a parabola looks like it doesn't exist if you try to do linear regression. Okay, so finally, how do you do nonlinear regression? How do you do nonlinear dimensional reduction? This is, of course, a much more recent area than PCA, which goes back to, the 50s or something, and multidimensional scaling. And nevertheless, in the last, 10, 15 years, there's been a whole explosion of algorithms for this. I'm just going to tell you about what is probably the most famous and widely used one. And in some ways, it's sort of like what set this off. We briefly mentioned last time, by the way, that one thing you could do was, remember when we were talking about the kernel trick and I said we can apply this to other things besides SVMs? One of the things you can do is apply to dimensional reduction. Well, actually, at this point, you can kind of know how that would work, right? You can do PCA on the kernel space. You transform your things by the kernel, and then you PCA on that, and now you can actually learn to project things onto a manifold that, could be very far from a plane, right? Why can you do that? Because those matrix multiplications, at the end of the day, they boil down to doing dot products, right? Well, those dot products are what's going to be replaced by the kernel, which means you're doing dot products in the new space. Okay, so this is actually one technique that's kind of, easy to describe. But let's look sort of like at a native nonlinear dimensional reduction technique. And also one that, the basic scheme of this algorithm, appears in many others. Okay? And it's a very, at heart, it's just one idea, and it's a really, really powerful idea. And here's how it works. So, our goal is to find our best projection of the data onto a nonlinear manifold. Right? What does this mean? A hyperplane is a linear manifold. Okay? So let's suppose that my data points live in this room, but really they all came from a point that goes from, the ceiling over there to the floor over here, right? It's a plane plus a little bit of noise. Then PCA or, MDS will work just fine, right? But let's suppose that the surface that the points really live in is something that moves like a big, bowl, right? The points live in a bowl, right? Again, they come from the bowl, plus or minus a little bit of noise, right? PCA, for example, will just say like, oh, you guys just look to me like you're on a flat plane with a lot of noise, right? PCA basically is blind to what's going on. What we would like to do is discover this surface, right? And also discover sort of like the coordinates by which we can refer to points on that surface, right? Maybe that later one we don't need if we just want to visualize the data, but it might also be something that you want, okay? So now we're trying to project our data onto a low-dimensional manifold, not just a hyperplane. And there's a lot of phenomena out there that's exactly how you got your data. They came from a low-dimensional manifold, and then they got a lot of noise added. Like here's an example that might not be obvious to you, but kind of illustrates the power of this. Your visual system, you could say that this is what it's doing. It's doing nonlinear dimensional reduction. Because let's say you're looking at faces of people, right? A face of people is, let's say, a million pixels, right? Each of which has RGB values, right? So it's a very high dimensional point, right? But the faces of the people were really just generated by a small number of dimensions, like, how far apart the eyes are from each other and from the nose, and whether they're smiling or frowning and looking to the right or the left, right? It's a very complicated manifold, but it's much, much lower dimensional than, a million pixels, right? There's maybe 20 key dimensions by which you can generate a face. And what you want to do is discover those dimensions. PCA and MDS are incapable of doing that. Things like isomap can actually do that. People have actually done experiments where they do this for faces, and it's like, see, This dimension here is whether the face is smiling or frowning. And so at one end, for x equals 0, let's say they like, and then they go. And, and let's say the y direction is, which way they're facing. So, like, as you move on the y direction, their face looks like this and this and this. So those are just two dimensions, of course. This, if you generate the face, is mainly varying about, as to how they're facing and whether they're smiling or frowning. But this can actually be done. Okay? So, how do we do it? Sounds really hard, right? And indeed, for many decades, people didn't really have very good answers for how to do this. There were some things that people proposed, for example, things like the autoencoder, right? The autoencoder, the autoencoder network, in a way, is also doing a kind of nonlinear dimensional reduction, right? But the truth is, it didn't really take off. What took off is what I'm going to describe now. Isomap and things like this. So here's the idea, right? What I'm going to do is I'm going to construct what's called the neighborhood graph of my data. My data are, living in Euclidean space, right? He's actually, like, let me pick a very simple example of things, right? Let's suppose that this is how my data are, right? There's a big clump of them here, right? Or actually, let me just pursue this. Well, let me redraw this in a slightly better way, right? Here's an example that is very simple, but really shows you what you can and can't do with different kinds of dimensional. Let's suppose that the points live on a spiral, right? So the points are like, let me actually first just draw the spiral itself. So here's the spiral, right? And now let's suppose that my data points live on this spiral, so let me draw those in blue, right? But with some noise, right? You see what I'm doing? Right? You can see that for any linear dimensional reduction technique, this is totally hopeless, right? Well, all I can see, like, if you take out the spiral, right, and just look at the data points, linear techniques can only see that this thing lies on a plane, right? And that you and I can very well see the black curve from which these points came, right? It's that spiral that you want to discover, right? So how do you do that? So here's the, the whole problem, right, is that just looking at Euclidean distance is, like, doesn't, like this curve here, right, is very nonlinear, right? So here's the trick. You form the neighborhood graph. What is the neighborhood graph? For each pair of points, I'm going to measure its distance. Let's say just its Euclidean distance, okay? So far, nothing interesting. But now what I do is I draw an edge in the graph if the distance is less than some epsilon, than some small value. Okay? This is so simple, but it's so powerful. You know why? Because here's what happens. These points, right, are going to have edges between them, right? Because they're close to each other, right? So I'm going to have a graph where all these guys are connected to each other. But, for example, this point is not connected to this point, right? Because this is above epsilon, right? So what I need here, and surprise, surprise, the choice of epsilon is going to be crucial, right? I need an epsilon that's larger than this distance, but smaller than this distance. So that the points that are next to each other on the spiral get connected in the graph, and the points that are, sort of like on different turns of the spiral do not get connected, right? If I make my epsilon very large, well, this just becomes, the same as using plain Euclidean distance. If I make the x very small, if I make the epsilon very small, then, this all becomes disconnected, and I'm not going to learn anything useful from that either, right? But with the right epsilon, then what I do is I now compute the shortest distances along the graph. Well, this is a graph, right? Now what I have is, forget my original Euclidean space, what I have is a graph. And I'm going to compute the distance between points by only following edges in the graph where the edge is labeled with the distance on it, right? So the important thing is, for example, these 2 points are going to be very close, right? Because the distance along the graph is very small. These 2 points are going to be very far away, right? And these 2 points, for example, they're going to be, this point and this point are going to be very far away, even though, directly they're kind of close, right? So now I've just re-expressed the distances between my points as being the distances along this graph. Okay, are you with me so far? And now final and amazing step. So, like, I can use something like Floyd's algorithm, shortest paths algorithm to compute that, right, in polynomial time. And then I just apply multidimensional scaling to that distance. And that's it. multi-dimensional scaling applied to that distance will basically put all these points on a straight line where, like this is one end of the line and this is the other end of the line, which is exactly what I wanted. So what was the trick here? The trick here was to change the space into a linear one, from a nonlinear one into a linear one by doing this neighborhood graph thing. Okay? Everybody got this idea? Very simple, extremely powerful. This type of thing can actually learn to decompose your face into, its various aspects. On a good day, right? These things can also fail, but, you can actually do things with this that people couldn't dream of 20 years ago. Questions?
How do you choose epsilon?
Yeah, how do you choose epsilon?
Cross-validation?
Yeah, which in this case, remember, you don't have a clear objective measure, but what it means is like you have to try a bunch of epsilons, right? And probably for some of them you'll get, degenerate results, right? That's because it all becomes, the same, Euclidean plane, right? Or because you get a bunch of separated things, right? Notice that if you get a bunch of separate clumps here, this is very bad, right? Because there's no communication between them. So you have to try different epsilons until you find one that when you run the algorithm with it, this produces an interesting lower-dimensional space. So there is no great recipe, but indeed, this is sort of like the crucial parameter that this depends on to work. But if your data, but the moral of the story is like, it's okay for your data to live on a very complicated surface, as long as it doesn't diverge from that surface a lot, because then there's an epsilon that will capture the within surface distances and keep the off surface distances outside. Okay. More questions?
So following this question, so if they're clumps, then you could, if you set the epsilon high enough, then you're going to get the wrong results, right? Because then you might be, in that example...
No, small clumps is when I make the epsilon very small, right? Because then these guys might become disconnected.
Oh, so one example, maybe if the data is kind of separated along this...
Well, then what happens, right? So what's going to happen here, right, is that the distance between these points and these points is going to be infinite. Right? These are separate clumps. Right? So there's no way to express them along the same dimension. So what we're going to have, in essence, is a different, dimension or set of dimensions for each of these. Right? Which is not what you want in this case, hypothetically, right? It's basically kind of giving up on the problem.
But if you increased epsilon so that they are connected, then you could be connecting in this example for, across the line.
Yeah, and that's what you don't want, right? So hopefully there's so the problems that you can do this with is where there's an epsilon that connects within the line but not across, right? If the noise is large enough that you start connecting across the lines, then you're host. Right? Again, this doesn't always work, but there's many conditions where it does work. But in a way, whether or not this works depends less on whether the data, on how nonlinear the data is. It could be very nonlinear, like the spiral. It just depends on how noisy it is. Right? By noisy, we mean that, like, how far does it differ from actually truly living on that manifold? The manifold is very nonlinear, but the data really lives there. You can find an epsilon that works. But often what happens is that, well, that manifold really, there's more detail, and I could have gone further, right? So the epsilon that you set may also depend on the amount of data that you have, right? And how much detail you want to capture. Okay. Any other questions? All right, our time is up. It's been a pleasure. I hope that you enjoyed taking this class. And I hope even more that, you find good applications for this in the future. And if you do, let us know. Okay? So please keep in touch. There's, of course, one last thing left to do, and this is the class evaluation.